minimize, subject to some constraints that are problem dependent. And this is used to simulate motion in a realistic manner. So I don't know whether this is going to play, but like, you know, these are, this is a reel from some of my collaborators who worked on a method called IPC, which basically does like cloth simulation and non-rigid body simulation in a very realistic way. But the energy here, I have to stress, is like completely made up. It's just like, oh, I wonder what it would look like if we had this energy, and then let's try to minimize that. And it turns out that it looks great. Let me stop that there. And okay, so part of why that stuff works so well is this notion that the physical world is sparse, right? And I think Saman touched on this. Fred has this in their slides. I'm going to phrase it as a question. Is the physical world sparse? Not that the physical world is sparse. But the core piece of why these things work as sparse methods is because for most of the energies that are being optimized, you try to take a local view of that energy. You don't try to kind of minimize the whole thing. Each point is kind of interacting with this set of neighboring points or triangles and so on. And then you have an energy that is summed over that entire thing, right? So you have this notion of local influence, and that is where the sparsity arises, right? And that's where we come up with these connections to the physical world. So often when you construct these energies and these problems, what happens is that the gradient or the second derivative in other problem formulations is what is sparse, right? And our tooling that we have for this really does not do a great job of treating the world as sparse. Generally what we have is tools like Simit and TinyAD, which came out of the SIGGRAPH community, where for specific kinds of structured sparsity, you have tooling that can do this, but you have to really like kind of squeeze your problem in a specific way to get it to fit into that paradigm. And for many of the energies that we're interested in, that just doesn't work. You have to kind of hand code it. So what do these folks end up doing? They spend countless hours. Basically, you create this energy function, then you have to derive its gradient. And how do you derive its gradient? Well, the problem with using things like AutoGrad here is that they don't really understand that the gradient is sparse, right? So you end up with a dense gradient and an intractable problem. So what people in this community really do is spend days and weeks with Mathematica. If they're lucky and Mathematica works, they get this really gross equation out, and then you have to hand translate that into C, or if you're lucky, Fortran. And that, that's kind of what people do. So you go to SIGGRAPH, you see all these papers where it's like, hey, look, here's my new energy, here's why it's so great. Usually why it's so great is because they've also been able to come up with a formulation that takes it from a sparse problem to a dense problem. And why do they do that? Well, because the tooling, like I said, doesn't really support sparsity, but also the core algorithm here is often direct solves, right? And sparse direct solves are pretty finicky to work with. There's a few packages with onerous licensing agreements, which is why people don't use them. But it's also just a matter of the factual, like the software engineering aspect of it is that if I have to use a sparse direct solve library, I'm probably copying data from somewhere into that format, then I'm calling that library. So if I'm going to do that data copy, I might as well just figure out a projection into a dense matrix or a dense tensor and then project it back. I have to do copies either way, right? So it's not really saving any performance avoiding those copies given today's tooling. Okay, so I'm gonna kind of shift a bit, but I'm gonna come back to this. There is a point here. Okay, so at the same time, all of this stuff is going on with that community, which, by the way, I'm not sure that there's a lot of representatives from that community here today, but I think it's really interesting for people who work in sparsity to kind of interact with those. I know Gilbert, I would count as part of that community, at least a foot in there, but I think like there's a lot to be learned from like the actual difficulty of doing these problems, and maybe we can come up with better tooling. You know, PyTorch for these kinds of problems would be amazing in terms of increasing productivity of many people in graphics. So just taking a little aside in ML architectures, right? So there's like this paper that came out in PMLR by Philip Isola very recently, which has this like kind of very interesting hypothesis. So they have these two observations. The first is that if you look at neural architectures today, they're kind of converging on transformers. And I mean everything, right? Everything from vision tasks, large language models, generative image, generative video. They're all basically shoehorning those things into this like transformer architecture. But what's even more interesting that they observe is that the representations learned by these different kinds of transformers have similarities, right? So their hypothesis is this Platonic representation, which is like there is a true representation of the world that all of these networks are learning regardless of the domain. Like it doesn't matter whether you're talking about language, imagery, video, there is something in the representation of the world that that model is learning that is reflected, and maybe is the truth about the world. I'm not going to go so far, but I think it's a really interesting observation there. The thing that I will add to this is that these feature vectors have to be sparse. The entire world of things, you can't be everything, right? You could only be a subset of things. It's like a red ball is not maybe it's close to a blue cone, but it's not like a table or something, right? So there is something about what a thing is that is also sparse. But also in this field, the dense representations dominate all the implementations, right? There's been a whole bunch of research recently about sparse attention mechanisms, because this is the core computational bottleneck of transformers, let's say, in many different transformer architectures. For those who aren't familiar, what this essentially is matrix times matrix times matrix multiplication, right? So it's a lot of flops, super expensive. But again, a thing can't be that many things, right? So like you have this dense matrix times another dense matrix times another dense matrix, and really the things that matter are just a few of those entries, right? So people have been, working on sparse implementations. Here's, one paper that was looking at translation between two languages, and the feature maps in the attention are extremely sparse, right? So they built a specific sparse transformer implementation that they wrote about, but there's a lot of papers like this that have come out recently. The thing I will point out is that none of them use any of the tools we work on in this room because, well, reasons. They all are writing code by hand, primarily targeting GPUs. And it's painful. It's extremely painful to write this code. I had the unpleasant experience of writing code like this recently, and it's not something I want to do ever again. And I was using, a small abstraction above CUDA. There's a language called Triton, which makes it a little bit easier, but it's like not what I want to be doing. So that kind of brings me to like, what is the hurdle here? Why aren't any of these things using that, right? It's basically that none of our tools are maintained in terms of their correctness. We don't really have a robust compiler for this, and it's a chicken and egg problem here, because if we had robust compilers, then we would use them. But if we use them, then we would have robust compilers because we'd fix the bugs, right?
So when you say correct, the side what provably correct? Or yes.
So here's where I'm getting to here is that even for our theories about how to do sparse compilation, we don't actually know that they're correct. We believe they're correct. We've implemented them in more than one system, but we don't have a proof of correctness here like we do in other areas of lowering, right? Code generation. So something to think about. But given all this demand, I do wonder, and I swear I did not talk to Saman before about this, but I do think we're approaching like kind of this important moment for sparse computation. You know, one of the languages I work a lot with is called Halide, which Saman mentioned, which is a language invented at MIT that you know, is great for dense image processing. And it really allows users to explore the space of optimizations, excuse my typo, across different architectures. And you can do this rapidly. It still requires you to understand performance programming. It's not automatic. You have to dictate what the loops should look like, but you can easily alter that loop structure. So this came about at a similar moment where there was a real need for this kind of thing. Also, there was Andrew Adams, who is the smartest person I've ever worked with, and therefore like understands both the image processing algorithms and the performance part, and can write the compiler, you know, or at least like make the compiler more robust across those two things. Okay, so I've talked about these two like areas where sparsity is really important. I think, yeah, there's a great moment here maybe for sparse computation, but there are some headwinds and maybe potential opportunities. So the first is that GPU tensor cores are by far the most compute dense thing available to any of us these days, right? These 88% of flops are in the tensor cores at 32-bit. I'm comparing apples and oranges. It's actually more than 88%. But if you go by their marketing numbers, let's say 88%. The other thing that people don't talk about is that memory bandwidth is still really important, and that actually is an opportunity for us, right? Why are we moving across all these zeros? But many transformers are actually bottlenecked by memory bandwidth for various reasons. A lot of times it's the smaller parts of the transformer, but huge opportunity. And like I said, sparse direct linear solves remain a core bottleneck of quadratic programming. That is a little bit harder. As far as I know, there is no common infrastructure for writing sparse direct solves, even dense direct solves really. So there's research to be done there. But I think in this moment of like, you know, at least for me, many of the domains that I work in, there's a huge opportunity here. And also the tensor core thing, I will say, that may point us in the direction of what NVIDIA likes to call structured sparsity, but really, you know, BCSR has existed for many, many years. If we have blocks, we can do better than just, you know, plain sparsity. So what will it take to get there? I don't know, you guys tell me. I think that's kind of where hopefully we could fill it in. I'm happy to talk more about it. But I do think, you know, giraffe with a funny face aside, I do think that there is an important opportunity here that comes around correctness, right? The problem with using any tool is if I can handwrite code that's faster, then I may still use the tool if the tool is more correct than me handwriting the code, right? So we really have to make sure our tools are robust. And that's basically all I wanted to say about this convergence moment. And I did want to give a shout out to this artist who made this piece of work that I'm using for background. Robustness. So, you know, I will say this as a co-author of papers, but I've reviewed many papers this year that tried to compare against works that I co-authored, but nothing works, and I can't blame them for that. That's our fault. But yeah.
Is it more of a feature thing like sparse left-hand side type things, or is there things that you claim to implement is not working properly?
Both. So I mean, for example, like there's kind of basic things like BCSR times CSR that we just don't know how to do correctly in this formulation. And then there's also just things that like we implemented and then never ran the test afterwards.
So it's more of a testing thing and proving correctness.
I would say that testing and proving correctness will get us on the path to being able to solve the other problems.
Oh, I got this. Yeah, should be good. Okay, hopefully the color's all fine. Nice to see everyone here. So Saman had this wonderful intro where he said, here's an idea, here's another idea, here's all these great ideas we have. And then Shoaib told us about all the impact on applications that we could have and all the different angles we could take there. So I'm going to be the big downer talk for the first session. I'm tired of all this research. I want to go home and play video games. So can we please figure out when we're done with this and everything is optimized? And more importantly, I want to talk about sort of limits here, right? So if we have a bazillion different ideas, which of those are important? How do we figure these sorts of things out? So I was preparing this talk, and I decided, well, let me go through the most boneheaded, least effort way to try to get some sort of timing on sparse matrix times vector computations. Probably you know what this is if you're in a sparse workshop, but if not, I mean, I have a matrix, which is sparse. I have a dense vector, and I just want to multiply it. This is the sort of thing that you would do for a lot of stencil code implementations, like Shoaib was talking about. For QP, a lot of the time, if it's an iterative algorithm, you have something like this sitting there. And I went ahead and set it to be a million by million matrix with about 8 million non-zeros. This sort of about linear growth with respect to n holds for a lot of spatial problems. They wouldn't be random, though. But OK, this is a perfectly reasonable thing. And I wanted to measure it on 2 systems. So I think maybe this is running Taco, but I don't know. And I'm not trying to beat up on Fred here. But these were 2 things I could get working really quickly in Python. And here are the timings that I got on my first run. And then I went ahead and ran this 2 more times. And you think, Gilbert, you did a terrible job benchmarking. Why are you telling us about performance measurement? No, well, this makes sense. If I have randomness in the matrix, there's no reason to believe that these times should be stable, even if I get a clear measurement for that particular matrix by running it many times. OK, so you won't harangue me about that. Now, here's my question. Is this performance good or bad? What do you think?
It's terrible. Show room for computation.
Well, yeah, so we don't have enough information, right? But I'm going to get to this. How good is SPMV in the last system that you built for research or used?
It should reach peak memory bandwidth.
Yes.
OK, yeah, that's a reasonable claim here. Well, so I don't know whether or not everyone always measures this, but for dense matrix multiplication, it's pretty standard to report your performance results as a % of peak throughput, right? So we have, this is a slide from the EXO paper that we did in 2022. And you can see that both we showed were competitive with other BLOS implementations, and that this is very close to peak. That's peak there, right? So this is a very important concept that we have some notion of peak computation that we're working with. So what should the peak of SPMV be? As we got a great answer, right? It should be bandwidth bound. And so how do I go about computing this? Well, I say, well, what's my hardware? This laptop I have right here is a first generation M1 Mac. It has about 68 gigabytes a second CPU bandwidth. I looked it up. I didn't run a micro benchmark. Maybe that's wrong. I'm taking it as gospel. OK. So then we have the question of how much compute or memory movement we need to do here. And we have approximately 8 million reads from the matrix, and another 1 million for the input vector. And then we should have 8 bytes each for these, because they're doubles. And if we put this all in the blender and press stir, that's how blenders work, right? Then we see that this computation should take at least 1.2 milliseconds. There should not be a way I can run this faster than 1.2 milliseconds. It doesn't matter how many cores I have or SIMD or anything else, because I'm bandwidth bound. Now, that might be slightly too optimistic, because I haven't factored in anything about the data format of this matrix. So, well, even before I mention that, let me go ahead and say, well, here's the numbers I got. So this seems like it's off by about a factor of 10, right? So that's probably not very good performance on my machine, as far as I know. Well, if I factor in that data structure information, I'm not going to go into this in detail, I should expect something like this overhead on a CSR matrix. And then I can say, well, OK, I achieved about 15% of peak by just running this. OK. Is 90% of peak bandwidth achievable for this problem? We have a bunch of people working on sparse computing. Can anyone confirm that they've gotten that working on their system?
So I got this for much larger graphs where, because you have a synchronization barrier at the end, so for those tiny problems, it's very hard to achieve. But if you scale up to gigabytes of a graph, then it's possible.
OK, like this million is tiny in that book?
Yes.
OK. Anyone else, have they measured this in their system? I see some nodding, but I see a lot of people not nodding. So that's something that's basically the gist of this talk, is how many people in the room are not nodding on this. OK. So if we want to do this for dense gem, right, here's sort of your recipe. You need to calculate your machine limits, then which is both bandwidth or compute, right? Depending on what your arithmetic intensity is, one or the other will obtain as your limit. Then you calculate how much resources your problem is going to need, including whether or not it's compute or bandwidth bound effectively now. You throw this all together and you derive a theoretical optimum. And then you go ahead and measure performance and you report your efficiency as a % of optimum, right? This is not complicated, definitely not rocket science. But there is a simple recipe. OK. So as I was suggesting a second ago, my big question here is, how efficient are current state-of-the-art SPMV implementations? Do they achieve 60%, 70%, 90%? Does anyone know?
Doesn't it depend on your matrix?
Depends on your matrix. OK, this is a somewhat reasonable question, I'd say. Now, I anticipated this, so thank you, Paul. I'm going to say no whataboutism allowed. What about what matrix we have, right? Here's a bunch of examples. Isn't the performance data dependent? Well, it depends what hardware you run on. Well, what format is the matrix presented in? OK, great. I like all your questions. But note, for this dense matrix problem, no one gave me any whataboutism. Well, what about if it's not a square matrix? We can play this game with any of these things. The interesting thing, and these are important questions, so don't let me disregard that. Pick an answer you like for this question. Pick a uniform random matrix, like an Erdős-Rényi random graph matrix generator. Pick some other sort of scheme for saying what my matrix is. And, well, what is this number, right? it happens to be that we know we ought to be able to do really, really good for dense matrix multiplication when we have square matrices. And this is the first thing you're going to check on an implementation. What's the first thing we check on an implementation of SPMV? OK, cool. Great. I think I've got everybody on board with this. So if we want to figure out how efficient current state-of-the-art SPMV implementations are, which I'm just taking that as one example. Obviously, we're interested in many more sparse computations. We need to know answers to these two questions. What's the speed of light for this computation? And what's the best speed we have right now? And we could call these roughly lower bounds and upper bounds. So I'll talk about the lower bounds first. OK. Lower bound sounds like a really fancy term here, right? This is like a thing that serious theory people say. Not, I just futz around with my computer and try and get these compilers working. They do these complexity theory proofs, right? I'm way too dense for that. Too dense, too dense. Well, OK, we know about doing this implicitly, is my claim, for dense matrices. And we have sort of a lower bound thing for dense gem. Well, or do we, right? If we go to the theory people, they say, well, there's this cool thing called Strasson's algorithm. It runs faster than n cubed. It turns out currently the best algorithm requires about this amount. Vanessa Williams is probably the leading person on this at MIT, right? Or no? Isn't she?
It was never implemented.
Sure. Whoa. Yeah, we're getting there. So there's also no evidence in theory that this can't be done in order n to the 2 plus omega time for very tiny omega, right? So this is a very important open theory question. But as we all know, that's all nonsense. No high-performance gem uses any of those things, the basic Strassen or Winograd. OK.
Strassen is used, totally used.
And also the small case, you might optimize like the number of
What system is it used in?
So there's a bunch of ML stuff that uses.
OK. So apparently, purportedly, Strassen is being used for ML stuff, and none of it is public anywhere. Is it?
So I've seen a Kacken paper that actually outperformed the peak dense compute that you could achieve on a hardware box with an efficient implementation.
For which numeric precision?
Single precision, I believe, but this was handcrafted. So it's not a library or anything. It was a handcrafted algorithm.
Theo, here. See, I'm going to run into trouble.
So
That's
for
fine.
complex matrix multiply, doing Strassen on your bottom cases actually can result in a non-trivial constant factor savings. If
OK.
it's a complex number.
Sure. OK.
For dense stuff, people who are designing hardware accelerators have built in like littler versions of Strassen into their design of like their vectrix. They're like tensor 4 type thing, and they're weird.
OK. So see, I might be getting in trouble, but let's just take this as sort of something that we've been working with as commonly accepted for the sake of this talk. And I think this talk will also make it clear why this sort of stuff is interesting as well. Cool. Thank you all for correcting me. OK. So I mean, if we take that sort of perspective, we might think, well, this complexity theory stuff is making this really complicated. Is it even useful? So I'd like to give sort of a way of grounding this notion of let's not use Strassens as a sort of theoretical perspective, a little bit more heft. So there's this less well-known result from Kerr in 1970 that if you want an arithmetic circuit for matrix multiplication that works in a particular semi-ring, and apologies if you don't know precisely what this means, this requires at least n cubed plus gates. And so this tells you something about, like, if I'm not going to use certain kinds of manipulations in my compiler or in whatever optimization technique I'm using, then this is, in fact, the best I can do. And there's an interesting implication here, which I was just saying, is that any algorithm which relativizes to arbitrary semirings is going to have this 2n to the cubed lower bound. And I got this, by the way, from this theoretician Stas Junka's work, which is quite interesting on these things. And so there's a way we can make progress here by making certain assumptions on our computational model, restricting it, in ways that align with our practice. And sometimes we're going to disagree with that practice and have ways of getting things faster, but this is still a useful way of approaching things. So we can presume that certain kinds of optimizations aren't useful. And then here is a very simple question I have along these lines, is I would like to have a program that computes precise lower bounds for arbitrary sparse linear algebra problems, assuming that subtraction isn't used. So we only allow these semi-ring optimizations. This would be pretty useful if you think about it as a performance engineer who's trying to tune things up. And this doesn't exist. I think there's a little bit of work here as well. I put it in terms of a program, but can we just collect the relevant theory results to justify this lower bound? I don't think it's even, we have to be incredibly creative with the theory results. And if we proceed down this road, right, I want to now suggest, once we've introduced this split here, like with the dense world and the discussion we just had, we can imagine two possible future worlds. One of these is, like dense matrix multiplication, sparse linear algebra basically doesn't benefit from Strassen-like algorithms. Modulate this with the previous comment. But the second world is that, unlike dense matrix multiplication, maybe there's something in this context where these sort of tricks become even more practical for sparse linear algebra. And if you can show that, I'm pretty sure a lot of people would be interested and you'd have a major breakthrough. So what's the pattern of thought here is, let's introduce a useful assumption to work with, right? And then we can always try to, that effectively everybody implicitly agrees on in all the work we've been doing, and then either focus on violating that assumption or focus on making things really good under that assumption, right? This will really clarify our thought and help us make progress. Okay, so some roadmap on this sort of stuff. Sort of the basic question, I'd say, for lower bounds here is this semi-ring question from the last couple slides. And there's some issues that remain there. Now, if we start factoring in other issues, this is going to be a little bit trickier. How do we account for data dependence of the computations, right? And databases has a lot of thoughts on this sort of thing. And I'll mention in a second, but I've been meeting with a group of people, including some people in the room here, for the last, I don't know what it is, probably a year and a half or so, talking about this sort of stuff. So we've been tossing around different ideas. It's quite interesting. And a third thing that I think is really important is somehow accounting for regularity. So here I've said SIMD, but another great example would be, as Schwab was talking about, those tensor operations work because of exploiting a high degree of regularity. So is there some way to account for that regularity constraint in the sort of lower bounds we compute so that we're not so optimistic that we never achieve those lower bounds? Okay. So that's all about lower bounds. Now we've got to put on the squeeze here on our problem and talk about upper bounds. Okay. And as with the other stuff, this is an ongoing effort with researchers at a bunch of different institutions. And I've mentioned a couple who have been very active in that group. And one of the things we're doing here that we're really trying to get traction on is having a sparsity-specific benchmark. And I want to talk about two challenges that come up in that process, which are different than what you might assume for your average dense benchmark. So one of these is data dependence of sparse computations. So here, not from a lower bound perspective, but just from a practical benchmarking, how do we account for this data dependence? So here's an idea. Let's generalize our input data to input data distributions instead. So for instance, at the beginning of this talk, I measured performance with respect to random matrices of density 1 over 8n. Great, that's a distribution. presumably we might want to think about our benchmarks as always taking inputs from a distribution. And this is really nice because it prevents overfitting implementations to the benchmark intentionally or unintentionally. And this is effectively standard practice in databases, by the way. Right? All the TPC benchmarks have data generators. Second idea here, impact of data structure in tensor format that we load. This is something we need to account for. It didn't come up so much in the discussion yet. So the problem here is that when we specify the sparse data structure, and so we have an idea for this, which is we should incorporate staging into our benchmark. So for SPMV, in stage 1, you would expect that you're only supplied with some of the inputs, say A in this case. So you haven't seen X, and now you could pick whatever format you want here, right? You can do as much computation as you want, and then you tell the benchmarking harness, I'm ready for stage 2. It supplies you with X. So now at this point, arbitrary storage optimizations may be applied to A before we measure stage 2, but the actual computation can't be performed until X is supplied. And so this provides a very nice constraint on the benchmarking framework to ensure that we're measuring what we care about and allow for flexibility on reformatting the data. And this actually reflects some existing ideas in the Sparse BLOS API. I should particularly give a shout out to Willow for helping coordinate with them. OK, so I will finish up here real quick. I want to point out that lower bounds and upper bounds are very interesting in that they are complementary. And I want to give these two processes of thinking feedback into each other. And an example here is, if we think about this very information theoretically, I really liked some of Saman's comments along these lines. So we were considering, well, what about if you have alternative data structures? Well, what's the minimal sparse data structure overhead, right? That's an interesting question. And the way we would try to bound this is by thinking about compression. What's the limit on compression? It's going to be some sort of entropy measurement. We could apply this, say, strictly to the sparsity pattern and not the data values themselves, or to the data values as well. And if we think about the implications of that on our benchmark, right, that really helps drive this idea of having distributions over inputs, right? Once we're talking about distributions there, we can talk about the entropy explicitly. And that might give us some other ideas on thinking about how we should bound this. And if you drive this process, I bet it gives some good ideas on future research things that are less negative in saying what we can't do and more about demonstrating things we can do. OK, so I won't talk about the current status too much. But if you're interested in these things, we'd be happy to have you join our group working on it. OK.
OK. Let's do one question for Gilbert.
So very nice point on data-dependent kind of lower and upper bounds. Wouldn't the same also apply to dense?
So if you do not, so if you consider compression of dense data as being possible, then yes, that's an interesting angle. If you make an assumption, if you assume that you can't do anything there, then the only degrees of freedom you have are what the size of the matrix is. And that is something which is usually accounted for in serious BLOS benchmarking. You can see plots with like variation over aspect ratio and the like.
OK, time for our first mini panel. So maybe Saman and Schwabe can come and join Gilbert.
You want to remove the light bulbs so we don't have
Oh, yeah.
errors.
Ugh. OK.
OK, so we're going to take questions and topics for the panel, but I'll get us started out. I think we can start by asking, what do you worry about? What do you think is the most important unsolved problem that maybe that nobody is working on in this area? Sparse databases, tensor algebra, or graphs, and so forth. Saman volunteered you.
So what is the thing that nobody is working on?
Yeah, what's the most important things that are not addressed? So you already mentioned some things.
Yeah, but I don't think that nobody is working on them. I think, some of the things I mentioned, I know, some of these abstractions, I know Willow's been working on, Olivia's been doing some of this stuff. So it's not that nobody's working on it, but I do worry a little bit about whether the world is actually sparse and whether we just need to find a mapping to denseness. But yeah, honestly, for me, the biggest worry is just we have great research, but we have very few ways to apply that research to practical problems. And that is, for me as somebody in an industrial research lab, it's kind of a nightmare, because there's so many times where I'm like, I know the answer to that, and we don't have a good way of doing that. And and in terms of like impact, what practicality can have, one of the biggest, speaking of attention, one of the biggest things for attention was this library called Flash Attention, which I'm sure many of you have heard of. But Flash Attention is really the tiling that Saman teaches in, the first parallel programming course. That gets you like a huge percentage of the performance gain, right? It's not all of it. It's like the memory bandwidth savings really comes from that, from tiling, not unnecessarily reloading data. So the gap between like what we know and what we can actually use, that is something that I find worrying.
Why do you think this?
Is it because R factor almost works but doesn't?
That's too much in the weeds for most people.
No, what I mean is this. You think about the tiling, the attention. You say, well, what was flash attention really? It was an exploitation of the properties of the exponential operator being factorized. And you would really like to do that per tile. R factor can't recognize that. R factor is a halide scheduling command. It can't recognize that sort of associativity. So you couldn't do that tiling in halide. But by God, it's really close, damn it.
I would maybe try and translate some of what Teo said. And this is something I would differ with Schwabe about. I was about to say is that it's not just the simple tiling, because you need to exploit algebraic properties of transcendental function to do this rewrite. This is like well outside of the realm of what most of these compilers are going to do. It's not a very complicated transformation mathematically, but it's essential. And so you had to have a more integrated view. Halide would say, oh, well, you're changing the algorithm, but you're changing the algorithm in a way that couples to the scheduling. And they're not independently separated in that case in the way that it's intended for them to be. That's a really interesting challenge, I think, in general. And may be much more prevalent in sparse stuff. And maybe to connect that to Saman's talk, the fact that for sparse computing, I mean, Halide sort of had this for image processing reasons, but sparse computations are much more likely to be bandwidth bound. And so the benefits of fusing multiple sparse computations together is much higher and much more important to handle.
So let me answer that question, take a little bit of different angle in here. For 50 plus years, the best data structures we get performance were dense arrays on integer grids. So what that means is the application community has calcified on that as a method to get their results. So right now, how do you get these application people to go to the first principles and say, okay, if we give you these different set of primitives that's as performant or close to as performant as dense, can you redo the problem? The problem is you have to probably go keep couple of generations of these people before, because for many people, the way they do things today are kind of it's a religion. It's a given. And I don't know enough of the math and the domains to try to undo that. Saying, okay, no, don't look at this. Why are you using this kind of a thing? I think part of that is we bring these new things. Are we too late to the game? If we bought it like 30 years ago, then when they first start using it, if they had those tools, they would have gone a different path. Have we, in many of these things, are we stuck in a local minima, and how do you get out of it?
Anyone want to ask a question or give a topic to the panel?
Just curious, what your take on sparsity exploitation in hardware is. So I guess starting at A100s, they added this clipping of 4 values to 2. You have FPGAs and other things, and they are lower and upper bounds are even much harder because you can arbitrarily replicate certain circuits. So what's your take on that?
Okay, let me take that question, because my entire life doing a compiler person, I always get this hardware people saying, I have this new whiz-bang thing, would you take advantage? I'm like, no, just give me a vector machine, I'll be happy. For the first time, I feel that there's a use of hardware. Because right now what happens is, we bring all this data to memory without understanding what data is, to throw out most of it. Okay, so earlier we understand what this data is, and do that filtering, I think we'll have a huge benefit in here, because most of the sparse computations is basically, that's why we can't take advantage of, because if you do sparse matrix multiply, we have to bring up the entire damn matrices in, whereas 99% of that will be not used. The part of that, the hard part is hardware, for the most part, until the data arrives way into the processor, data is opaque. You are just drinking data as just bits, bringing it there. You need to propagate the knowledge what data is, the representation downstream all the way to memory, even to the way the data stored in here. If we can do that, I think for sparsity, I think we'll get huge benefits in that.
So on the relevance of the lower bound and upper bound thinking, I think this question about, well, I'm going to change the hardware is great, because I gave the talk from the perspective of someone writing the low-level software. But if you talk with architects, figuring out things like roofline models and the limits of what you can do is extraordinarily important. So you could think about, I have some particular piece of hardware. Have I maxed out the software or not yet? Once I max out the software, what are those lower bounds which are limits? Great, you just identified the most important things to address in your new architecture. If you don't have some kind of conceptual map of these things, then you end up thrashing a ton, and it's hard to prioritize which parts of the architecture need addressing. So I think it's even more important and more complicated in a way to handle these things in hardware.
Awesome, thank you very much.
Ami had a question.
So, to Shoaib, actually, the point that you mentioned about the light moment actually for the sparse word. So, can you give somehow more details actually? Why what do you think would take actually to bring the sparse tensor compiler word actually to the robustness of what we have actually right now in the dense word? So, I want to give a hypothesis. I'm not sure whether you would agree or not. So I think that, for example, halide, it was based on the array abstraction. Perhaps could we say that, dense array abstraction, could we say that one of the reasons that we cannot see the robustness for the sparse word is because perhaps the dense array abstraction, is not the right level of abstraction for that word?
So it's interesting that I don't see halide as having arrays at all. So I can see why people think that, but in halide, really, like, what you have is an infinite space, multidimensional space, right? Indexed, as Saman points out, by integers, but it's not physically backed by an array, and that's part of what makes it possible to transform these computations kind of more robustly. But that I'm dodging your question by concentrating on that. I think for me, the thing that I pointed out here was that there was a driving set of applications and hardware, right? So you had on the Pixel phone a very early DSP on the Qualcomm chip. That was maybe Saman's ideal machine. It was a very large vector machine with the weirdest instruction set I've ever seen, right? Programming that was really difficult, but you could get really good performance with very little energy. So the hardware was sitting there to be exploited, right? People were hand coding imaging pipelines on that hardware. At the same time, you had an application area that really needed to use that hardware. The early Pixel phones, the Google Glass, the battery was so minuscule, the efficiency was so bad that you really, really needed, for this kind of application, you need kind of almost real-time performance, right? So I think like the convergence of both, of three things really was there. There was the hardware was waiting to be exploited, there was the application area, and there was a partially written and somewhat working compiler, right? And at the center of that, there was a person motivated to make it all work. So, in terms of sparse computation, like I really do think for the tensor compiler stuff, we can take maybe that the lowering algorithm is in fact correct. Let's take that as an assumption. Saman assures me that's the case and he has proof. That's one building block, right? But we still need kind of the other pieces. And I think application areas I pointed out are here. The hardware is also kind of here. I think, as you were pointing out, the place where we are right now is we have to maybe maximize our exploitation of the dense hardware as much as we can in order to prove to hardware manufacturers that, hey, you actually need to add this other piece. And I've heard willingness from manufacturers. Maybe they're just telling me that because they like Adobe or something, but I've heard this willingness. But I think we're not there yet. We're not hitting those bounds in a way that convinces hardware designers.
Yeah, I'll add to that. I think if you look at hardware today, they don't believe in what compilers can do, and so what they have done is build some very simple built-in, okay, I just need to get SPMV or SPMM, I'll build that, oh yeah, I can only do this 1-2 formats, that's all that matters. So I mean, there's good precedence for hardware people to not believe in compilers, but that said, we don't want Itanium example again coming in here, but if you don't give flexibility, either they are very smart and just build something that works on one application, or they do something stupid and build this architecture nobody can use, but there's flexibility hidden inside that compilers can do that. But I think they are getting smart and they are trying to build this like very domain specific one algorithm accelerators. And that's going to kind of really reduce the compiler's ability to kind of expand around. So I want to find a couple of dumb architects who will build something that has all this power hidden that can't take advantage of.
So one sort of along what the lines of Saman said, an interesting thing on flexibility versus optimizing for one problem is NVIDIA's continued success for machine learning workloads over, say, TPUs and the various sorts of custom accelerators. Those are really focused on the matrix multiplication, and it can be really difficult to incorporate other computations in around it, and that's been, sort of the death knell for them. So it's sort of weird. You have to account for two different things. I think this applies for anything with sparsity as well. You need to have the common case, which is going to be the bulk of the computation, run as fast as possible, and you need to also not completely have a performance cliff on everything else. And that's hard to do. And that's from the system perspective, not just the hardware, not just the compiler.
Okay, let's
add one thing to that. I will say, like, in this, the other piece of it is really the hardware-software interface. Like, for example, if there's anybody from ARM, I'm sorry I'm about to say this, but like SVE is insanely difficult to use and program for, right? To the extent that I think one of the biggest ARM manufacturers has SME and not SVE. But then you have this other problem, which is that how do you take your matrix outputs and use vector instructions on them? And there's streaming SVE. So there's all these like different places where, as Saman says, the hardware manufacturers don't trust compilers. But that leads to bad designs also, right? So I think that there is somewhere here where there a middle ground between having instructions that are very specific for this one specific operation, matrix multiply, versus having more flexibility as building blocks. I think the other thing with those, where hardware manufacturers are going, is that we're not allowed to program a lot of these functional units, right? They're completely hidden behind opaque APIs. So there's something to be overcome here in that aspect also that did not exist at the time Halide was there, mostly because DSPs were coming from a different domain and were being like repurposed for the specific image processing domain.
Okay, in the interest of time, let's do a closing statement, quick, saying if you want to end on a word.
Okay. I'm just going to repeat what I said from the talk is, can we max some things out and know that we max them out? I think that's a really important problem. I think it would drive a lot of progress. It makes it where you can't lie to yourself in your eval a little bit more, right? Which I think is a good thing and would push the community forward.
So it's interesting that we have come this far in programming languages, and you look at a company like NVIDIA, why it's success, because they have a horde of engineers who were able to take these codes and write it in very low level. In fact, Jensen gave this keynote address in a keynote or I think commencement speak, and they said his biggest contributions they have made to the world is CUDA, saying they made this language that makes it possible to take advantage. I'm like, damn, from programming languages point, that means we have failed. You have to go to all these, like the next level assembly language to get performance. So I think Sparse is this one of those interesting areas where it's not simple to get to that performance in there. I mean, we are still struggling in dense, but this is harder. So I think there's a good opportunity to make it in a way that you don't end up being like the next level CUDA, that you have to write all these things low level by hand going forward to get performance.
I just want our software to work. So that's what I'm going to leave us with.
Okay, thanks.
Thank you.
We're going to start up again in 20 minutes at 10:40.
Yeah, I can take this. Check, check, check.
This session is looking at also different approach to sparsity, especially looking at the like kind of database kind of view in there. Yes.
Thanks for the kind introduction. So my name is Matthias Böhm. This is all about exploiting sparsity and redundancy, which nicely links to some of the concepts on lossless compression, specifically in data-centric ML pipelines. So what is a data-centric ML pipeline? So probably all familiar with the classical ML pipelines of some iterative procedure to train a model, and then once we have this model, deploy this model into practice. Typically, those procedures, they are wrapped into library functions that you can utilize. However, a practical machine learning pipeline usually has additional pre-processing steps, so feature transformations, feature engineering in front of that, as well as outer loops for model and feature selection, hyperpyramidal tuning. Now, a data-centric ML pipeline wraps additional outer loops for reasoning about data integration and cleaning pipelines, data programming. So how can you synthetically generate additional labeled examples around those inner loops? And on the other side, we have additional primitives for actually model debugging. Is a model with 85% accuracy actually good or not? How can we find this out? Even before that, there is a feedback loop from model debugging, data validation, back to our procedures for data integration and data cleaning. And even before that, we have additional data engineering. Now, the premise of data-centric ML pipelines is that constructing a high-quality, good coverage data set is often more important than small algorithmic changes of the core model we are trying to train. Now, a key observation is that state-of-the-art data cleaning and integration strategies are themselves based on machine learning. So it makes total sense to build those primitives on top of a machine learning system. So I want to highlight two aspects what we build on top of machine learning systems. One is data cleaning pipelines, great work by Shafak. She graduated last week and built essentially a system for automatically enumerating pipelines of data cleaning primitives, such as data imputation by robust functional dependencies. There are something like missing value imputation by chained equations, where we repeatedly build for categorical numerical columns, classifiers, and regressors to fill in those different values. So given a target machine learning application and an input data set, we enumerate really data cleaning pipelines and tune their hyperparameters in order to find the top K cleaning pipelines that improve some metric on your user-provided target application. And all those different data cleaning primitives are expressed in linear algebra. Many of them are actually sparse. Another example is slice line for model debugging. So what we are given a trained model, we want to find the top k-worst slices, where a slice is defined as a conjunction of attributes such as degree, PhD, gender, female, where the model, instead of 85% on average, gives you only 55% because this slice, this conjunction of attributes, was underrepresented, and you should go ahead and find additional data points. So we introduced an intuitive scoring function that balances slice errors with slice sizes under alpha equals 0.5. It's actually perfectly balanced, so a slice with half the size of the original data set, twice the error, has exactly the same score. Now, we formulated this actually as an enumeration problem where we look at the entire lattice of all conjunctions of attributes, but we exploit monotonicity. So for degree PhD, gender, female, this slice can only be frequent if both their subsets are also frequent. And if that is not the case, we can prune any reachable nodes in this lattice. So we formulate all this as a fast linear algebra kind of program where, given the input data set, in this case 2 features, red and black, that are one hot encoded, an entire level in this lattice can be evaluated with a single ultra-sparse matrix multiply, and essentially while also applying pruning. Now, those are 2 examples of things we built on top of Apache systemd, which is the machine learning system we are working on for more than a decade now. Our system provides a DSL with R-like syntax and then provides an optimizing compiler that compiles hybrid runtime plans of local in-memory operations and distributed operations on Apache Spark. Initially, this was an proprietary product at IBM Research Almaden, where I spent first a postdoc and then research staff member time, 7 years in the US. We made it into the Apache Incubator project in 2015, became a top-level project 2017. And the beauty of open source, when I returned back to academia, is I could just fork that system and continue with our entire research group working toward building better and better infrastructure. So over the last couple of years, we even added additional backends, for example, for federated learning, where we can compile those linear algebra programs into federated execution plans. Now, what we learned over the last decade is the separation of concerns of working with abstract data types, matrices, and frames, and implementation agnostic operations allows us to really add additional backends without changing any of the machine learning algorithms and primitives on top of that, which is a huge investment people made in actually implementing those things. Now, in the remaining 10 minutes, I want to talk about 2 things: exploiting sparsity in this context and exploiting redundancy in terms of lossless compression. So you're all familiar that there's a variety of different sparse matrix formats. So in systemd, we are supporting, of course, dense row major linearized arrays. We support a modified CSR, which is more update friendly, that you can reallocate individual rows separately. We support CSR and double compressed CSR, as well as coordinate format. And systemd actually automatically, during runtime, measures the number of non-zeros and automatically switches between those representations. Now, in terms of sparsity exploitation, of course, we have all combinations for all hundreds of operators, essentially to do all combinations of sparse and dense inputs. In the literature, there has been then additional work on how we can exploit sparsity across entire chains of operators. So this is not from our group, this is from Duke University, but the first author was an intern at IBM in our group as well. So what they are doing, they essentially, from a sparse matrix, a sparse driver O here, compute a mask and feed this mask into an entire subtree of operators to only compute the cells that are actually relevant. What we are doing instead is we similarly rely on a sparse driver. So this example comes from matrix factorization. So you have an ultra-sparse ratings matrix, often 10 to the minus 8, 10 to the minus 7, X. And in this case, we're computing the squared loss. So in matrix factorization, we want to compute a low-rank approximation, U matrix multiply V, that roughly approximates X. Now for this squared loss, you see that we compute this outer product, which creates a dense intermediate, minus X, another dense intermediate, squared, another dense intermediate, and then this element-wise multiplication with W, which prunes away most of the computation. So what we do instead is actually we compile source code for the entire chains of operators in order to exploit sparsity, iterate over over the non-zeros in X or W and only compute dot products when needed. So this comes to our spoof code generation framework. So here we see our basic compilation chain, and as part of this compilation chain, we invoke our CodeGen compiler who identifies subtags of operators to fuse, then generate code, load this generated code as an operator back in, and treat them as a normal operator in the remaining compilation chain. Now later we added an actual cost-based optimizer that finds the exact cost optimal plan for those fusion plans. There are different templates we are supporting. So here's an example of a basic L2 regularized support vector machines, kind of two loops. The outer is for a conjugate gradient method. The inner is for line search, how far in the direction of this gradient we are getting. By default, we compute plans like this. So it starts at the bottom and computes the results on top. Our normal fused operators that we hand-coded often only cover 2 or 3 inputs. This is good. This already reduces the number of vector intermediates from 10 to 4. But what our code generation framework does, it takes the entire inner loop and compiles a single fused operator for it. And what you see here is we actually just compute for a single cell that we pipe through all those operators, all the different computations we do, and compute ultimately 2 aggregates that are used for the convergence check in the surrounding loop. So what worked extremely well for us is to have hand-coded skeletons that handle actually hash blocking, multi-threading, the entire access to different sparse representations, to compressed representations, and only generate really the custom code what happened per value or per data item. Similarly, we supported for row, piping entire rows through those fuse operators, which is important if you have in a DAG those row aggregations, for example. Again, it gives us a DAG. Ultimately, we compute those little intermediate representations and generate Java source code that pipes individual vectors, dense or sparse vectors through those computation graphs. In the last couple of years, we did a similar backend for GPUs as well, where you have additional steps of reordering rows in order to create more regular structures. Now, in terms of performance, we compare against TensorFlow, XLA, and Julia. So for this first example, the sum of 3 matrices element-wise multiplied together, you essentially see that our base is kind of the, without any fusion, generated is our generated operator, and fused is the handwritten fused operator. So you see that there's an order of magnitude actually benefit of doing this kind of fusion. Interestingly, for the sparse case, where you have 3 matrices and you want to exploit the sparsity of all 3 simultaneously, in this case, we get even better performance than fused operators, whereas Julia, even the fusion reduced performance, so made it slower, because if you're not careful about sparse access, every access in the CSR will create a binary search, right? So you need to keep stateful iterators and actually linearly scan those representations. For more complex matrix vector multiplies, where you can actually transform 2 scans of X into a single one, observing that an computed intermediate is joined against the exact same row where it was computed from, you get similar performance. And in this case, it might be partially unfair to TensorFlow because they focus primarily on hardware accelerators, and this is a CPU computation. But back to sparsity exploitation. So here we have another kind of cross-entropy loss in matrix factorization scenarios, and you see on the x-axis how we vary the sparsity. So sparsity of 1 means completely dense, and as we go by orders of magnitude, you see you get orders of magnitude better performance. Now, this is basic sparsity exploitation, but I want to make a case that redundancy exploitation, so lossy compression, is actually a generalization of sparsity exploitation. So let's look at a couple of data characteristics. So classical data sets like COF type, so forest cover, that you see you have often way more rows than columns. In those tabular data sets, you have varying sparsity per column, per feature that you have. Furthermore, you have often very small column cardinalities, so a number of distinct items compared to the overall number of rows that you have. And furthermore, you have a lot of column correlations. So on the right, you see, for example, a census data set where almost every column is correlated with every other column, which makes a case for co-coding columns. And you see actually that the compression ratio that we got increased by almost 3x by exploiting those column correlations. So our prior work on compressed linear algebra applied lightweight database compression techniques to individual columns of a matrix. We did co-coding and we selected heterogeneous encoding for schemes for the different columns. Then we encode an uncompressed matrix into those different things. So one scheme, for example, is DDC, which stands for dense dictionary coding. We encode the distinct items in the dictionary. Every value becomes the position in the dictionary, which then also identifies how many bits we actually need to represent it, which reduces memory bandwidth requirements and allows us to make things much faster because some of the operations can be directly computed on the dictionary instead of all the different rows. Because it's heavily data dependent, we actually do sample from the matrix and then make all those decisions what to co-code. To show you that we can perform linear algebra directly on this compressed representation, here's a simple matrix vector multiplication. So we have 5 columns, a vector of 5 elements. We essentially scan through the distinct items. So in this case, it's run length encoded. We pre-compute the multiplication with whatever value in the vector is, and then go over the compressed index structures and add this to the output. Now for co-coded columns, like in this case, column 1 and 3, we actually have a pre-aggregation on the dictionary. So you have multiple columns, you do multiple multiplications and additions, you pre-aggregate this and only add this pre-aggregate to the output, which reduces the number of floating point operations. Coming back to those lower bounds, even for dense and sparse, it's heavily data dependent. You can get arbitrarily fast with a constant matrix, for example. And you do that, and you scan through them, and ultimately you compute the same result. Now, because this scatter into the output can be really slow, we then did cache-conscious kind of segment-aligned scans where we can bound the working set on the output vector, and similarly it works for vector matrix multiplication. Just a quick set of experiments. So in terms of compression ratios, we are outperforming lightweight schemes like Snappy and LC4. We sometimes even outperform heavyweight schemes like gzip. But notably, so here we use the InfiniMNIS data generator, generated all the way up to 1 terabyte. What you see, if our matrices fit in memory, we are very close to uncompressed operations. However, if the data is larger than memory, so in every iteration we have to read partitions in, there by the compression ratio, we actually outperform uncompressed representations. And recent work of one of my PhD students actually now does this in a workload-aware manner. So we are actually, while compiling the plan, we see what kind of operations we perform. And instead of optimizing for compression ratios, we're optimizing for execution time. So if your data fits comfortably in memory, you should optimize to have faster operations. If your data does not fit in memory, you should optimize for compression ratios. Recent work, so that was the aware work. Our next is the beware work, where we push compression all the way into feature transformations like one-hot encoding, recoding, feature hashing, where there's a lot of potential. So instead of applying those structural transformations and then rediscovering redundancy, we go all the way to the sources and exploit this redundancy. We see a lot of redundancy in data-centric ML pipelines. I want to make a case for sparsity and redundancy exploitation. Both are super critical, but redundancy exploitation is even a generalization of sparsity exploitation, and both need optimizing compile and runtime infrastructure. We are really doing system-oriented research in my group. It's all about finding the appropriate abstractions and the right collaboration. So I hope to talk to many of you during this conference. Thank you very much.
Sparsity and compression stuff. Some of this stuff is new, so I'm really glad to find that. So questions? So if you are looking at compression, so have you looked at more structured data type compression, like a block structure and stuff like that?
So right now we're doing lossless compression. The mainstream, however, is lossy compression. And what we are currently doing is we separate things. So we actually, at the algorithm level, at DSL level, we are trying to learn both sampling, data augmentation, quantization schemes, but we include essentially those decisions into the loss function. One aspect of it is I want only kind of 3x3 blocks of cells to preserve this regularity for GPUs and other representations. representations. But we strongly believe that what we should do inside our system should focus on lossless strategies, because that is really trustworthy. You can guarantee the exact same results. And the other things, however, can be pushed at algorithm level, and you get the benefits
because
of both worlds.
a lot of machine learning, you can actually play with the algorithm level too, and get more compression in there.
Excellent question. Yeah.
Any other questions?
So on the data-dependent optimization aspect, you mentioned that you have basically a cost-based optimizer. And actually, one of the interesting problems in cost-based optimizers is basically to propagate the sparsity information.
So excellent question. So it's about sparsity estimation. So we had a Sigma 2019 paper where we introduced the MNC sketch. And what we did there is compare. So there are a couple of really good estimators, like the layered graph, super high accuracy by Edith Cohen. A super underappreciated paper from the end of 90s, has only 50 citations or so, is super accurate, but relatively expensive to construct. It's a graph that has an edge for every non-zero and a node for every row and column in a long chain of matrix multiplies. So we added a more cost-effective sketch, and we integrated it into a dynamic programming optimizer for finding the optimal parentization for matrix multiplication chains. This was experimental work. It worked quite well, but we did not fully integrate it by default in our system, because sometimes the overhead of creating those sketches, you don't know if it will be amortized or not, if you ultimately end up with completely dense representations, for example. At SIGMOD 2 weeks ago at Santiago, there was actually a follow-up work by another group that followed up on our MNC estimator and got even better results. Casting this entire, you have a chain of matrix multiplies. We should not just think about compilation and subsequently executing this plan, it's just a joint thing. And ultimately, we should measure the execution time of both optimizing and executing the sparse chain of matrix multiplies, and there's a lot of potential in that. Yeah. Excellent.
Okay.
Thank you very much.
Thank you. Okay. Why don't you plug it in first? Here we go. To switch.
Okay, does it work? I can also use.
Okay. Take it away. Go for it.
Okay. Hello, everyone. My name is Haozhe Zhang. I'm a postdoc at University of Zurich. And today I'm going to give a short introduction to the recent advances in incremental view maintenance. So let's first define the problem incremental view maintenance, or IVM for short, trying to solve. So given a database, a dynamic database, and a query, we want to maintain the query output under updates. So the updates can be tuple insert or delete. Why we want to solve such a problem? In typical data processing scenario, we normally have some small change to the query input, and they will lead to some small change in the query output. Right? It doesn't necessarily to be the fully materialized output, but it can be the representation of the output. So the naive approach to reflect the change is to recompute the query output from scratch. But this can be inefficient because the input data can be very large, and if you compute from scratch, it can be expensive. So the more preferred way to do it is to use IVM, which is to propagate the change from the input to the output. That is, we only compute the changes that are triggered by the update. Because the change is normally much smaller than the original data, so this can be much faster. And theoretical results shows IVM can give lower complexity than recomputation, and there are also runtime improvement reported for practical workloads. So let's look at a warm-up example on the maintaining of a triangle count on this IVM problem. So assume we have a database with these three relations, R, S, and T. They have this schema A, B, B, C, and C, A. And we want to know how many triangles are in this database. So we use the semantic. We consider these relations as functions mapping from tuples to count. In fact, we can also map them to more complicated things, anything in a ring, but here we use count. For example, in R, the first tuple A1, B1, it has the count 2. It means this tuple A1, B1 appears twice in relation R. So we want to understand how many triangles are in this database. So for example, here, these three blue tuples A1, B1, B1, C1, C1, A1, they form a triangle, which is in the result A1, B1, C1. And the number of triangles they contribute is 4, which is because there are 2 A1, B1 in R and 2 B1, C1 in S and 1 C1, A1 in T. So in total, there are 4 triangles contributed by these 3 tuples. Similarly, we can compute the triangles contributed by the other tuples. And in the end, we sum these counts together to get 19. There are in total 19 triangles in this database. And this is formulated as the formula there. We do the product of the 3 relations and sum over their variables. So this is about computing the triangle count in the database. So what about updates? Assume we have an update to relation R, either an insert and a delete. We represent it as a delta R there. We use positive or negative values to represent insert or delete. Here we have update to R with A to B1 with -2 count. It means we remove 2 A to B1 tuples from relation R. So that means we need to update that tuple in the original data, and we update its count from 3 to 1. So the naive approach is then to recompute the whole thing here and to get the updated result. But actually, we can just compute the change change triggered by this update. So we need to update. We see this right tuple A to B1 is joined with these 2 blue tuples in S and T. So we can update the corresponding tuple in R times S times T, update its count from 9 to 3, and consequently update the final current result from 19 to 13. So this is the idea of IVM. We try to minimize the time to reflect update. So in this talk, I will mainly focus on the fine-grained complexity and optimality of IVM for conjunctive queries. Theoretical results are made in the past decades. They aim to mirror the development of worst-case optimal join algorithms, which were developed for static databases. And these results guide the development of some new IVM engines like dbToaster, Dynamic Inkaki, FIVM, cron, and the IVM system in relational AI. And they yield lower complexity, and also experiment results show they have faster runtime than classical IVM. And each of these reported advancements is a small increment, but together they pave a way to a deeper understanding of IVM. So let's take a closer look at the IVM problem to understand the different complexities we are interested in. So assume we are given a query and a database. We have this pre-processing step, which is we use this time to compute some data structure that represents the output. This data structure does not have to be exactly the fully materialized result, but it should allow us to enumerate the result efficiently. Whenever the user gives an access request to the result, we should be able to enumerate the result, every tuple in the result one by one efficiently. And the time for enumerate every record in the answer is called the enumeration delay. Then when they are updated to the input database, we want to update also the data structure to reflect the change. And the time to do this is called the update time. So we are interested in this 3 time, pre-processing time, update time, and enumeration delay, especially the update time and enumeration delay. And we want to know which IVM workloads admit the best possible maintenance. Best possible maintenance here means constant update time and constant enumeration delay, and how we can achieve them. So this question is already answered in the paper in POS 2017. So they defined the class of query named Q-hierarchical queries, and they proved that this is exactly the queries that admit the constant update time and constant enumeration delay. They show that every query that is not hierarchical cannot achieve such complexities based on the OME conjecture. Now the question is how we can achieve the complexities for Q-hierarchical queries. And the short word is, the keyword is factorization. So this Q-hierarchical queries, they have this nice property that use the factorized version of it. And such factorization admit constant delay enumeration. So we can enumerate the result as if it is already materialized. And at the same time, this factorization is more succinct, so we can update it more efficiently. There are several systems use this idea. One example is the factorized IVM, FIVM. It factorized the query output as a tree of materialized views. So the result of the query is distributed in this tree of views. And some other systems, they also use this variance of view trees. Let's see an example how this works. Let's consider this Q-hierarchical query, which is the join of RAB, SACD, and TACE. And we have the 3 variables ABC. That is, we want to enumerate the ABC tuples in the query result. So for Q-hierarchical queries, we can construct such a variable order. A variable order is a tree of variables, and it serves as a guidance how we process the query. It must satisfy some property, but we know for Q-hierarchical queries, we can always find the variable order such that every relation is exactly a root to leaf path. Right here, RAB is a root to leaf path, and ACD and ACE. Having such a structure, so variables on different branches, they are conditionally independent on their ancestors. For example, here B and C, they are conditionally independent on A, and D and E are conditionally independent on A and C. So variables on different branches, they are processed independently, which means which can lead to lower complexities. So Q-hierarchical has such a property, and factorization tries to fully exploit this. Here is how we can do it. We can map this variable order to a view tree, a tree of views. So each view is constructed from its children, and it's either by projecting away one variable, or it is the join of its children. For example, here, this V prime E is constructed by projecting this E away from T, and VC is constructing by joining the 2 child views, VD prime and VE prime. The constructing of this view tree can be done in a linear time, in a time linear to the size of the database. So for those views that require joining the children, which are the VA and VC, which are the 2 views here, they can be constructed by just joining them, which require linear time. We just iterate over one view and do the join in the other view. And the other views are just by aggregating away some variables, so we can construct them in linear time by iterating over the views. So overall, all these views can be constructed in linear time. Then it's about update. Assume we have an update to a single tuple update to relation R with the given value A and B, their delta R there. We compute what are triggered by the change triggered by this delta R all the way along to the root. So here, this VB, we compute the delta version of it, V prime B. It is by projecting away B, this should be B, from the delta R. Because it's a single tuple update, it can be written as just do a lookup in the view. So this is a constant update. Then we can construct the delta for the root view VA, and delta VA can be constructed by joining this delta VB prime with the V prime C on the other side. So we propagate this update all the way up to the root. This is for update to relation R. If we have update to relation S, we can propagate also from here all the way up to the root. So for the view V prime D, we compute the delta of it by just doing a lookup. And then for this, we need to do a lookup in the V prime E, and similarly all the way to the root. For each updated view, our relation, we compute the delta of it and apply it to the original to get the updated view. So in the end, we have an updated view tree that corresponds to the updated query result. For q-radical queries, every update requires only a constant number of lookups or projections in the view tree. So that's how we achieve a constant update time for this view tree. And then for enumeration delay, another property of q-radical is we need the free variables, which are the variables that are in the results. They should be connected at the root. So for this one, we have the free variables A, B, C. They are connected at the root, which means in the corresponding view tree, these variables, they are stored in the views that are connected at the root. So by constructing this view tree, remember for each view, it's computed by the child views below. So it is calibrated top-down by construction. That means every value in the root, it must appear in the views below. For example, here, so to enumerate the ABC tuples, we can start from the root view. From it, we get the first A value, let's say A1, and then we get the paired B value in the result. From relation R there, we get the B2, B3, those values for this given A1. And then we can get the C values paired with this A1. And we just concatenate them together to get the final result of ABC values. Once A1 is, once this BC are exhausted, we move to the next A value A2, and similarly, we can construct the ABC tuples. So this is how we achieve the constant enumeration delay. This is guaranteed by the property of hierarchical queries, q-hierarchical queries, where the free variable values are connected at the top of the view tree. So, so far we talked about the q-hierarchical queries, but it might sound not very useful because it's only for this class of queries. But actually, many non-q-hierarchical queries, they also behave like q-hierarchical queries when we have more information about the data or the update sequences. So for the definition of Q-hierarchical query, only talk about the structure of the query, the schema of the database. But if we know also about the data or how we do the update, we know more. So for example, here, if we know more about the query structure, like this cascading queue hierarchical means if we have multiple queries, we want to maintain them simultaneously, we can reuse the result of one query to help the maintenance of other queries. And together, actually maintaining multiple queries becomes easier than maintaining them one by one. And the maintenance of all these queries, they behave like they are a single queue hierarchical query. And for data structure, if we know some like functional dependencies in the data, then there are more queries can be considered as Q-hierarchical query. Or if we know some relations are static, we can actually, again, consider them as Q-hierarchical. And if we know integrity constraints about the data, more queries are hierarchical. And for the update structure, so for update, insert only, we have shown that insert only is actually easier than the mix of insert and delete. So if we know the update sequence is just insert only, more queries are Q-hierarchical. And for the enclosedness of update sequence, if we know in the advance the pattern of the update, like windowed stream or our first in, first out certain patterns of insert, certain patterns of update, we know we can characterize more queries to behave like Q-hierarchical queries. So that's about the things we are doing and the result we achieved so far. So Q-hierarchical is important because for IVM problems, constant update time and constant immersion delay is important. And this gives a big picture of what we achieved so far. Okay, that's all.
Thank you. Questions?
Yes.
So you keep mentioning this term Q hierarchical. Can you give us some intuition?
Yeah.
What are they?
So Q-hierarchical is defined by both. First, it is a hierarchical query. Hierarchical query means we can, given a query, we can construct a variable order such that every relation, it is exactly a root to leaf path in the variable order. And property Q there means the free variables needs to be connected at the root. So that's an example of it.
Does sparsity come into play in the data structure in here?
Yeah, this factorization is actually trying to exploit the sparsity of the data or the independence of the data. Because Q-hierarchical has this property makes sure the data has this independency, and factorization tries to exploit it. That's the sparsity here.
Okay, great. Thank you. How many is next?
Hello, everybody. This is Amir from the University of Edinburgh. And so my talk is about hybrid relation tensor processing. And this is joint work with these many collaborators. So on the left side of me, right side of the view, these are my students. And on the left side are my amazing collaborators, who are actually, most of them are from the database domain, if you don't know them. So actually, one of them is from the PL domain, and he has a paper in PLDI, which has nothing to do with this presentation. So let's motivate the problem. So we are surrounded by a lot of data, and we want to extract insights from them. And who are the people who are extracting insights from data? They are data scientists. And so the main conference here is PLDI. Let's see what are the main programming languages that data scientists use for that. It's really sad. The first language is Python. But the good news is that the second language is SQL. And this is where basically the database people come into the play. And why is this the case? So let's take a look at an end-to-end pipeline for data science. So we have a bunch of phases. We start from some sort of structured data in the form of a graph or relations, or also sparse tensors, perhaps. We do a bunch of data wrangling in SQL or in Python, like lightweight SQL, which is basically Panda data frame. And then we construct tabular data. Then we do more preparation. We construct then, at that point of time, tensor data. And then we pass it to the machine learning frameworks, which are basically digesting tensor data. And this tensor data, of course, could have also a nice structure. But the sad thing is that the very initial data had some nice structure, which was heavily crafted by some domain experts. All the undergrad courses on databases you see about first normal form, second normal form, or this kind of normal forms, all of them are going to be thrown away throughout the pipeline. Why? Because there are these different components that are developed in isolation. And if you take a look at, have a bird's eye view of that, we see that we have database workloads on one hand, and we have tensor or linear algebra workloads on the other hand. And each of the components in the data science pipeline is actually dealing with one of these pipelines. And the sad state is that we have two different communities. So the database world have been very successful in developing relational algebra and also nested relational algebra and relational database systems and the lightweight version of that. And the linear algebra board, also the high-performance community, have been very successful in developing tensor algebra compilers. But these two communities don't talk to each other that much. So let me motivate why they should talk to each other more. So, yes?
Why isn't databases more?
Yeah, it's just for the color correspondence. I'm using blue for databases and red for yeah, I could use it the other way around. So relational databases, from a very high-level point of view, they are basically compilers. You give them SQL queries. There's a parser. It constructs an intermediate representation in the form of relational algebra. Then there is a relational algebra engine, which digests the relational data and produces the answer. Of course, this is oversimplified version of that. Databases are much, much cooler than that. But what is this relational algebra? As the name suggests, it's actually an algebra for relations. And it has a bunch of nice algebraic operations, selections, projections, joins, which basically have a nice set of axioms, rewrite rules that we can exploit. So for example, we can push down selections, we can commute selections, we can use the associativity of joins, and all these kind of things. So let's take a look at machine learning frameworks or linear algebra frameworks. Again, the same thing. The user writes the program in terms of Python or one of these languages. But behind the scenes, what happens is that there is a library that behind the scenes, it's basically a bunch of linear algebra operations. And there is a linear algebra engine that digests the tensor input and produces the answer for us. And again, for the linear algebra board, we have a bunch of cool optimizations again. So the question that I'm answering in the first part is that, can we have a unified environment which basically combines the benefits of these two words? Let me give you one other motivating optimization. Let's consider this cryptic query, which basically what it does is that it joins three relations and it computes a group by aggregate over them. So there is a very nice optimization in databases that it says that rather than first joining these three relations and then computing the aggregate over that, which results in actually creating a very large intermediate relation, you can compute partial aggregates by just doing the join between two relations and computing the group by aggregate over that, and then join the result of that partial aggregate with the other relation. And let's take a look at another thing that we do in the linear algebra domain. Whenever we are multiplying three matrices, so what we don't do is that we write a very kind of long nested loop to basically compute the multiplication of that. We do matrix chain ordering. Yeah? We compute the multiplication of two of the matrices first, then we compute the multiplication of that result matrix with the other one. And basically here you see the correspondence between two of the optimizations that basically the database word, the Earth word, is doing and the Mars word. And here I'm presenting our intermediate language called semi-ring dictionary query language that brings the peace to these two words. Let me decipher each of these terms. So Gilbert gave a hint on semi-rings. Let me give you a definition of the semi-ring. It's basically a set R with two particular elements of that set, 0 and 1, and two binary operators, plus and multiplication, addition and multiplication, with this very intuitive set of algebraic axioms. Yeah? So that's it. That's what the semi-ring is about. But the very cool thing, the very two sets of rules that are very cool, which are basically one rule, is basically the last two rules, which are basically connecting the multiplication operator and the addition operator. And that's the distributivity law or the factorization. So what are the examples of a semi-ring? The most obvious example is real numbers and natural numbers with 0 and 1. A slightly more interesting example is the Boolean semi-ring, which we have false and true instead of 0 and 1, and we have disjunction and conjunction instead of addition and multiplication. Another cooler one that also Gilbert hinted at it is basically the so-called tropical semi-ring, which instead of addition, we have minimum or maximum, and instead of multiplication, we have addition. And the zero element is actually plus infinity. And this is actually used basically to solve some graph problems using linear algebra. So now we have seen what is semi-ring. What is a semi-ring dictionary? So there is a notion of ring here. So it's basically one collection to rule them all. So, and what is that collection? It's basically a dictionary from keys to values that form a ring, but not a ring, a semi-ring here. Because a ring basically has a subtraction operator, and we don't handle it here. So, and with that, we can basically handle the relational word as, well, what happened? As well as the linear algebra word. Let me show you how we can represent them. So, I don't know what's happening here. So, as it was hinted in the previous talk, whenever we have a relation, so in practical databases, as opposed to what you have studied in your undergrad courses, practical databases have a bag semantic, meaning that a relation could have several elements of the same row. And basically, this means that we need to have a dictionary from the tuples to the number of occurrences of that tuple. And this is how we basically represent, as a dictionary, basically, a relation with duplicates. How about the linear algebra board? Basically, we can represent a matrix, a sparse matrix, as a dictionary from the index to the value. And here, we don't need to explicitly represent the indices which are associated with a 0 value in the semi-ring. So this is how we can represent this matrix as a semi-ring. And so we have seen semi-ring, we have seen semi-ring dictionary. What is the query language part? Basically, we have some constructs in the language around this notion of dictionary to do querying over it. What is the main construct? It's basically a summation. What is the summation? It's a loop. you can see the translation of the summation and how it corresponds to a for loop in C++. And of course, in the body of the loop, if we have a scalar thing, it's basically just doing the plus equals. And whenever there is a dictionary inside it, it basically is going to do a pointwise addition. And now with this powerful query language, we can express a bunch of queries and translate it in terms of this language. We can represent aggregations and also group by aggregations. And we have a translation for the entire relational algebra operators. And similarly, for the linear algebra word, we have a translation for all the operators that you would have over the vectors and also matrices. You don't need to read that. So from the expressiveness point of view, we have seen the power. I don't know, it's not processing. But on the efficiency side also, we have a bunch of optimizations. Sorry, the animation is broken. So here I want to show you 2 examples of the optimizations that we have. Let's start with this very naive program, which is basically doing the join between 2 relations. It's basically doing equality join by doing a nested loop. So one optimization that we can do here is the reverse of inlining, which is known as outlining. And we can basically cache the result in the form of a dictionary. And then one interesting thing that we can observe here is that that snippet of the code is going to be invariant to the outer loop. So now I can apply loop invariant code motion. And you know what happened now? We have synthesized the hash join operator in databases from the nested loop join. And not only that, there are a bunch of optimizations that has been happening in databases for a long time. And there was also in the other word, in the high performance community for the linear algebra, there was a corresponding thing. And here you can see a bunch of corresponding optimizations that we can actually apply on this intermediate language. And not only the optimizations, there are a bunch of good data layouts that has been done in the databases. So for example, there is column stores and row stores. And also, as the previous talk was mentioning, the factorized relations. And they basically correspond to the dense tensor representations as well as the more kind of nicer compressed representations such as CSR and CSC. And so what we can do is that now with this intermediate language, we can translate basically the relational algebra part of our code, the linear algebra part of our code, or we can expose this intermediate language also as an API. And then we can do cross-domain optimization across them. And here, I'm just showing some benchmarks to show you that we are good. But the point of this benchmark is not that we are better than the other systems. It's that we built one system that is competitive with specialized systems for the database workload, for the sparse tensor workload, and also for hybrid workloads, meaning that we are doing some linear algebra computation over relational data. And now I'm going to the other way around, and I'm going to study whether can we do also, how well can we do sparse tensor algebra with this intermediate representation. And after all, I'm partially a database person, and everybody should know this code, that everything has been done in databases before. So naturally, we can represent sparse matrices as a relation. It's obvious. We have this sparse matrix. We can represent it with a relation with 3 columns, row index, column index, and the value. And whenever we have this tensor contraction problem, which is in this case matrix multiplication, it's nothing but a join and followed by an aggregation. So then the databases should do a perfect job. But are they competitive? The sad state is no. So here we are using a particular famous kernel, the BATAX kernel. We are comparing SciPy Taco with a state-of-the-art in-memory database system called DuckDB. And we are seeing that they are not competitive. Lower is better here. So why is it the case? It's because they do not support the optimized storage formats that the sparse tensor frameworks are using. Sorry for stealing your figure, Fred. So basically, this is from the Taco, the successor of Taco paper, format abstraction. So here you can see a bunch of nice tensor representations. I'm focusing just on COO. So for the database people, COO is nothing but a column store. CSR is kind of compressing one layer, one of the columns. And at least the in-memory databases that are publicly available, they do not do that. And what we do is that we use our intermediate language to express both the storage format and the tensor computation. And then we do some magic with equality saturation to basically optimize it away. So how do we do that? So we basically express the tensor computation as a program in SQL. Then for the storage computation, what we do is that we express the storage specification as a program that converts from the compressed representation back to the uncompressed representation. That's how we specify the storage specification in the SQL program. And now we just compose them. Problem solved. Yes? No. It's inefficient. That defeats the whole purpose of the compression. So we are uncompressing the data, and now we are doing the computation over the uncompressed data. What should we do? We should optimize it. How do we do that? We have 44 rewrite rules. One of the important ones is basically loop fusion, which gets rid of the unnecessary intermediate allocations. And the other important one is basically the one that uses the distributivity law to basically hoist modification outside the summation. And then we pass it to a magic framework, the equality saturation, the EQ framework, and which uses basically builds something like what the cost-based optimizer of database systems are doing, but it has a kind of compressed representation of the search space. And then it does the magic for us. Modulo some caveats. But what happens after that? Now we are good to go. We are also going to be, for this particular kernel, we are going to be faster than the existing systems. Why? Because, for example, Taco has this notion of schedules that it uses basically to leverage workspaces and these kind of things. But now, with this equality saturation magic, we can automatically do that on our intermediate representation. So it's a combination of optimizations and compressed storage. And as a follow-up work on that, in this CGO, we have also worked on the differentiation component also. Now we have a kind of nice algebraic language which we can do automatic differentiation and gradient computation over that. So, but what we do is that here we have a spin on it. We use the kind of database idea of separation of the concerns of having a logical representation and a physical representation. So we deal with the AD computation on the logical layer, and then we basically do the fusion with the storage specification at the physical layer. And then we can basically, that's, as far as I know, the first framework that does sparse differentiation. So to conclude, data science is hybrid. So it needs both relational and tensor workloads. And we need to rethink how we are developing data science pipelines. And the approach that I'm advocating for is combine techniques from databases and programming languages / compilers. And so in my lab, we have worked a lot on the language design aspect. So what I've shown you here was the STQL intermediate language. And so very recently, so 2 weeks ago in Santiago, we have presented our work on also adding the support for recursive computing, fixed point recursions also on top of this intermediate language. And the other thing that we did was that we have used a variant of this intermediate language to automatically lift Python data frame code into SQL. So basically, rather than running Python programs on Python engines, or rather than compiling it down to C++, we basically do a source-to-source translation from Python code to SQL, and then we use the magic that database systems have behind the scenes. And we have also another work on the structured tensor algebra part, which takes a different design from the language that we have seen here. It's basically taking mostly the design ideas from the data log language in databases. And also we have work on the probabilistic programming using a variant of this language. And so in all this work, we are basically leveraging the structure inside the data. And in this way, by redesigning the stack for the data science, we can basically optimize across the domain, not only individually in one domain. And that's it. Thank you.
Fascinating talk. Questions?
Hey, so very, very interesting. So the formulations you have with the loops are very sort of based on rewrites,
Yes.
very interesting rewrites to get to different things. But is that, how robust is that compared to, say, generating the right code in the first place from the higher level things? Do you have some thoughts on that? Because there's sort of two approaches, and you can do things during lowering and generate the right code, or you can generate simple code and then rewrite that.
Yeah.
What's your thoughts?
Yeah. Yeah, so the approach that we are taking here is that, so our intermittent algorithm can have multiple layers, so by itself, so you can express something in a very concise, in the same language, that then you can expand it actually to a lower level thing. And I think my approach to robustness is basically to do all the magic on the, by using basically provably correct rewrite rules, correct by construction rewrite rules. And then doing the lowering as an obvious one-to-one mapping rather than changing the level of abstraction too much during the lowering. Yeah, so I'm not sure whether I...
No, thanks.
Thank you.
Okay, thank you. Olivia, take on.
Hi everyone. So my name is Olivia. I'm a 5th year PhD student advised by Fred and Kunle Olakoten, and today I will be talking about mapping sparse applications to accelerated computing systems. Normally I say I'd be happy to take questions during the talk, so it's a little more interactive, but you know, we have a panel session after, so maybe hold questions till the end. So to put this work in context, there has been a whole history of programming systems for dense domain-specific accelerators. They're ubiquitous. And we often use them without even knowing. But there exists really no such system or no such ecosystem for sparse applications and for sparse accelerators. And that's exactly what I'll be talking about today. So I originally had a motivating slide on like why sparse applications are important, but I don't think we need that in this room for this audience. So sparse programming systems research and development is lagging behind that of its dense counterpart because there are some more challenges that we have to face. And this is also stolen from Fred's slides, but there's a bunch of complexity in what we want to compute, including through the algorithm or expression, this specifically for sparse tensor algebra. But there's further complexity in the scheduling, so there are scheduling optimizations that you can do in dense land, but actually in sparse land there are more sparsity-specific scheduling optimizations you can do. Now you can tile by different factors instead of just that impact performance more, as an example. And then there's also the compression formats that you care about. So there are data structures that originally you don't have to handle, and also the dependence on data for your performance. And for a general programming system, you actually want to handle the Cartesian combination of all of this. And it's impossible to do by hand. So this really means that things should be managed automatically through a compiler if we want to handle the whole entire domain and do it well. And so prior work compilers have compiled from high-level languages down to generated sparse codes. But these sparse programming systems are for CPU-only codes. So here I show CPU code for sample dense matrix multiplication, or SDDMM. And you don't really need to understand this code. This is generated by Taco. All you need to know is that it's really complex, and I certainly wouldn't want to write that by hand, right? So the compiler is already handling it for you. And so there's all this prior work that we can leverage, but why do we want to even support these sparse accelerators? Well, they're actually promising for accelerating sparse computation, and we've seen this popularity start to happen both in academia and also in industry, for example, through sparse cores on the TPU, in the GPUs, and also the Meta MTIA, or the training and inference engine that also supports sparsity. And so not just through popularity am I going to motivate you, but actually benchmarks show that accelerators can improve performance as well. Here I'm showing sparse matrix addition, and I show the performance for Taco. And also we show like, okay, we have some high performance libraries that can also express this kernel, and because the data changes, you know, no system dominates. So it really motivates the need that you handle both. But on the other hand, we have some sparse accelerator from academia and from prior work, and it shows that actually maybe the accelerator can outperform a CPU by over 2 orders of magnitude, right? Because you have parallelism and pipelining, and then you also have things like lower overheads because these accelerators strip away all of the things in the CPU that you don't need for these sparse computations. And so the accelerators, though, I already said, like, sparsity further complicates these programming systems. Well, accelerators will further complicate it even more because you now need to consider how your CPU host, or in any distributed system, how you offload data and computation onto your domain-specific accelerator. And on top of that, you actually have to program and configure the accelerator itself, if it's programmable, and even if it's a fixed function ASIC, oftentimes they come with many configuration files. And if it's not programmable, you need to figure out what hardware constraints, like what hardware constraints are there in that accelerator, and you need to be able to match those constraints. And so how do we program these accelerated computing systems? And I really just mean a computing system accelerated with an accelerator. And this is through the compilation systems that address both programmability and the mapping problem from different levels of the abstraction. And when I say different levels of the abstraction, I really mean different levels of how we think about the computing system abstraction. So the first level is through thinking about our accelerator as a black box. And so I will talk a little bit about Mosaic, which is a compiler that we presented last year at PLDI, and it really allows you to offload data onto your accelerator, treating it like a black box. And then I'm going to talk about the Sparse Abstract Machine, or SAM, which configures and programs the accelerator itself. And then I will talk about follow-on work stemming from SAM, where we actually built a new sparse accelerator. And so first, let's talk about Mosaic, offloading computation onto accelerators, treating it like a black box. So again, starting with our SDDMM CPU code example, it's already so complicated. But the problem is that there may be an accelerator that can do an expression that you'd like to accelerate. So for SDDMM, maybe we have some accelerator that can do sparse, dense, matrix element-wise multiplication. So that's a sub-expression of the total expression you want to compute. And because it's faster, you know that you can accelerate your full expression. Okay, so what does Mosaic do exactly? Well, first we need to identify the code or the sub-expression that the accelerator can compute and isolate that sub-expression from the code. Then we need to actually slot in the accelerated API call, right? And then also offload that computation onto the accelerator itself. So that's many things to do that maybe a user would not want to do, especially if they have many accelerators and they want to do this for many types of expressions. So Mosaic does exactly that. Mosaic allows users to programmatically describe the capabilities of their accelerator so it can automatically find ways to utilize that accelerator. And how exactly does it do this? Well, Mosaic programmatically describes accelerators using its external function interface, which is a plug-in system where users can plug in different accelerators or external functions. And then using that, users, so the external function interface describes an accelerator in 2 ways. It first describes what does that accelerator compute, and then it also describes how exactly to target that accelerator. So how do you call that accelerator using its API? And then users can manually use these accelerators by manually writing schedules. So maybe you want full control and you're a performance engineer, you know exactly what to do, right? I can schedule this, I know that I want to target this sub-expression. And then Mosaic will validate that the binding is correct using a solver-based approach. But if the user isn't really familiar with the accelerator or the function that they want to plug in, Mosaic also has an automatic search mechanism, which will then, given a full expression, look for all of the sub-expressions that it can replace, given all of the accelerators that the user had plugged into the Mosaic system. And although I've been talking about Mosaic in the context of accelerators, like Stardust shown here, it actually generalizes to all high-performance systems as long as it can do some external function call. And then to reiterate, through composition of the high-performance systems, and Mosaic has a default code generator to fill in the rest of the code, and through a compilation path, the compiler is able to generate the code that you want for the end-to-end expression, calling the accelerator or high-performance library call that you want. And then actually the numbers that I showed to motivate a sparse accelerator in general, these were all generated through the Mosaic system. So Mosaic was able to call through its default code generator Taco, but then was also able to call Intel MKL through an external function interface and our sparse accelerator through an internal function interface. So what that allows you to do is it allows you to use independent systems all in one system, right? So you can generate numbers and comparisons, but also it gives you a higher level of representation for accelerator programming. And Mosaic automatically takes care of the rest. But now that I've presented a programming system that can call the accelerator as a black box, we need to answer the question of how do we actually program the accelerator itself? There needs to be a way to describe actually the fine-grained computation and mapping onto our accelerator and the fine-grained data flow, as we call it, or the computation ordering within our accelerator. So we do this through the Sparse Abstract Machine, or SAM, and this was work presented last year at ASPLOS. So to motivate the need for finer grained representation of accelerators, let's consider the performance implications of data flows, or in imperative loops, loop reorderings on sparse computations. So by data flow, I specifically mean the processing order of all of the indices, which will modify where the sparse filtering mechanism occurs in our computation. And so that will impact where the compression skipping occurs. These filtering mechanisms specifically include intersections and unions of the sparse metadata. And concretely, let's consider the sparse matrix multiplication example. So here I show all 6 data flows of sparse matrix multiplication on one sweet sparse matrix. And here I want to show that picking the wrong data flow can actually lead to an almost 2 orders of magnitude performance difference. And so this performance implication really means that if a designer or user chooses the wrong data flow, no other optimizations they do can get you back that 2 orders of magnitude on the hardware. And so as previously mentioned, there are many expressions we care about, okay, and there are many data structures we care about. But now to achieve this performance via data flow control, right, which shows up in these expression schedule combinations, they actually lend themselves to multiple backends that we care about, these hardware accelerators that we want to program. And so we designed SAM, or the Sparse Abstract Machine, to be fully general to this. So it is general to all of the expressions in sparse tensor algebra, but it lends itself to multiple backend designs, so both fixed function and reconfigurable, because some fixed function ones are fixed to a specific data flow, and reconfigurable ones can do multiple data flows. And so, well, why do we even care about an abstract machine, right? An abstract machine is just a representation. Well, it's not only general for the input domain and also these backends, it's the perfect compiler IR or compiler target. So we also develop from high-level domain-specific languages from prior work, mainly the Taco body of work. We develop a front-end compiler called Custard to our sparse abstract machine. So it doubles as both a streaming data flow representation and a compiler IR. And then I'm going to go into some details about SAM, but this is an overview. This is just an overview. If you have questions about it, you can come talk to me. So SAM represents data flow in 2 ways. It represents wires carrying data through streams, and then it represents modules that compute on the data streams through primitives. And so from a high level, the way we represent tensors as streams is that we are able to represent multi-dimensional tensors, including higher order ones, as flattened one-dimensional streams. And so here I show an example of a 2D matrix, and one 2D matrix is converted into 3 streams combined. So there's 2 streams for the coordinates and then 1 stream for the values. And the streams have a unique representation in that they have control tokens to maintain the dynamic data shape. And when these streams are streamed back into memory, they actually then can recompress into canonical data structures that we care about, like CSR or COO. And so SAM, like I mentioned, supports all of tensor algebra. And this is done through the interfaces that we define for our primitives. And we call them interfaces because we don't actually care about what how a hardware designer implements these primitives. We only care about defining the interfaces and how they interact with the streams. And so the first primitive class iterates through multi-dimensional tensors, through our level scanners. We're able to combine multiple tensors or merge them together through intersection and union. We're able to repeat operands over other operands through tensor broadcasting. We're able to compute on scalar elements and then also do reduction operations. And then we're able to assign the multidimensional result back to memory. And then it's not really important that you understand how this whole SAM graph works, but this complete SAM graph demonstrates that SAM is able to represent full end-to-end kernels. And so this is, again, for the sparse matrix multiplication example, and I'm just going to touch on a few things to note. So sparse matrix multiplication, specifically the row-wise or Gustafson's data flow here. So K, the contractions in the middle. And the first thing is that our hierarchical streams with data flow through the wires, which are our arrows in the graph. Data flows through our computation spatially. And then hierarchical sparse iteration occurs by composing level scanners together. So one level scanner will stream through one dimension, and then multiple composed together will stream through multiple orders. And then these primitives are format agnostic, which means that you can actually, for the same interface, you can use different level formats. And we have intersectors and unioners, which actually merge streams together, and tensor broadcasting through the repeaters. And then once the metadata is processed, we get the values and perform our computation, and then we construct a tensor result and store it back. And one thing to note is that our reducer is actually a vector reducer. Because it's Gustafson's data flow, you have an outer level accumulation. And the main portion of the computation in these sparse applications is really the metadata processing, which we've seen in a lot of work in this room, but really this graph visually shows this, that this is the key part of the computation. And then I wanted to touch upon an inner product algorithm for sparse matrix multiplication because you actually use the same primitives and the same streaming representation. All you have to do is recompose the graph. And so some key differences are now the reducer, instead of a vector reducer, is a scalar reducer. So it uses asymptotically less memory. And actually, the intersection is now at the last data flow level. So it's after 3 level scanners instead of just after 2, which makes it less performant because you're filtering later. And so although I already explained how we have a front-end compiler and we motivate the need for a compiler, for these accelerators, what you really want is actually a compiler that provides a clean abstraction interface. So this is kind of like LLVM-IR or a stable ISA. It allows you to develop your front-end compiler and have a shared unified front-end compiler and decouples it from the hardware implementation on the back end. So you can do iteration of both independently. And so our front-end compiler, Custard, has an algorithm to SAM, which is very straightforward, which kind of shows that SAM is the natural representation for these data flow graphs. Again, we take in these domain-specific languages from prior work, so a format, a schedule, and an einsum. And we combine it to concrete index notation, which is just an abstract loop nest for sparse tensor algebra. We convert it then to a spatial representation of that concrete index notation. And then there's a one-to-one mapping between the spatial representation of your tensors and your indices to your actual primitives that you lay out in the graph. And then although SAM is abstract, SAM can actually bind to real hardware targets. So we show that SAM, using our cycle approximate simulator, is able to recreate results from prior work, namely Extensor, which is an accelerator from MIT. And then also we're also able to bind it to reconfigurable accelerators, so reconfigurable data flow accelerators and coarse-grained reconfigurable arrays. So this leads me to my follow-on work, which was presented at VLSI 2 days ago, which is we fabricated Onyx, which is a coarse-grained reconfigurable array, or CGRA, that has sparse support for the full domain of sparse tensor algebra. And so some background on CGRA architectures. CGRA architectures are reconfigurable tiled architectures. You can think of them similar to an FPGA, but they're coarser grained. So instead of working on 1 bit at a time, they work on one element, like 1 word size at a time, or they work on, for a vectorized unit, like n word sizes at a time. And instead of lookup table-based processing elements, you have actually ALU-like processing elements. And we used SAM to fabricate the sparse CGRA. So what we were able to do is take prior work, a dense CGRA architecture, implement SAM primitives in RTL, and then produce this Onyx CGRA, which has both sparse and dense application support. And so what this means is that you don't have to understand the primitives here, but there's basically an RTL implementation in Onyx for each SAM primitive. So SAM acted as the architectural specification in terms of streams, and Onyx acts as the implementation to SAM. And on top of that, because I said we decoupled the front-end compiler, Custard was actually used, and SAM was used as the application compiler for the CGRA. So to program the CGRA after it's been fabricated, you're able to actually reconfigure the CGRA and then reprogram it with different sparse tensor algebra expressions. And on top of that, we had to extend the compilation flow to use a more implementation-specific representation. And create a new lowering pass from SAM to that Onyx IR. And then on top of that, we get functional and performance verification practically for free. So here I show the SAM cycle approximate and functional simulator for the repeater block. Because it uses the same streams again as the RTL implementation in Onyx, you can run the simulator and run the RTL simulation together and check functionally if they're correct, and then also look at the cycle count and see where the bottlenecks are occurring in your RTL versus in your actual functional simulation. And the functional simulation is cycle approximate, which means it is optimistic, but you can still see where the big mismatches occur and then figure out how to improve performance in your RTL from there. And so we have some Onyx results, and there's a bunch of results, but we basically show on average that we're between 4.4 to over 500x more energy efficient through our energy delay product. And our CGRA can run basically 8 applications across a varying data sets.
You're supposed to be done with the talk too, but somehow I can't stop my time.
But I am also done with the talk. So in summary, I presented 2 programming systems and a sparse accelerator for how we can program these sparse accelerators and really bring them to high performance users or end users. Thank you.
Thank you. Questions?
Very interesting talk. Can you talk a little bit more about those repeaters you had in this stream of operations? Is there a danger if I have a sparse matrix and a dense vector, where the vector is logically broadcast, by actually repeating that physically, so materializing this dense vector, that you change the asymptotic behavior of this particular operation?
Yeah, that's a great question. So if you're doing it for a dense vector, we assume that dense vectors have random access so that you don't have to repeat across the dense vector. The repeating mechanism is really for broadcasting across sparse vectors.
Got it.
Yeah.
Thank you very much. My second quick question would be, for the mosaic part, where you essentially outline certain primitives into accelerator calls, do you do a fine-grained scheduling that, I mean, I have the accelerator available and the CPU available. If the accelerator is 2 times faster, then I should schedule kind of 2/3 of my data to the accelerator and 1/3 on the CPU to actually fully utilize everything.
Yeah, that's a great question too. In the mosaic work, the reason why we don't call it an auto scheduler, we call it an automatic search mechanism, is because it doesn't have any performance information. So it's only based on functionality of the sub-expression matching to the total expression that you want. And it will search and find all of the places and just enumerate the list. It won't give you a priority ranking, and it won't schedule based on runtime. So that we assume someone would build on top of the automatic search mechanism.
Awesome, thanks.
Thank you.
One more question. Okay, back there. And then we can get to Brian.
Thank you for your nice talk. And I was wondering, is it possible for SAM being plugged into existing high-level frameworks like Rapids, PyTorch, or other graph processing frameworks?
That's a great question. That's ongoing work. We are re-implementing SAM in the MLIR framework and trying to use Torch to MLIR to then implement machine learning end-to-end models through SAM that can then target reconfigurable accelerators.
And is it possible for the users to write his own compiler front end to maps the the high-level operations to the SAM API?
Yeah, so there's a little bit of flux in terms of the MLIR front ends from end user code to MLIR. So that we assume is already provided. It's not like on us as the backend compiler writers, but you would be able to write your own pass as long as you hook into MLIR.
Thank you very much.
Okay, thank you. So now we'll start with the panel. First of all, any questions for the panel? Let me start with one thing, because something I really like about this setup is we get people from different communities. We have some database people and stuff like that. I learned a lot from the database talks. What do you found from the other side of the talks for the database people? Is there something interesting that came out of other things?
So I actually have to brush up on my related work in your community. So I've seen things on lossless compression, for example. In the initial talks, I've seen some of the hybrid relational linear algebra, which is closely related to many of the works we are repeatedly reviewing that we are working on in our groups, and sometimes we are too narrowly focused on related work in our own field. So I think it's very inspiring to look broader in terms of related work.
Yeah, so I also like especially the talk by Amir, where he tries to connect the PL community, the knowledge there, and the relational database things. So, for example, I'm from the database community, and a lot of the techniques there can also be seen as some techniques in the PL, like for matrix multiplication. Its very nature in database, we just represent it sparsely by keeping the index of them and mapping to the value in it. Yeah, it's just nice to have them.
Okay. Amir, do you want to say something? Yeah.
Yeah, so if I want to be negative, I'm academic homeless. If I want to be positive, I have several academic homes. So I was kind of already following the related.
You're in both sides anyways.
Yeah. Yeah. So I think, but so one thing is that there are some techniques in databases that are kind of not, it's being somehow rediscovered in the functional language community especially, but also in the high performance community. So I think the talk on incremental V maintenance, so for example, I've seen some recent work actually on the sparse tensor algebra work that basically is doing something similar, but I think that there are many things that still can be learned from there. Basically relations, so the formulation that was given, basically they were like tensors. Okay, so n array relation is an n-1 array order tensor. And so there are many techniques. So there are recent developments in databases, for example, on worst case optimal joins, which are basically kind of what you were saying about the SPDMM, which was basically rather than considering binary operators, we can consider like more kind of hybrid operators. So this has been kind of based on theoretical foundations. It has been discovered in databases, and I'm seeing actually more work that is trying to connect these two works.
So let me also turn the question to Olivia. You are probably the only architect in here. So what should PL community learn from architects? What should the Sparse community learn from architects? Did you find anything interesting coming from that community that can influence other direction?
Yeah, I think it goes both ways. So I know Saman earlier this morning said that architects don't really care about programming their system. That's actually not the trend in architecture anymore. I think that was the case back when Moore's Law was booming. But now the way you really get people to use your accelerators is through the programming system and the software stack. And so that's how architects kind of can learn from PL. I think the way the PL community can learn from architecture is part of this optimization, like performance optimization, and very like detailed approaches are necessary. And so sometimes I think the PL community oversimplifies a lot of the problem and oversimplifies kind of how hard it is to build hardware, right? And so they'll say, oh, we don't want to build the hardware. Or they'll say, oh, we support these optimizations, but it's not the optimizations that the hardware community has used for years and cares about. So yeah, it goes both ways.
So we have both database folks and people with hardware background on the panel, and there was a time in databases where people are building hardware for databases, and that seems to be coming back a little bit. Should we be building hardware for databases? And I'll add, I remember 5 years ago, 10 years ago, I was in a talk where Michael Stonebreaker was heavily ranting about no hardware in databases, but I'm not sure about that.
So when I just graduated back in 2011, I interviewed at two places, IBM Research Almaden in San Jose and Oracle Labs. And the project I would have worked on at Oracle Labs was the Rapids project, which actually built a kind of database machine again. And ultimately, I was talking 1 or 2 years ago with Eric Zettler, and he simply made the point that if you're building custom hardware, it's not this one-time effort, but you have to keep up with the mainstream development, which is a huge investment. And if ultimately you get an end-to-end performance improvement of 2x, it's simply not worth it having a village of people actually working on it. So it's ultimately an economic measure, I believe. So if you find a sub-kernel that's orders of magnitudes more expensive and the bottleneck, then it's worth building hardware. But in data management, we have so many different operators and kernels that you can't find this one single little piece. So I'm not sure if
there's no matrix multiply, I guess. That's what they found in machine learning. Yeah.
I think there's been a resurgence of, so some of the ideas that I presented about these reconfigurable arrays is a resurgence from the very long ago architecture. So there, again, like the database community, have been ideas that, you know, had been brought up and then lost and then are now coming back because the workloads are changing. And so again, something that Saman said is like, if you target this generality, then maybe the performance cost is okay because you can then keep expanding the space of the domain that you're working on. So it's kind of been a shift in mentality, but we have yet to see, you know, if this will work in production. The other thing is that a lot of hardware ideas in the architectures, maybe you don't build the end-to-end system, but the ideas from these like architectural subunits have been making their way into production, like the TPU, the MTIA, right? They have the sparse cores, they have these indirect memory lookup fetches. So it's often not about the full end-to-end hardware, it's about the ideas that come up and then go into a mainstream hardware.
Questions?
So I guess to continue along this lines, I'm curious, thinking about bandwidth and compression and hardware, and it's sort of from what I was talking about earlier, what really matters here? Where is it cutting close to the bone, in a sense? Like what aspects of SAM and the Onyx construction for Olivia is this bandwidth bound, or are you looking at workloads that aren't? Where is the tension there? I think also from Matthias on compression for databases, wondering if you can chat about if there's anything productive there.
So one thing that I did not touch on is that the utilization of our array for the sparse applications is actually very, very low because the sparse kernels are they're kernels, right? So our array is more performant when things are fused or you have multiple inputs, multiple cascaded einsums. And so that is something that we need to look at. So I think we reach about like 1% of peak when we're running our sparse applications. But that wasn't really the problem we were trying to solve. The problem we were trying to solve is that, okay, no such system exists. So now that we have these numbers, how can we get to what you were talking about, Gilbert, with like the utilization and figuring out, okay, how do we actually integrate the sparse and the dense side? And how do we actually use the dense hardware well and the sparse hardware well? So I think those are open questions that still need to be solved.
So for lossless compression, we have seen great successes in the sense where the compressed representation actually if we look at what we could have achieved with a sparse or dense representation, went far beyond essentially peak bandwidth bounds. So in that sense, compression helped really push the boundary there. But I think nowadays we're in a decade of specialization in many, many different dimensions. So my PhD student who followed up on compressed linear algebra, instead of having 4 different encoding schemes, we currently have 350 for all sorts of specific characteristics, data types, dictionary sizes. And I think that combined with new data types that you see in the hardware accelerators with different ratios of having exponents for a certain range, but in various forms of precision, automatically exploiting that has huge potential still that is untapped right now. I think people are good at optimizing for the common case, but as we get more and more specialization, we need to think about new abstractions and then really pushing this down. And compilation, in my opinion, is one way toward that, but there are other kind of microkernel approaches and things like that. Yeah.
Yeah, I just want to add another dimension to the problem. So we are right now focusing on kind of some architectures that we have full control over. So there are also other architectures. I'm using double quote. So for example, the cloud environment. So so I think there are kind of another kind of abstraction layer also on top of hardware that we can consider, and similar problems arise there. So for example, I don't know, in AWS you have like the S3 layer, and then you have basically compression and decompression there, and perhaps you need to basically consider kind of the abstractions that are kind of sitting. I don't know whether they are like hardware abstraction, but perhaps the SAM could be a kind of good abstraction for that as well. But I think similar problems in a different scale also appear there. So again, the memory bandwidth shows up, but then it's going to be basically the communication that happens across different nodes. Yeah, I just wanted to make the problem even more problem.
No. Other questions?
Other questions?
So there's a compilation of these sparse programming models, but apart from that, in the database world, Hyper and various other systems have started to bring compilers for low-level code generator into databases, and that seems like it's become more and more common. What are your thoughts on that trend from the database side, and where do you think it will go? Where is it going?
So there are 2 classical execution modes nowadays that are the state of the art. One is vectorized, where you essentially take from a column small little vectors that fit into your cache hierarchy and you pipe them through. There it's super simple to implement because you have just tight loops that you're implementing and you're composing, you're interpreting a plan, but piping through those little vectors. And the opposite is you have query compilation in a push based manner, and you're utilizing kind of the LVM stack and others. And actually the 2 opponent groups came together. So Peter Bons was actually at the Humboldt Stiftung professorship part-time at TU Munich. And here I wrote those really interesting papers of saying, on the same footing and implemented in the same system, we systematically compare the 2 things and found that, well, it depends. It's there are use cases where one outperforms the other, but generally they achieve similar performance. But what you see in practice is that both are applied. So there are large systems like AWS Redshift that heavily depends on code compilation. There they have challenges though. Challenges again in the combination with specialization. So they have lots of different lossless compression schemes. And if you want to generate code for all those different schemes, it's a combinatorial explosion. You have to pre-build things. So they try to separate at certain boundaries to avoid this combinatorial explosion.
So actually, my PhD thesis topic was on the kind of code generation for databases, and so I totally agree with all the points that Matthias mentioned. I think one of the problems, there are 2 main problems that actually to kind of integrating these code generation mechanisms in basically industrial databases. One is the complication of that. Of course, whenever you add a compilation component, it's going to become much more complicated. But the vectorized engines are easier. to maintain. The other thing is that the code generation time. So the recent kind of research line in databases on this topic, so most of the problems were solved. But the interesting research problem is that, okay, you could have very large queries. And so whenever you have a vectorized engine, yeah, you're just going to interpret it. And you're going to basically pass vectors in the string. Whenever you're compiling, you have to generate machine code from that. And basically, there are line of work on how to generate directly assembly code from the physical plans of databases. Yeah.
Just adding one, there are also hybrid approaches where you try to get both of those things by start interpreting, compiling in the background while the query is already running. Whenever this compiled version is ready, you swap them out and kind of get, if you actually process a lot of data, then for the majority of the query, a really compiled query plan.
And one other component that exists in databases, and actually so it was in Matthias's slides, and I don't, maybe I overlooked, I didn't see that much research in the kind of programming language and compilers world, is basically this kind of sparsity estimation or cardinality estimation. And that is the Achilles heel in databases, basically. So it hasn't been properly solved yet, the problem. So the kind of main technique that database systems are using, most of them the industrial ones, is basically you create histogram of your data. And the challenge is that, okay, whenever you're joining, then how you would basically propagate this information. So what is the kind of, you have to basically see what is the dependence of different attributes to each other. And so because then you can, the choices, basically the schedules that you choose are totally dependent on the size of the intermediate results that you would have.
So I want to push that question to Olivia. So in SAM, are you doing anything about finding the cardinality, especially things like if you want to do like sparse left-hand sides?
So currently, in SAM, we do not handle that. We have looked at like some data analytics for these sparse tensor data sets through some of the work with Gilbert, but also some of the work through the AHA project where Onyx was taped out. And right now we're also just looking at histograms. So this is a problem that it also exists in the sparse community, like regardless of hardware or not. Because if I ask a question about, does this schedule make sense? And I ask Fred, and Fred, knows a lot of things about sparse things, and he goes, I don't know, right? So these are the open problems that we're trying to solve as well in the sparse compilation community. Yeah.
So basically, Fred is the cost model.
Fred doesn't know.
And says infinity.
Okay, I guess with that note, we will finish the panel. We'll thank the panelists. So we'll start off lunch.
Yeah, they were all made this morning.
Should we be very on time or should we leave 2 minutes or so? Okay. He's not trying? Okay. He's on a panel. Oh, the RT. Okay. Hello, everybody again. Welcome back from lunch. And now we have the session on compilation frameworks. And we are starting with the talk by Max on equality saturation and joins.
Right. All right. Thank you, Amir. Yeah, so I'm going to be talking about a couple different topics today. It's going to be a bit of a whirlwind tour, so I encourage you to talk to me afterwards if any of these sparked your interest, because this is going to be surface level at best, given the time I have. All right, so I'd like to ideally make it through all three of these topics. We'll see how it goes. A lot of the work that I have been working on recently centers around E-graphs, which is a data structure, and equality saturation, which is a technique for program optimization that, as I believe the next talk will sort of focus on, has been used in for sparse optimization as well as other sort of compilation and program synthesis contexts. So I'm going to give a quick whirlwind tour on that and actually sort of leave the application to sparse context to the next talk, because I think they're going to do a better job than I'm going to do. But then I want to move on to how recently we've been focusing on using relational techniques to basically power this compilation technique of equality saturation. And sort of branching off from there, another sort of angle on this recent work that actually came out of our sort of trying to imbue equality saturation with this relational perspective is an entirely new family of join algorithms, which we recently developed that we tested again in the relational setting, sort of applied it against DuckDB and things like that, but I think could see applications in the sparse context as well. All right, so let's get started. So if you haven't seen E-graphs before, this is an E-graph. This is sort of baby's first E-graph on the left here. It looks very similar to an AST. This is, in fact, a very boring E-graph. And that's because we've partitioned it into two parts, E-classes, which contain E-nodes. But all of our E-classes here, those are the dotted boxes, only contain a single E-node. Right, so we're not really representing any equivalences yet. And we say that an E-class can represent a term when you can sort of follow the lines and find the term within those boxes. So this E-class containing the division E-node represents this program, A times 2 divided by 2. And so we're going to try to optimize this program down to A. And we're going to do that via rewriting. And we're going to start out with this sort of potentially troublesome rewrite, which if you were in a greedy rewriting system would sort of represent a locally good idea, it's a strength reduction, but globally bad idea because you're going to take a wrong turn here and sort of miss an opportunity to cancel out this multiplication and division. So the way we do that is we look for instances of the left-hand side, just like in rewriting, and we apply the right-hand side. But instead of replacing the multiplication node with our shift, we add it to the same E-class. All right, now we've got something interesting going. We have an E-class that represents two terms. It's got two E-nodes in it. So we have our left-hand side of the rewrite, A times 2, and the right-hand side, A shift 1. And this notion propagates upwards. All right, so the E-class containing the division E-node, it's a singleton. There's only a single E-node in there, but it represents two programs. A times 2 divided by 2, that was our input, and now our misoptimized input as well. And long story short, this is a monotonic process, right? So I haven't lost anything. I can still see my A times 2 there. And so if I wanted to now go down the correct path and actually find the cancellation, I could still do that, despite the fact that I sort of took a wrong turn. at the beginning. And in fact, you can hit a phenomenon called saturation here, where if we keep applying these rewrites, we'll observe that nothing actually happens to this e-graph. It's what's called saturated. You'll try to apply a rewrite, and you'll add the shift node, and you'll be like, hey, the shift node is already here, right? And when you hit this point, you've sort of learned everything that you're going to learn with respect to these transformations on your given set of data. And then finally, if we want to use this for optimization, the final step is called extraction. So what we do is we identify, well, where did we put our input? There's a lot of these different classes of equivalent programs, so we've got to remember where we sort of put our input, and so we put it in this funny shaped E-class here. And then all we do is we look for the smallest or cheapest, depends on what your cost function is, program. And if your cost function is sort of cooperative, we can do this very quickly via dynamic programming. And if it's uncooperative, then, well, we have to resort to sort of heavier techniques. So this is, again, the sort of whirlwind tour through equality saturation. The basic workflow is we take our initial program, we chuck it into the e-graph, and that's going to initially look like our boring e-graph, right? It looks like an AST, one node per class. And then we start cranking our rewrites. And again, this is a monotonic process, so you don't really have to worry about taking wrong turns. You can apply a transformation, and the things that were transformed are going to still be present within that e-graph. And ideally, you would hit saturation, but in practice, this is a non-terminating procedure for many rewriting systems. It depends on the system. You stop after some limitations, and then you can extract an optimized term, and voila, that's how you do optimization using e-graphs. This loop is hiding a lot of work here. This is sort of the bread and butter of the algorithm. This is where all the work is being done. And like a lot of sort of iterative search-based algorithms that are doing all this complex matching, there are some bottlenecks. Okay, and in particular in our workload, the bottleneck is in a stage of the algorithm called e-matching. That's basically when you're doing the rewriting, you're looking for instances of the left-hand side. It's a lot more complicated in an e-graph because it's a compact encoding of a bunch, like exponential number of terms, and so you can get a lot of matches, and you want to filter out a lot of those potential matches that are not going to match the rest of your pattern. And so we developed a technique called relational equality saturation to sort of optimize this e-matching procedure. And this came from a couple insights. First of all, equality saturation, as I was saying, is a monotonic procedure. You can sort of squint and be like, hey, this is sort of looks like a database that is growing. We're just adding facts to it. We're adding more equations, we're adding more terms. It's only growing. We never lose anything. There's no destructive rewrites. And as I was saying, e-matching is the bottleneck. And if we sort of squint and think about, well, what is e-matching doing? Well, it's a backtracking search for substitutions that satisfy some sort of pattern. This is basically a formula. And if you're familiar with Datalog, which is I'm sure many of the folks in the room are, then these sort of terms, bells should start going off in your head. Hey, it's a monotonic process. We've got this whole search for substitutions that we instantiate on the right-hand side to add more things to the database. And so we started thinking, hey, can we encode equality saturation into Datalog? The biggest step of doing this would be encoding e-matching as a conjunctive query, as a relational join, basically. So let's see how we do this. The essence of it starts from a very simple flattening. This is very standard if you want to represent tree structured data in a relational context. So here's a simple AST here, and we have one table per kind of function symbol. So you're going to have a plus table, maybe a minus table, F table, G table, times table, whatever. And the first couple columns are going to be the arguments of this operator, and the final one is going to be the value. And this is just a marker sort of that is unique for every invocation of the function. So B plus C gives us BC, and A plus BC gives us ABC. These are just names for now. It's also worth noting that these constructors are they're functions, and so there's a functional dependency in all of these tables from the arguments to the output. And in fact, in the other way as well for now. OK, And this resulted in the tool, which is called egglog, based on egg, which is our original egraph library, plus datalog. And when you really look at it, what it does is it boils down to datalog plus functions. So you need a notion of functional dependency, plus an extensible notion of equality. And we'll see how those two features interact in just a moment. Well, if you could click in this slide, you would see that these are links. But you can write programs that look and feel just like classic datalog programs. So if you wanted to do like your classic datalog program, you have paths and edges, and path is a recursive. Your edges are paths, and paths are edges plus paths. You can write that just as well in egglog. You can do some fun things by combining datalog with our extensible equality. And by extensible equality, what do I mean here? Well, in egraph land, one of the primitive operations that you're allowed to do is say, hey, this E-class and this E-class are the same. We merge them, right? So we're saying that all the programs represented in this E-class and all the other ones in this E-class, we've learned that these are now equivalent, okay? And in an egraph land, when you when you union these two E-classes, this propagates up and you might learn new equivalences and things like that. And likewise, in egglog, everything reacts to these new equivalences. So if you wanted to write your reachability program, where you have a graph and you're talking about, what are all the paths through it, and then you just said, aha, this node and this node, they're the same, right? Well, in sort of graph land, what that would be like is you take these two nodes and you merge them, right? This is going to create all sorts of new paths. And that just sort of falls out from our egglog implementation. And finally, you can do things like equality saturation. You can represent tree structure data, and you can prove them to be equivalent, and you can extract out optimal things. And this implementation of equality saturation falls out from the interaction between functions and extensible equality. So let's briefly just take a look at where that comes from. All right, so if you have functions in your data log, you typically, or in any relational context, again, we're going to sort of tabularize them. So, it's a table, an n-ary function goes to an n plus 1-ary table, where the output is the last column. And so here are two tuples, right? They're recording that f of a is b and f of c is d. Easy peasy. Well, what happens? Our equality is extensible in this world, right? So what happens when the user asserts a equals c, right? We said that there's a functional dependency between the first column and the last column. And these equivalence assertions can violate. They can induce violations of functional dependencies. So what happens, right? And so the natural question is, what happens in, if you look at data logs that feature semi-rings or lattices, where the last argument has a lattice value? What happens when you have two tuples who overlap in their first n arguments? Well, you combine the last argument according to whatever the lattice laws or the semi-ring laws of that system dictate. Okay? And we have a very similar system in egglog. We call them merge expressions. So we can do the lattice stuff, and here's a very straightforward example of how that would work. So if you have a function foo, it just goes from integers to integers, and we need to give it a way to say, hey, if there's a collision in our inputs, how do we rectify that? What do we do between? We can only have one output. We have to pick one. So say we set foo of 7 to 5, and we set foo of 7 to 4. Well, here it's pretty clear. Our merge expression is going to take the min of the old and new values, right? So that's what's going to happen here. More interestingly, we can get basically congruence closure, which is the thing that powers the egraph, by just getting a little bit more creative with our merge expression here. So if we wanted to build terms, tree structure data, well, that's nothing but a constructor is just a function that takes in an expression and maybe a couple expressions and outputs an expression as well. And how do we rectify sort of FD violations there? Well, we use the underlying union function, right? And this is going to, in our union find, sort of in the underlying data structure that's tracking equational, the extensible equality, we're going to identify those two values. OK, so all those extra features are really nice. But again, what I was saying earlier, the reason why we sort of dipped our toes in this relational technique is we wanted e-matching to go faster. And long story short, it goes way faster than the previous approaches, which just use backtracking search. You know, we're sort of cheating here because it's asymptotically faster, right? These algorithms were never designed to search very complex patterns. You can, you know, if you squint, you can sort of read this very long pattern, which, you know, translates to a reasonably long conjunctive query that has all sorts of variable reuse. And the backtracking algorithms just aren't built to scale for that. But the relational technique does. You know, and for simple patterns, you know, you don't gain very much because there's no joins. Okay, so what is actually the join algorithm that is powering egglog and other, and now hopefully, you know, some other relational techniques? And this is another strain of work called free join. And I promise you, you can. This paper was just selected as a SIGMOD research highlight, and my colleague Remy did a great job of sort of simplifying the exposition and making it much more readable than whatever I'm about to, you know, throw at you in the next 2 minutes. So I encourage you to check that out. The basic idea is you want to combine some of these newer worst case optimal join, also referred to as variable at a time join algorithms, with binary or relation at a time join algorithms. We want to sort of break that dichotomy in free join. And as a teaser, I'm going to explain how free join works, but one thing that I'm not going to explain is how do you compile these plans? I think this is an open question that you know, I would love to see some sort of future work on. So let's start from binary join, and we'll get to free join, and then we'll approach it from another perspective. This is the Clover query. If you're not familiar with it, it's basically, you know, X joined with 3 other, you know, things. And let's just look at the free join plan, and we'll explain what it means. So this is a free join plan that sort of represents the binary join plan, where you first join R and S, and then you join the result with T. So if we're going to do that with nested loops, what would we do? Well, we would first iterate over R, and for every you know, tuple in R, and so that's sort of what we're doing here. Each of these groups, each line corresponds to a loop level, and the first atom, the first or subatom rather, tells us what we're iterating over. Okay, so we're iterating over R, and we're taking both values, X and A. And then to the right of the bar, that's going to tell us what we're looking up at this loop level. These are the sort of the probes. You know, we're probing into those hash tables. So we're going to look up using the you know, the join key for the R and S join. We're going to look up into S. Well, that could result in many values of B, so we're going to loop over those, and we're going to probe into T. And then finally, you know, there could be many results in C, so we in the C values of T, and we're going to loop over those, and we yield. There's a better plan, though. There's a pretty straightforward optimization to this. And that's, you can see that, hey, well, this indexing into T with value X, there's no need to wait to the second loop level to do that, right? As soon as X is bound, you can do that right away. So the free join allows you to very concisely represent these kind of optimizations. You could go even further and say, hey, this value of A, we don't actually even need it. We don't need to iterate over all the attributes of R. We only need to iterate over the X values. We don't need A until much later. And so now we could write at the first loop level, we're going to iterate over just R of X, and we're going to look up X and T. And then, sorry, these are 3 separate loop levels here. I just ran out of space. But you'll notice I didn't write a bar here. I just wrote a comma. And that's because, well, when the schema of all these subatoms is the same, you can sort of choose, it doesn't matter which one you iterate over. And in fact, you want to choose dynamically to say, hey, I may not want to iterate over R and look up at S and T. I may want to iterate over S instead. And this represents a sort of an intersection that you might see in generic join, where you're dynamically, based at runtime, choosing whichever one of these has the lower cardinality to do an intersection in the time scaling with the minimum of them. And I think this will be even more clear when we approach free join from the generic join side of things. So let's look at the triangle query. If you're familiar with worst case optimal joins and how generic join operates, the free join plan for this isn't super surprising, right? You're going to intersect on all occurrences of X, loop over them, intersect on all occurrences of Y, loop over them, and then intersect on all occurrences of Z and loop over them. Okay? But this is free join. So if we wanted to do a different plan, we can. We can represent all kinds of different plans. Like say, for example, we didn't have a try to index over R. Or maybe R is huge and we didn't want to build such an index. We wanted to scan over it. Well, we can scan over it. We can loop over X and Y and then do immediately lookups into S and T. And then we can still intersect over Z in the second loop level. So we've lost a loop level. So for some statistics, this might be a better plan. And that's basically all I have to say about free join. You should check it out. We have an efficient implementation, blah, 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 in the paper. There's some cool systems things. We have an eval against DuckDB. Again, we don't know how to generate these plans. So we started with binary join plans from DuckDB and sort of massaged them into free join plans. I did some light examples. But you could probably, from scratch, come up with much better plans. Not only is it faster than DuckDB, but one interesting thing that we noticed, and other folks have noticed this as well, that these join plans that are based on worst case optimal join are much more robust to bad statistics. If you have bad statistics, this might be an algorithm to check out. OK, that's all I got. Thanks.
So, Avery, do you want to set up? So we have time for one question, perhaps.
Thanks. Really cool. So if you didn't have a compiler, did you write up the different algorithms by hand? Or did you have some sort of other implementation than a compiler?
So we took the join plans.
Can I hold the microphone? Or?
And you wrote them?
And so it just
oh, sure. I can use this.
Binary plan. And every binary plan is admissible as a free join plan. So we just start from there and did only obvious optimizations with that.
I see, but you manually wrote the code, or did you have a generator?
No, we have an automated generator that takes like analyze SQL analyze and creates a free join plan.
Cool. Thanks.
But the execution engine is better. If that's your Okay. So the second talk is by Avery on spec, which basically uses equality saturation for translation of sparse code.
Thanks. So my name's Avery, and I'm excited to be presenting spec. This is a joint work actually between University of Toronto and some folks at Microsoft Research. And the first thing I want to do is just show you right off the bat like an example of the goal of what we're trying to do here. So on the left-hand side, this is a snippet taken from the NASA Parallel Benchmark Suite, which for compiler people, this is a very famous benchmark. And it's doing a matrix vector multiplication. And the matrix is stored in CSR. And I felt kind of silly like throwing up a slide about CSR at this workshop, so I'm going to assume everybody knows what compressed sparse row is, but if you don't, let me know. I can dredge up a slide about that. But anyway, so it's operating on a sparse matrix. And I'm coming at this from the perspective of a general purpose compiler person. And if you give this to a general purpose compiler, it will not be able to do anything for you. So wouldn't it be nice if instead you can automatically translate this code into like a library or a DSL that's already very good at executing this code for you. And so I have an example there. This is using QSparse to offload to GPU. You can imagine a similar thing with MKL, and actually you don't have to imagine because it will do it for you. And we also support OMP as well. And an important thing to note on this slide is that if you want to do this translation correctly, which is a big emphasis of the tool, then you also have to make sure that the input, in other words, the sparse matrix in this case, is in the form that you actually expect. You have to verify some kind of precondition. And in this example, because the matrix is stored using CSR, we have to make sure that it actually does represent a sparse matrix at runtime, because it easily could not, depending on the input data. So I'll have more examples later in the presentation to explain all of that. But before I move forward, I also just want to clarify a bit of the motivation, because I think for practitioners, probably in the sparse domain, a lot of the questions come up for me is, okay, why not just do this by hand, or use one of the many existing tools out there? And it's definitely true. Like, you can imagine, especially for somebody who knows sparse codes, they look at this, they immediately know what's going on. Okay, let's rewrite it to like the latest DSL. And there's two main issues I see with that. So the first issue is it's very tedious. So a lot of legacy codes that you're going to find this pattern in are they're old and they're big, and so you have to search through the whole thing, find these cases, make sure it's actually in a form you expect. And you can imagine that you do that, maybe you make a mistake. So it's also error prone. But you could do the whole process, and now it's in the newest, fanciest DSL. But there's a DSL born every day, and so there's all of these proliferation. And then what happens when the new accelerator comes out that your DSL doesn't support that accelerator yet, or it's not maintained anymore? You have to do the whole process over again. So what we're aiming to be is like the layer in between these great tools that are out there that can generate super fast sparse codes for you, or maybe handwritten implementations, and some existing code you already have that you just want to automatically get into that form. Okay. So this is the general pipeline. We operate on LLVM IR. And I will go step by step through this pipeline just to explain the whole process using a running example. And we can take a look actually and compare what is possible just with this SPMV example that I showed in the previous slide. So on some of the benchmarks we tested on, there was 4 of the benchmarks that actually had some kind of SPMV happening in there. And we support, for this version of the paper, OpenMP, MKL, and QSparse. And so this should not be surprising, right? It would be really weird if you weren't getting really high speedups. So I'm not showing this to say, okay, we get amazing speedup and that should be impressive. More, I just want to give some indication of what's possible when you step away from relying on the general purpose compiler to do something and find the global maximum of performance. Okay, so let's start with the first stage of the pipeline, which is where we try to figure out what storage formats are actually being used in the input code. So there's the running example again on the left. And on the right, I'm showing kind of like a cartoon. It's not totally accurate, right? There's more detail hidden underneath. But this is a graph to represent the relationship between definitions in the program of variables and the usages between them. So for example, we have some J induction variable, and it has a range, in this case, from 0 to M. And this arrow is to indicate that it's used by this other range below, from row j to row j plus 1, and so on. So that's how to read this graph. And as I mentioned, everything here is in the LLVM IR. So I'm just showing the source code here, so you don't have to parse a bunch of LLVM IR. And so we can generate this graph very straightforwardly from the IR. And then we also have, a library, a database of a bunch of different storage formats that are used in these types of codes. And this is not something we made up. This is very, very, very well explored already in previous work. And for each of these formats, you can generate kind of like a template version of this graph that has the same structure. So I'm going to need some kind of V2 that has some sort of range, and some arrays in here that have very particular constraints as well. And so you can try to create a correspondence between what you actually have in your input code and what you expect to see in codes that use particular storage format. So this very first step is just a way to give you like a very rough guess about what kind of storage formats might be in there. And there's more details in the paper about how the matching works and everything, but I'll just leave it here for the talk. But of course, like this is a guess. So it's not at all guaranteed that it will be correct. There's two main things that could go wrong. So the first thing is you could have made a correct guess in the sense of all of the correct structure is there, all of the variables that you need are in the program, but at runtime, it's actually doing something different. So this is an example on the left to show some data that doesn't actually represent a sparse matrix. So to call a code like this with this input data in SPMV is wrong. It's not actually doing SPMV, it's maybe doing something else, or maybe it's a bug, but anyway, we can't call it SPMV. And the other issue is that there might be some format or some other structure that spec just didn't match or didn't understand. And given all the different types of formats, that's not so hard to imagine. And so we want to have a way to make sure that we guard against these two cases. And the way that we do that is through an equivalence check. So how it works is we have this input code, and it's operating on some sparse format, so in this case, CSR. And we have a guess that this is CSR, but we don't know for sure. So what we can do, based off our knowledge of CSR, is we can create a version of the input program that looks like it's operating densely. So we can try to factor out, we can invert the compression process, try to get a version of the program that looks like it should be dense, and that's represented by this dense matrix below. And these two versions of the program, if we made the correct guess and we detected all of the storage formats, they should be provably the same program. And if we miss something, then they will not be the same program. So the next question is, okay, how do we actually prove that these are equivalent? That's not a super straightforward thing to do. And here, these next two slides, I just want to give a broad intuition of how it works. I have some slides after with actual detail, but I'll go quickly over those because it's a bit complicated for a shorter talk like this. But how it works is we could have two possible cases between these code versions. Like the original input code version is on the left, and the code version that we created is on the right. And one possibility is that they're both processing the same elements at the same time. And in that case, we can prove equivalence for each step just by checking that these states are equivalent. And visually, it's fairly easy to see, okay, yeah, these should be equivalent. But the sticking point is when you have this kind of thing happen, which is the dense version of the code is processing all of the elements, including 0 elements, not just non-zeros. But the input code is sparse, and so it's allowed to skip 0 elements. And we have to be able to relate these skipped states back to the dense version of the program. So that in transition system terminology, that's called stuttering. And I have an example of the transition system snippet on this slide, where the dense code is taking one extra step. In other words, it's processing this 0 times P4, while the sparse system is idling in this same state. And this red dash is to indicate that these two states are related. In other words, they're equivalent, because if I add 0 to this, I get the same thing as before. Okay, so we can prove these are equivalent. And for anybody who is interested in the details, this is how the joint system itself is actually created. So we smush all of the variables together from each program. We conjunct the initial states of the program, and then we have a relation where this is the dense program. It will always take a step. But the sparse program has two choices. One choice is that if there's no zeros to process, it will have to take a step. Or if there are remaining zeros to process, it will idle. This represents the idling transition. And we wrap this up into a proof rule that I'm just showing for the fancy formulas. But the main part of this formula rule is SR3, where we're able to prove that these two programs are equal in all reachable states of the transition system. And this is an example instantiation of like what these relations actually kind of look like, just to give you an idea. So like when both systems are processing the same elements, we have a certain predicates that are true. And when the dense system is processing a zero, then we have to make sure that we're asserting that there is a zero stored in the dense version of the matrix. And this M represents a way to measure the distance of how many zeros there are still left over to process. And this is a way to guarantee that the dense system will always catch up back to the sparse one. Okay. So for more detail, yeah, you can take a look at the paper. I don't want to, bog everyone down in the details here. And the final step is we want to try to recognize the dense version that we created as having some sort of knowable semantics. So in this case, we'd want to recognize it as a GEMV. And we do this through equality saturation. And Max already did a really great job of explaining E-graphs. So I won't re-explain everything here, but basically we have some written reference implementations in like C or Fortran, whatever you want, as long as it gets into LLVM IR. And we generate a rewrite rule from each reference implementation. So if you give me a reference for GEMV, then I'll create a rule that says every time I see this in the E-graph, you can just rewrite it to this kind of, you can think of like uninterpreted function label. And then we also take the format-free code that we generated, we create a term out of it and put it in the E-graph. And now, because of the rewrite rule we had before, we can E-match on these two symbols and assert that, okay, now they're in the same equivalence class. In other words, we've proven that our input code has this mapping to what we call a GEMV. And the final step for translation is basically a lookup table. Like if we know the input code is GEMV and we know that it's using CSR, GEMV plus CSR, SPMV. And we can, for Sparse, we know, okay, this Sparse call relates to GEMV and CSR, this OMP call, so on. MKL call. So we have an evaluation over 10 different benchmarks and different formats. And the spec itself is actually not specific to sparse code. Like it's designed to handle types of sparse code, but we also can handle like reduction, histogram. Like I said, anything you give us in the reference implementation, spec can search for it using the quality saturation. And we also compare against some other tools that do a similar sort of thing, but we're the only ones who actually check the preconditions to make sure that it's correct. Okay. We're also not too slow in terms of latency. So even though the whole thing is implemented in like Python, we're usually fairly close to the O3 pipeline at LLVM, which is multi-threaded C++. So there's not a huge overhead here. So the main idea of this tool is you should be able to give us a reference implementation of some code that you're interested in finding, and we can go through, as we compile your code, we can go through and look for instances of that and let you decide, okay, I want to offload to this or this or this. And the artifacts are available online. There's instructions for how to add your own kernels that you want to look for and add your own backends. So please, feel free to download it, give it a try, and let me know, what bugs there are and everything. But yeah, that's everything I wanted to talk about. So thank you very much for your time.
Time for one question.
Thanks for the talk. So do I understand correctly that you're executing those precondition checks during runtime for every input matrix? And does it then even apply for a matrix vector multiply, where if you have a memory bandwidth bound operation and you have to scan actually the entire matrix to detect there are no duplicates in column indices, does it make sense to apply during runtime?
That's a very good question. It depends on the storage format and it depends on the context of the code. For example, if you have an SPMV inside of a conjugate gradient code, the runtime check can be hoisted out of the conjugate gradient loop and easily amortized. You also don't have, the preconditions can be simplified greatly. Like you don't have to scan the whole matrix most of the time. But that also depends on format. But yeah, I can also discuss more with you after.
Thank you.
Please click this.
All right. Yeah. So the next talk is by Tobias. So sorry for redundancy. That's my creativity. There are two DSLs there. So he's going to talk about how to design DSLs with XDSL.
Exactly. So yeah, well, thank you for everyone being here, and thank you for all the previous really interesting talks. So I'd like to talk about really like a compiler framework that we've been building initially in Edinburgh, where Ami is currently, and now in Cambridge, for building DSLs, or for building domain-specific languages. And I'm very brief with the kind of the motivation, but kind of our motivation came from kind of domain-specific languages. We collaborated with the D'24 project, which is a Python DSL for HPC, computational science. And there was this interesting realization that as D'24 became more and more successful, it became more and more a compiler project rather than a kind of HPC project. And obviously, D'24 also was more and more interested in saying not just we can run on GPUs, but really can we run on the latest AI accelerators? And then there was this interesting tension. Does Imperial now want to hire all the like AI compiler experts for the HPC project, right? And so that's how our project started. But kind of the more general question really is how can you build compilers for these kind of very specialized hardware? And in particular, our take on that question is how can you do that in a sustainable way, right? So D'24 had this HPC DSL, implemented in Python, has 3 IRs, applies many classical loop optimizations, and does actually really interesting. I mean, this is now a seismic imaging example, really interesting computations using algorithms like around reverse time migration to get a picture of the ocean ground. What I was deeply excited about is that when I learned that you can use very, very similar algorithms to pretty much get like CT level imaging just from an ultrasound, which I found really cool. But anyway, like this is a very domain specific application and they built a compiler internally, right? And it's incredibly successful, right? D'24 is actually a research project that is used at scale in industry just because it's so convenient to use it from Python and it actually provides the features people need. And at the start of our project, Google had a very similar problem that they had a framework called TensorFlow, which was quite large, had also a different kind of IRs, and then pretty much their solution was to eventually build their own compiler framework. And so some of you may already realize what I'm talking about, and I try to be very brief. So Google at that point developed a compiler framework called MLIR, which had the objective to make it really easy to instantiate reusable abstractions and kind of put them together and then use that to pretty much build your own compiler for whatever domain you want, right? And just to give you a brief introduction of what MLI really is, if you have a stack language, for example, that you want to optimize, and you want to build a compiler for that language, you pretty much can turn that stack language in an LVM-style IR using MLIR. Looks slightly more verbose, but in the end, what you need is what's called an MLIR dialect for that abstraction. And in this case, you have a stack dialect where you can push and pop types to your stack, and you have a stack type, right? And the interesting thing, and I think I'd like to be a little slow here, even though that's relatively simple, is that really the key idea is that whenever you have an abstraction, whenever you have a set of operations that somehow interact with, like, can be simplified through the thing around that framework, it's very useful and powerful to build these kind of things. And then, for example, you can use your DSL compiler to try to optimize these things. Then your stack language might fall away and become more optimized, right? So that's the idea of MLIR. And hopefully I convinced you in a couple of minutes that MLIR is an amazing thing, right? Some of you may believe that this was probably too short to convince the people who don't believe it yet, but maybe you have heard of it. So I was convinced, and so my objective in Edinburgh, now in Cambridge, was to kind of use this tool and research and open source development, for teaching at scale with students. I wanted everyone to use MLIR. I found it's amazing. So that was my objective, right? And actually, this is kind of, it's funny because I moved to Edinburgh and there was a little bit kind of, I had to take up a compiler class, needed to teach it, and it was kind of an old Java-based course, and I was just like, should I really learn, like update my Java skills to kind of teach that class, or should I just teach MLIR? And then we were really motivated and kind of just really tried to teach MLIR. In particular, we wanted to teach a lot of compiler concepts, but we quickly realized and actually burned one student over the summer on kind of the overwhelming complexity of the actual framework, right? There's a lot of unrelated tools there. So we realized that just getting started with this framework is really difficult. And so what we built is just actually tailored for students, a framework that is pretty much a deep copy without scientific novelty of MLIR purely in Python. And this kind of minor shift of like implementation language actually made this tool so much more accessible. So we really focus on approachability, accessibility. We try to reuse all the existing concepts already in kind of the production compiler world. And in particular, what I think was quite new is that we made that framework very much interoperable on the like textual IR representation. I have a slight motivation why it makes sense to have many IRs, but I think we go very fast. Over the last 5 to 10 years, there was just a huge explosion in IRs, and kind of we moved away from a linear compilation flow to really an entire DAC of abstraction that kind of gets built by many different domain-specific languages. Matrix multiplication, as a result, can be expressed very directly with like structure and control flow. And as you see, some of these operations, the for loop, the store, are relatively high level in the sense there's a full for loop operation in your IR. You can also have very tailored types, right? Reasoning about high-level multidimensional tensors is quite useful if you target modern AI accelerators. So being explicit and maintaining that kind of information is really helpful if you want to target kind of any hardware that exposes domain-specific expressions at the hardware level. The attributes is also there, but that's not a major thing. But this kind of structured nesting of control flow is what I think makes MLIR quite special. And so then you can really move through abstractions, through your compilation graph, eventually generate GPU code, and that is MLIR, right? And so what we did, what I found quite amazing, is next to MLIR, we built up almost like a parallel ecosystem of compilers that feels like MLIR, that does exactly the same thing. So you can actually quite easily transition between these two ecosystems. But sometimes one ecosystem is slightly preferable, right? So if you, for example, belong to the people who small number of people who have been convinced that MLIR is great, but you didn't try it yet, you could in a couple of minutes try it with XDSL and then get a first impression and then move to MLIR. But the key idea really here was that building compiler sidekicks in general sounds maybe not the most clever idea because you just copy paste ideas from others, but kind of it's actually quite successful. And there are many use cases where like a different sidekick might be the right tool for you. Let me just go slightly faster to what I want to show you. Like, just if anyone kind of wants to understand, for example, how we implemented the stack language, it's actually relatively easy to define, for example, new operations or new types by just using a couple lines of Python code, right? So in practice, you would probably need to use one of our tutorials or have someone sit next to you. But the main thing is that within maybe an hour or something, you could start building your own abstractions versus like having to spend a day or a week kind of getting to know a relatively large, complex framework. You can also quite easily implement rewrites. And overall, what I found interesting is that obviously Python is slower, but actually not so much slower, right? And in fact, installing our framework, downloading it, or even recompiling a file is relatively competitive, if not even faster than a kind of a large-scale C++ code base. So now I made the case for XDSL. Let me show you what you can actually do with that. And that kind of relates because I think many of you build DSLs, build domain-specific concepts. So I want to give you like two examples. One example where we built something with XDSL, and one example where we went a little bit crazy and built yet another sidekick. So what we actually did then ended up doing with Imperial was we took DeVito, the Open Earth compiler, and Cyclone, which is a climate simulation, and which previously all of these were completely disjoint projects with their entirely disjoint individual compilation stacks, and we analyzed them and saw can we find synergies, right? So in particular, all of them were monolithic domain-specific languages. They were successful in their own community. They had delivered high performance. They were relatively productive to develop. They were portable. But they also had plenty of compiler optimization inside that were all independently developed and maintained, right? And so what we did is really like we merged all these projects together to make sure that they share a common set of abstractions. And then over time, we hope that there will be a lot of synergies from reusing shared concepts. All of that was done around actually using MLIR-style abstractions implemented in XDSL. So we have a stencil abstraction, we have a Fortran abstraction, we have GPU, MPI abstractions, even hardware synthesis abstractions, and a lot of other abstractions. And what's interesting is that it's really a kind of a relatively modular accessible compilation stack. All of this was built around XDSL, extending the general idea of what we had as a kind of a stencil dialect in the Open Earth compiler initially. Then we added, and I think what I'm particularly proud of, we actually built an entirely new MPI abstraction, which we meanwhile upstream to MLIR. So if any of you is interested in doing kind of large-scale HPC code generation, I can let you know that there's already an abstraction available now that you can use and that kind of translates to linkable code that you can run on an HPC cluster. And then we pretty much built the entire flow from our stencil abstraction to a distributed memory high-level abstraction to low-level MPI, right? And I guess that's one of the lessons across DSLs. MPI is such a general abstraction, so maybe it really makes sense to share these things. Performance-wise, I think we were quite happy with, like, we didn't fully match DeVito's performance yet, but our scaling behavior was very, very sensible. And in fact, for certain GPU kernels, our code was already faster, right? And this is pretty much, we're just at the beginning. We're just getting kind of these codes optimized. So hopefully there's more to be done. Same thing for Cyclone. Scaling here is not as good, but wasn't actually quite bad. And some of the performance numbers for these like weather codes actually improved quite a bit. So now, this was kind of an end-to-end project. Actually took like several years to kind of build this entire project. But we're now at a stage where we really believe like the V2 built on XDSL actually starts to be quite a sensible like end-to-end software product in a way. And now I wanted to show us like a kind of a slightly crazy sidekick that we built. And we called it Lean MLIR. So it's, previously I made the case that it makes sense to re-implement compiler frameworks again and again in different programming languages. So we kept doing that, and this time we chose Lean as an interactive theorem improver to provide a formally verified implementation of MLIR, right? And the very same benefits apply. You can copy paste your code, you can copy paste your IR, you can write transformations in one framework and then in the other. And so depending on your use case, right, if you care about productivity, maybe you want to use XDSL. If you care about correctness, maybe use Lean MLIR. But I guess I want to expand on the case, like building sidekicks, so building like kind of almost like an ecosystem of compilers really may make sense. And the main idea is that there's CompSet, which is a really impressive project, end-to-end certified, but also painful to develop, and in fact, really as a disjoint development, right? If you don't care about airplane security, you might not want to become a CompSet developer. That is maybe overly extreme, but roughly, they are very disjoint communities. But interestingly, in the LVM community, there was actually an incredibly successful formal methods project, which is called Alive. And this project is referenced weekly in the LVM commit logs, not because the LVM community cares about correctness, but because they care about, they are lazy. They want to save code reviewing time. And so it's really helpful to have an automatic tool that can assert correctness for certain people rewrites. And that's where like the LVM developers keep using Alive. I think they have over 800 commits which reference Alive. And so Alive is great, but it only works on bit vectors, and it's also not certified. And so our question is, can we use Alive or an Alive style workflow kind of to trick the LVM developers into starting to use formal methods at scale at even kind of more formal and maybe even larger level? And can we use that also to maybe reason about non-bit vector types? And the first problem we saw is that MLI obviously doesn't have formally defined semantics, but kind of semantics and documentation, code, comments, and conversations. And so we actually have two projects, one where we use an SMT solver purely, and one is our Lean MLI project where we kind of go for maximal expressivity, and that's pretty much how it looks like, right? So this is a slide where we need to go a little bit slow, but it's actually not very complicated. So if we want to prove correctness of that an at is the same as an XOR for a 1-bit type, in our framework, we pretty much just complete the MLIR code. And as you see, we have a full syntax embedding of MLIR and Lean. So you now have a definition of your source statement, your target statement, plus all the like semantic data structures that are related to the syntax. And then the only thing you need to prove is pretty much this proof. So we need to check that source and target have a refinement relationship. And our framework can pretty much simplify away all the like SSA properties, all these complexities, and just leaves you with a bit vector level proof obligation, right? And so this particular proof obligation, Lean can solve automatically. Slightly more complicated ones you might need to step in. But the key from that slide really is that, and I think that's something interesting. We moved this Alive, interesting. We moved this Alive framework pretty much a full interactive theorem improver, and now we connected the MLIR community with the interactive theorem improving community, and people can collaborate on these kind of proofs. We are working on making SMT level decision procedures automatic in Lean, and there are type definitions, and in particular, you can now start using that framework to verify lowerings or rewrites on an abstraction level. We did that for big vectors, for loops, and for fully homomorphic encryption. And that's the end of my talk. If you want to know more about XDSL, check it out. And thank you for all the other collaborators that worked with me on XDSL.
We have time for 1 or 2 questions in the meantime.
How much of my DSL compiler does XDSL want to eat? More or less, like one key thing that's always ambiguous to me when I see this is, okay, I see I can define an IR with this tool. I see there are mechanisms for defining transformations, but this MPI dialect kind of raises a question for me, which is, did it start out with this as something you defined within the project and then eventually push most of it into MLIR for various reasons? Or is it somewhere in between? And if I was defining something, would there be some point at which I would say, oh, I can no longer continue to do what I need to do if I express things in this framework? Like, where should I make that point of trade-off? Why did the MPI, Like, how much of it should it eat? Where should I be doing things in Python or in the framework or in MLIR?
Right. So I guess let me just briefly talk about like how does that work with I mean, MLI is so generic as a data structure that you pretty much can express anything in it. And I think you should, because the main benefit of MLI is not actually like beyond being the specific framework, and I think that's what the case I wanted to make with these sidekicks, is actually not even the framework, it's the fact that you pretty much completely eliminate the thing you have a project, I have a DSL project. If we want to connect our projects, the first thing is different programming language, different programming language, different implementation, data structures. Let me cut that. So the first thing is you have different programming language. No, that doesn't work. Let me do one after another. I mean, I'm clearly not. Hello? So I'm clearly not an expert of multitasking. But let me answer that briefly, and then we get the stage for our next speaker. So the main point is that it eliminates any kind of like engineering efforts you need to do to connect frameworks before you start discussing the actual abstractions. And if eliminating that is actually the one thing that you can like with automation, with tooling, really streamline. Discussions about abstractions, how much to share and all these things, I mean, that's what you need still to do. And I think our like Lean MLI framework is an example that, for example, if you want to formally verify your DSL compiler, if you implement it in Python and you have like a completely homegrown data structures, that's a major effort, right? You pretty much, the question is, what is the like main principles for these data structures? Lean MLI provides SSA and all these kind of formalizations for free for pretty much anyone of a developer. And again, having these kind of sidekicks where you just agree on the very basic data structure that you want, I think is what as a community can give us a lot of synergies. Thank you.
So now we go to the last talk of this session. So I want to also remind everybody that today we have also a welcome reception in the City Hall. I don't know whether you have received the email or not. We are going to start walking at 5:30 apparently from here towards the City Hall. So the last talk is on... I'll give another. Yeah, sure. Yeah. So the last talk is on compiling control flow in sparse and structured array programs by Willow.
Thank you. Yeah. So thanks for the introduction. I'm Willow. I'm part of Saman's group. We do compilers at MIT. So we'll start with a question. Do sparse array interfaces match the interfaces that we have in the dense world? Another way to think of this slide is like, how should we be programming with sparse arrays? If we can write all these compilers, what's the right interface to say what we want to do? So we, of course, have collectives, right? The NumPy style stuff. And we have ein sums. That's another way we can say how to compute with sparse arrays. We have scheduling, right? So we can use these kind of predefined transforms. Usually they're semantics preserving. That's great if they are. And then there's auto-scheduling or search things. We can do really fancy symbolic stuff, kind of like search for a better program automatically, give it a cost model, tell it what to optimize, right? In this talk, I will advocate that perhaps we should also be able to just directly tell the sparse compiler what to do without considering sparsity or structure, right? So we'll talk about structure as well. Here's my favorite little program. It's a snippet from the Fortran gem. So we start with a little example. It's not GEM, it's breadth first search, right? So this is a program that we should be able to express in a sparse compiler. But there's a couple reasons why breadth first search is a little tricky, right? We can't always just write an einsum that doesn't get us all the way to where we need to go with like what kind of optimizations we want to do. So the classic BFS, right? We have a frontier, we put our start node on the frontier, and then we iterate over the neighbors of the start node and add them to the next frontier, and we mark them as visited. So we can sort of, like the GraphBLAS folks have kind of convinced us to maybe write this in a different way, which kind of looks like this, where we've sort of, the main change here is that instead of using a stack for the frontier, we're sort of using a sparse array, right? And so now this sparse vector is sort of binary representing in sort of a one-hot way which elements are in the frontier. And most of the work is going on in this expression. So you can take a look. So we can say what kind of optimizations did we need to do to breadth first search? One thing we need to do is direction optimization. So if we're iterating over the adjacency matrix row major, we can't use the mask that we need on the output vector. So that's the not visited mask. So we could do column major, right? So this is like a a loop ordering problem. There's also masking. So we want to be able to fuse the iteration, right? So in addition to just the frontier, we also want to mask on the output. Different direction optimization will have different success with these plans. The other thing that we want to do is we want to early exit. So in the row major case, if each row represents a potential vertex to put on the queue, you can stop as long as you know that it's adjacent to something in the frontier. And so you need to be able to break out of the loop. A couple optimizations that are harder to represent pictorially here is you might want to only consider the structure of your matrix, right? It doesn't matter what the values are. It just matters that there's a non-zero there. And we also want to be able to fuse other calculations into this computation, like the calculation of parents. So I'm spoiling. I didn't expect Saman to be here, but he told me not to spoil. But I'm spoiling this is the code that we write in the compiler that I'm going to talk about, Finch. And so it has the features of what we would like to ask for out of BFS. So we can specify the loop order explicitly, right? We can add conditional masks depending on what kind of masking we need to do. We can mask off computation. We can use user-defined functions, of course. We can also put together multiple statements. So we can mask multiple statements and reuse that kind of control flow that way. We also have a little bit of short circuiting. We represent it a little different than a break, but we can short circuit. And we also have our structured operators, right? If we're going to scatter into the output, we should use a sparse byte map, this kind of thing. And we can achieve a performance that is pretty close to all of the optimizations that Tim Davis has done by hand in the GraphBLAS implementation of this algorithm. So why control flow? Like, why am I obsessed with this? I think that it's a good way to describe at a high level, in a succinct way, what we'd like our sparse computation to do without getting into the nitty-gritty of incrementing pointers over sparse arrays, because that kind of logic is going to be the same every time. So one example is consider the computation where we do only the even pairs in a dot product. You could represent this like this. You'd probably get, here's some pseudocode for what we'd be doing with a sparse array, right? You want to iterate over the intersection and then filter out all the elements in the intersection. Of course, this wouldn't be a very useful program if we did it verbatim the same way that it works in the dense world, where we iterate over every possible integer and then check the ones that are even and then randomly access the sparse array. So this is sort of the sparsified version of that code. You could also imagine a different strategy where instead we just filter the evens out of A beforehand and then use the evens later, right? And so that would give us an expression that looks a little bit more like this. And of course, you could imagine introducing a temporary, filter the evens from the temporary. All of these would probably be better or worse, depending on how many, how small the intersection is and how expensive filtering is. Here it's pretty cheap. So this, but I guess this leads us to a question of what kinds of control flow do we support, and then on what data structures do we support them? And so this is a hard problem. A lot of existing frameworks try to compromise by focusing on one part of this, right? Halide's popular. It supports many different programs, but only on dense data structures. Taco's a great project. It works on combinations of dense and sparse tensors. but it doesn't support as many programming constructs, right? It just supports the sort of einsum interface. There's also the Cora compiler. It only works on ragged arrays, but it does combinations of dense and ragged arrays, which are just arrays with different number of elements in every row. And it has a couple features that it supports. You can kind of cheat this if you limit the scope of the structure to one of the operands, and then use that operand to guide the program. So essentially just only allowing one argument to be sparse, you can get a wider variety of programming constructs. And so Tai-Chi is a much more flexible interface. And then, of course, we're talking about a compiler that can kind of do both. And this talk is a little bit about what it looks like to do both. So to give an overview of the framework, what we'll do is we'll describe this kind of simple loopy code. And then we have our description of formats. And we put it through a compiler that will reliably take advantage of all of the different structural attributes that you've described in your format description. So we'll talk a little bit about what I mean by structure, because I know I've been using this word, and it generally means beyond sparsity. But I think what I mean by that is that really there's a sort of simplified implementation, simplified representation that uses much less information, right? Sort of like a Kolmogorov complexity of the pattern is less, and we have a format that can kind of compress the pattern. So here's a bunch of examples of structure. We're kind of trying to generalize so that we can capture a little wider variety of these things. So we've seen sparse, but we also have run length encoding, or you might do a range query or something like that, right? In the case of a range query, we only need the height and the width of the box, and then what's the value inside the box. So we take pointers from prior work, right? I think we're convinced that we should describe the structure of tensors hierarchically, dimension by dimension. This works for matrices. This is CSR. It works for tensors. This is not quite CSF, but it's a fun little play on it, right? So maybe you have a dense innermost dimension, and here's our tensor. We also express the structure inside of each dimension hierarchically. So we're using a new intermediate representation called looplets. It allows us to recursively, hierarchically describe the structure of the dimension itself, which allows us to kind of generalize to all of these different kinds of structures at each level. This leads us to a question of which levels do we actually need? What kind of structures do we need at each level to be a sufficiently expressive language? So I'm going to propose a couple of properties that I think are worth taking advantage of. This list isn't necessarily complete. Maybe there are more. But maybe we can think of these a little bit more like axioms. So there's sparse, right? Is there a background value? Is it blocked? Is there more than one value, right? Is it sort of representing a range of coordinates or a single coordinate? Then we might ask, are all of those coordinates the same value, or are they different, right? So we have repeated. And then there's also a question of, is there just one structural feature that we're talking about, or is there more than one? And so we call this a singular property. And if we kind of consider all 16 intersections of whether it's possible to have one or more of these, not all of them are relevant, right? It doesn't make sense to block a repeated value because we don't know how long the repeats are. And so we still need to store the length of each repeat, and we don't get as much savings from storing the block. So this leads us to our 8 level formats. Some of these are more familiar than others, but this is sort of the level formats that we're providing the user, and we find that it expresses a pretty wide variety of structure in practice. Some of the new ones that I think are interesting is you have dense RLE. You might also have sparse RLE if you need to represent more of a mask with contiguous regions, and we find that sparse RLE is usually the more useful variant. You can also represent, say, our range query, right? If you only have a single run, we call that an interval. If you only have a single point, maybe you're doing a permutation matrix, we call that a pinpoint. And of course, if you only have a single block, we call that a band because it looks like a row of a banded matrix. So to give an example more of the program that it looks like to work with these formats, we'll start with a simple example of just statistics. Suppose we want to compute the sum and the variance, or I guess the mean and the standard deviation of every row of a sparse matrix. We could do it with a program that looks a little bit like this. We'll set up our structures on one side, right? And then we're going to read A once and reuse the value of A with our let statement. So this allows us to do one read, reuse the read, combine multiple updates, And this reads A only once, only accessing the non-zero values. There's a question about, in a program like this, how do all of those structures interact with their various usages as we move through the program? So to do this, we introduce a little bit of scoping, right? We say every statement has a corresponding scope, and loop bodies are going to introduce new scopes. So here, we have these dot equal, which specify tensor declarations. They set everything to 0, and they define the tensor in the scope. And so what we'll do is we'll restrict our structures to be in either a read-only mode or an update-only mode. And this allows us to kind of reinitialize them based on how they're going to be used. So we have a couple functions. There's the declare function. It sort of initializes the tensor to 0. You can freeze it to move from write to read, and you can thaw it to move from read to write. And this, if you can define these functions for all of your levels, then you're good. And we can insert these functions whenever a tensor transitions from being updated to being read from. Of course, this does mean that there's a restriction here, which is that we can't represent programs that recursively modify the same structure within the same loop. And that's kind of by design because the looplets framework doesn't handle that sort of thing. So if our underlying framework doesn't handle it, then it's kind of good that we scoped it out. So we'll go into a couple examples now of what it looks like to program with this kind of a system. So we might imagine 3 approaches to SPMV. There's the row major approach, the column major approach, and a symmetric approach. So in the symmetric approach, we read each value of A, and then we reuse it twice, one for each triangle. And then, of course, we've stored the diagonal separately, so we handle the diagonal at the end. Although you could use if statements to mask off the diagonal, and these have different performance characteristics. But symmetry is a property that is often introduced by the way we use tensor algebra, and so we're going to solve it with a program level solution to symmetry rather than in the tensor. And we can compare these different implementations of SPMV over many different formats. So this plot is describing which SPMV definition and which structure gave the best performance for these sweet sparse matrices. And we see that we actually get different formats perform better on different kinds of matrices, different column major, different column major or row major, right, might perform better. We see that blocked matrices do perform well on certain sweet sparse matrices, which is not a surprise given that some sweet sparse matrices are very blocked. And then we also see that for Boolean matrices, you should really use a Boolean representation, that sort of a structure-only representation, no values, right? We can also extend our definition of symmetry to multidimensional cases. So here's the symmetric MTT-KRP. This is a case where we have many different updates, right? So in this case, we would expect I believe it's, in the 3-dimensional case, it's a 2x speed up, and then we might get a 6x memory bandwidth speed up for reads of A. So here we've read A once, and we've reused it 3 times. We actually get a little register blocking too on B. And then we, of course, have a separate case for the edge, the tail conditions, right? And then the body of the work. So we've split it into 2, clean up the diagonals separately. And here we see that we're also able to do some efficient representations of equality. So for these cases, the Finch compiler can actually automatically insert a mask that can sort of wake you up when you hit I equal to k, rather than evaluating every coordinate repetitively. And we see, of course, that we get this n factorial speed up as we increase the number of dimensions, which I think is a sort of a good case that this works. Sometimes we do get a little bit super what we would expect. And I do suspect that this is related perhaps to register blocking and also some of the memory reuse. The last case I'll show is image morphology. So we can program, this kernel is erosion. So essentially what it is that if your pixel is on and all of your neighbors are on, you get to stay on, right? So this is essentially shrinking the size of the positive blobs in the image. And so for this case, we have a couple of things that are going on here. we're introducing padding, and that's what these coalesce operators are doing, is defining the off positive value, so the out of bounds value. We have these sort of like affine indexes that are occurring. And then, of course, we've unrolled the stencils. So we do left and right, and then we store that into a temporary, and then we reuse that temporary when we compute above and below. And so this is what we chose to measure. You can also imagine doing this on the bitwise variant. So you can change all the operators to work on the bitwise representation as well, and you could represent that like this. So this is the actual program that we are feeding to Finch to get these results. In the bitwise case, you might also want to include a mask in the event that like the entire integer that holds all the bits is 0. Then you can include a mask there, so that you can get an asymptotic performance improvement. And we measured on a couple data sets. The data sets that we chose were like data sets of digits. We have a database of sketches that were drawn by humans, and we have a database that we took from an image processing textbook. And so we see that we get some pretty like impressive speedups on erosion if we do 4 iterations compared to OpenCV. One thing that I thought was interesting here is that for some of these data sets, this run length encoding representation is actually the run length encoding representation actually does like much better than even the bit packed variant. So it's really data set dependent, right? You do need a compressible image, but if your image is compressible, you can use this sort of sparse RLE format, and you can get a good speed up by restricting computation to the boundaries. So that's all I have for the main talk. In conclusion, I think that we should really make high performance computing easier by being able to say what we want, and then have the compiler follow that high level sketch. There's several papers that contributed to the work in this talk. One of which is a student of mine, Radha Patel, worked a little bit on making a compiler that automates the symmetric transformation I was talking about. You can install Finch. It's a Julia package, so you can install it in Julia. You can install it in Python. We have a Python interface. And I'd also like to make 2 talk advertisements. Jayon will be speaking later this afternoon about extending Finch to continuous indices, to real valued indices. Also, there is a talk on Thursday by Vladimir about formalizing sparse computations, which I think everybody in this audience would probably be interested in. It's in the formalization section, so I felt I should shout it out. All right. Thanks, everybody, for your time.
We have time for one question. Yeah.
If somebody else has a more pressing question, I'm happy to defer. But okay. With the sweet sparse results, was RLE helpful on any of those?
Sweet sparse where?
I think you had a bunch.
SPMV, yes. Yeah. RLE was not as helpful here.
Okay.
And I think that's partially because the values were different very often, right? Oftentimes it's like they're not, you're not getting like the same value over and over again. Like that really only shows up in cases where that's sort of from the problem introduced as like a constraint or a computer generated image or one of those sorts of things, yeah. But we do see that the blocked representation does help sometimes.
Okay.
Cool, thank you.
Thank Milo again. So now we have the panel session. So unfortunately, Max couldn't attend the panel because he's giving another talk in another session. But are there any questions from the audience for the panel members to initiate the discussion? Yes.
Maybe a really specific question for Tobias, but I've talked about with John a few times about how in Alive 2 they have lots of these bit vector, exactly as you say, problems, and they want to kind of formally prove them, but they only look at like specific bit vector 16, 12, 14, right? And we always want to be, can we prove them for all bit vectors? Do you think your lean interface will provide us a mechanism to say, not just for all x, y of type bit vector 1, but of type bit vector n?
Yes, I'm convinced our lean already supports to quantify over the bit width in the statements. The moment you quantify over the bit width in your statement, I mean, it's a hard proof. It becomes hard. There's no decision procedure to solve that for you, right? So what we are working with the Lean community, actually, they're heavily, the Lean FO is now heavily investing in the like bit vector level decision procedures. So Lean will have actually quite high performance automation for bit vector level reasoning up to a fixed bit width. And then there's just a large math library with a couple of like decision procedures for subsets of big vector theories that can handle the arbitrary grades. And what actually is quite interesting, so we looked at a couple of proofs, and if you want to prove like theorems over arbitrary bit width that are not trivial, sometimes you find this interesting pattern that if you need to case analyze in your proof. And several of these cases are actually then very quickly becoming fixed bit width. So you have this interesting case where then a subset of your proof can just be dispatched to your automatic decision procedure for big fixed bit width, and then you just pretty much need to cover the general case either by yourself or using Omega or whatever.
So for the second and last talk, so specifically related to control flow, I'm curious how you would handle propagating traits across complex control flow structures, and specifically also interprocedural analysis. So for the second talk, it's about how do you detect patterns if it's scattered across multiple different functions. And for the last talk, so it's 8, 9 different shapes and properties, how do you propagate the knowledge that a certain intermediate has those shapes through complex control flow, and do you make actually already use of it?
I think in my case, the answer is simple. We don't propagate it. You have to say what kind of structure you would like to use to store each intermediate. I think part of the reason it's hard to propagate is that you don't know how the runtime values might interact to produce something which has structure or to produce something which doesn't. One challenge that I found when trying to wrap this up in a higher level API is that you sort of ask a really simple question, like which format should I use for the transpose of a sparse matrix? And it's like, I don't actually know in certain cases whether it makes sense to store the bottom level sparse or the bottom level dense or the top level, because it does actually depend on how those non-zeros interact and how they're clustered together. So we can make safe decisions. Yeah.
For the question about interprocedural analysis, basically right now we don't support jumping into some user functions unless it's been inlined. So the easy hack is just to make sure it's inlined, and then that's fine. But in terms of looking for formats specifically, most of the time they are specified by some include some header somewhere which will be already pulled in. So vast majority of the time when you're looking at the LLVM IR level, you don't need to do anything extra to have full knowledge of the data structures that you're accessing. But it does quickly become complicated when you have multiple storage formats in the same kernel, especially if you are writing to a sparse storage as output. And the way that we handle that right now is we have a greedy work list kind of algorithm to start with the what looks like the leaves of pointers in that graph that I showed. And every time we detect one, we kind of pop it off the work list until we reach a fixed point. And that works for all of the benchmarks right now, but it's not really a solution that can handle all possible cases because it's just too complicated. Yeah.
So I have a couple questions that are very specific, so maybe we can take it offline later. But one question I had for Avery, which is the work that I presented on in an earlier session, Mosaic, is very similar to spec, but instead of a bottom-up fashion, it's top-down, and instead of LLVM-IR, it's within like tensor index notation. So my question is basically, when we did this, we had this verified mechanism for the schedules and for deducting patterns, but oftentimes your function call backend needs arguments that your code doesn't necessarily provide. So for example, in a CSR matrix, you're not guaranteed to have the dense dimension anywhere because you don't actually need it in the loop nest calculation. So then how do you actually end up emitting the backend code properly? Because it seems like a final step, and that step seems to not be verified.
Yeah, good question. There are two scenarios. So first scenario is a lot of the time user code omits very common parameters like alpha and beta. And so the way we handle that is we have some kind of weird rewrite rules where we like inject back in facts. So like if you have, A, like AI, you're accessing, matrix A at position I, that's equivalent to AI times 1. And you can always put in any free variable name as long as you multiply it by 0. So we actually we do a few rounds of those rules where we like inject back in that kind of information so that we can detect those really common values of alpha and beta. So like in the example I showed, there was no alpha and beta specified. We just extract them through the quality saturation process. For the second part of the question, which was about for example with CSR extracting back out one of the missing dimensions, that's folded into the precondition check, because in the precondition check we're iterating over the row pointer and the call pointer, again for this CSR example. And so you can imagine the case where you just look to see how many columns there are in the sparse matrix, and any extra columns would have just been all zeros. So it doesn't really matter about those anyway. It doesn't change the semantics to just find the max number of columns and say that is your dimension. Yeah.
So I have one question for you, which is kind of connected to the presentation that Max had. So Max basically said that for the equality saturation technique, basically in principle what it does is that it allows you to do a search over basically the space of semantically equivalent programs. And then he said that, okay, there was a combination of that with this data log ideas, and they introduced egglog. You said that you have used egglog. What is it with egglog that you have used that you couldn't use just pure egg?
So I started off with egg, and then there was something I needed and I can't remember what it is. I think with the current version of how things work, I think I could make it work with egg, but the main reason I switched is because egglog is a lot faster and has a bit more of like a fluent Python API. It seemed to be the way things were going from their research, and it was the only one that was like most actively maintained. So egg was like no longer actively maintained, egglog was. So I thought, okay, this is a better choice.
Okay.
Yeah.
Yes.
So this is the compiler framework session, so I'll ask a question about frameworks. In research, you have this choice. You can hack up prototypes and you can explore ideas really quick, but you do it at a low level of resolution. Or you can build big frameworks, and the benefit of that is that you can have a lot of impact that way, and maybe you can explore ideas in more resolution, but then you go slower, so you can't explore as many ideas. What's your thoughts on these options?
I'll let someone else go first this time.
You can go. Can you repeat your question again?
Oh, maybe it wasn't. So you can, when you do research, especially in academia, but also in industry labs, you get this choice. You can hack up prototypes, and explore your ideas to a low level of resolution. And you can move really quick, so you can explore many ideas, and you can go quicker that way. Or you can build big frameworks. Maybe you can open source them. Maybe you can make them a little bit more industry strength. You get to explore your ideas to higher levels of resolution, but maybe you can't explore as many ideas because you spend more time coding. So what's your thoughts on the trade-off?
So maybe I would actually slightly rephrase that, right? So it depends a little bit like if there are pre-existing large frameworks available, right? I think it's definitely like if you work with large frameworks, there's a like learning curve. You need to get up to speed with that framework that takes quite a while. I would actually challenge the statement that if you work in a large framework and that this somehow slows down your research. But it's a very specific skill set to develop, right? If you try to solve like any of the frameworks presented here, I mean, if you hack them up quickly to get a quick result, I mean, I think you will be heavily burned, and it's just it doesn't work. You can't hack up complicated research in many cases quickly. And I think so sometimes it really pays off in kind of learning the skills to navigate a large ecosystem and use the appropriate tools well. It takes a lot of time or like at least take some training to learn these skills. But afterwards, I think you actually kind of almost become a wizard in combining like highly complicated systems in very novel ways, which I believe actually can be sometimes quite fast. Obviously, like some of the research I present actually builds up a lot of tools itself, which I guess can't be necessarily fast, but that is a very deliberate strategic decision to kind of, for example, connecting MLI and Lean. I mean, that's a lot of like, we did a lot of non-research bit vector stuff, which really is not research, but it connects ecosystem where I think in a couple of months, we'll see again this kind of catalyst of high performance research or quick research if the framework is built sensibly. Not sure.
I love rewriting systems. I think that everybody should rewrite systems all the time and frequently. But I feel like
nice. Don't give Simon an
No, I mean, I really like, I'm stubborn, and there's a lot of things that I would not have learned if I didn't rewrite systems, and that I appreciate more now that I have, and that, you know, it may be that there are like certain ways and results are presented that kind of gloss over some interesting thing that you wouldn't have known if you didn't like build it up. It also, like when you work in an established system, it constrains you to the decisions that were made at that time, right? And so you can't, you know, you're locked into certain, you know, assumptions and like things that are built into the system, and you can't get around them. So I think that's like the challenge. I will say though that like trying to productionize systems or working in larger frameworks also like, of course, leads to new questions, right? I would not have asked myself how to transpose a sparse tensor and then pick the format of the output unless somebody was saying, oh, you really have to, you know, make this new interface for it or something like that, right? So that the users will be happy, or so that, you know, it'll integrate with this existing framework or something like that. So.
But the thing is, when the framework collect lot of capabilities, it gets harder and harder to do this rewrite part in there, because you at the beginning of research, expectations are very low. You get some very simple thing working and you're very happy, you can publish web, and as time progresses, you have to build much more thing, and at that time it gets harder and harder to do that. So, but the thing about research is you don't know what you're doing when you start, so you will always end up with some new thing that you somehow or other kind of fit into the, like, put a square peg through a round hole, and when you do few of those, your framework is pretty much dead.
I like to think that we will rewrite these things over and over again until they're perfect, but I don't I don't know if that's true.
Yeah. And just to clarify, you were not referring to rewrite systems. Term rewrite
Those
systems.
are great too.
Yeah.
Can we just automate that process?
Yeah. Yeah. So do you have any comments on that?
Yeah, I agree with everything that's been said. Personally, I don't have the skill of being able to anticipate every possible thing and plan everything out and then execute it perfectly. I know a few like one or two people who can do that, and I wish that I could, but I just can't. So for me, the only solution is to very quickly experiment with a bunch of different things and then decide the path forward and go backwards, and maybe do that several times. And I do think there are also benefits to that approach, even though on the surface it may seem like you're wasting time. Like I think a really good example of this is the CVC solver. They, every couple of years rewrite the entire solver bottom up, because they just decide, okay, we learned lessons from the last time we did it, and let's just start fresh, let's start all over again. And every single time they do that, they always beat what they did last time. So I think, it can be really beneficial.
Yeah. So if there are no more questions, I want to ask actually one question, which you can combine also with the closing statements. If you were to rebuild the system that you built, how would you have done it differently this time?
I'm re-implementing it in MLIR, which I should have done from the beginning. Because what I didn't show here, but you can watch. I did a talk at the egress workshop yesterday that you can look on YouTube, and I explained it in detail. But basically, translating the LLVM IR into an egraph term is not straightforward, especially because of how memory is modeled in LLVM. And so it takes a lot of effort. It's not the LLVM infrastructure itself is not really designed to handle that. So I should have written it as a dialect in MLIR. It would have been much easier, and that's what I'm doing now. Yeah.
And just to clarify, you mean that using the dialect of MLIR, you don't necessarily mean that
creating a new dialect in MLIR that has a one-to-one translation to an egraph term.
Yeah. Okay. Thanks. Tobias?
Yeah, I'm not sure. Actually, I'm quite happy with the projects we have. I mean, our Lean MLIR stuff, I think, took way longer than I thought. I mean, I need to learn more about interactive theorem proofers and more of the theory. And in particular, I think what in general for some of the projects I think is really important is to get the kind of like the team right. It's you need expertise from many different areas to get really like many design decisions right, and it's just like an endless lesson that I keep relearning and relearning. There's so much knowledge in our community, and typically like a year after you develop your framework, you talk with the person and said, yeah, they knew what I should have done.
I've been thinking a lot about what I would put in a rewrite of my system, but I think the main thing is that, like you were saying, rewriting is good. It's almost purely syntactic. I think that leaning into that would have made things a little simpler.
Okay. Let's thank the panel members again. So the last session starts in 20 minutes? Yeah. Yeah. So see you soon.
and get started with this last session. We've had a number of interesting sessions today, except maybe that first one with those people bloviating or whatever. We've heard all these great things about how to build sparse systems, compilers, connections to databases. But all of this would be pointless if we didn't have any applications. So our last session here is hopefully a little bit more application focused. Why is sparsity coming up for people, and what can we do about that? And so to start us off, Luo Mai will be talking about efficient sparsity in AI.
Yeah, so thank you for the introduction. So today today actually it's my honor to present here about our recent work to build system to achieve offloading efficient sparse AI model serving. This is a joint work with my students, Le Yang, Yao, and Jai. So yeah, so in the last 10 years, right, we have been observing like the booming size of the AI models, right? So actually in the same time frame, the speed of the processor only increased by two times, so every 18 months, where in the same time frame, the size of the model increased by 35 times, right? So even though we could use like maybe distributed computing to really close the gap, right? But where we are really using 10,000 GPU to train the model, the communication overhead actually becomes dominating, right? This actually has to motivate the AI practitioners to look for new approaches that can really close the gap. Now, actually, the answer is called the sparsity. Actually, different from the sparsity in the conventional, so in the matrix sense, right? Sparse actually in the AI model usually means that you will selectively activate the partial parameters based on the inputs and the context here. And a very popular architecture to implement the sparse AI is called the mixture of experts. The first open source MOE model here actually comes from Google, and later OpenAI, and then later OpenAI actually get the entire team of MOE from Google to OpenAI, right? They secretly built the GPT-4. At the same time, Meta, they are also trying to use MOE to do machine translation. And actually, in this year, there are more than 10 open source MOE models coming out in the first half of 2024. So there are like many big companies like the Snowflake, Databricks, right? They are all trying to train their own MOE model. But what really makes the MOE model look like here is, so this is like a super simple example, right? So an MOE model, you have like a multiple layers here, and in each layer you have like a multiple experts here, and each expert is a neural network. And every time you are given like a one input token to the router, the router is also a neural network. The router will learn how to route the tokens to different experts for processing, right? And usually you are training the MOE model. So basically that actually means that you are training the parameters of the router as well as the experts, and ultimately you want to make sure all the experts, they have the complementary capabilities in processing different kinds of the data, so that they can make the promise that they can reduce the computation load given like a certain amount of the input data. So even though, so here actually, if we want to deploy the MOE model for the large language model case, right, usually we have some input prompts like this, like how are, and every time we will fill the tokens into the model, and then the token will passing through the model using different paths here. And if we give like the other prompt, right, so usually it can trigger another path for the activation, right? So, but in the reality, the MOE model will be much bigger than the one I show here. Usually, like an expert size will be around 10 to 100 times the megabyte, and every layer you can have like up to hundreds of experts per layer, and you could have like hundreds of layers. And that actually means like a huge memory cost for the MOE model. So taking the Google Transformer as an example, depending on its configuration, it can consume up to 1 terabyte memory. And we also see similar results in other models. Right. So right now, actually, MOE model is really achieving the sort of performance in many applications. This actually makes many organizations, they really want to trying to deploy the MOE model to serve for their customers. But because of the very high memory cost, right, so the default solution, like the NVIDIA, they really want to convince you that you want to deploy the full model into the GPUs. But if you are using like a quite standard MOE model, this actually will require 2 H100 server costing you around $1 million or roughly $100 per hour. This actually means that this cost can be only afforded by some very big organization. On the other hand, now the news they also report that here we have someone called the GPU poor. So they can only buy some consumer grade GPU like the 1490. 1490 actually provide very good compute performance at the H100, but they only have around 20% of the GPU memory here, right? To really fit the model inside it, you can use the quantization, but actually for any quantization actually below the precision like the INT8 or the FP8, it really hurt the model quality. So basically now, for many of these GPU poor people, they are looking for some solution that can balance the good quality of the model and also the affordability. And usually they will try to come to memory offloading. So in the context of the MOE, right, one of the key properties for MOE is that almost up to 99% of the parameter come from the experts, right? This actually motivates the people. They will try to keep all the parameter of the router and also the attention within the GPU memory. They will keep all the experts in the host memory. And while we are doing the inference, we will dynamically prefetching and caching the experts in the GPU buffer here so that we can and we hope to maximize the efficiency of fetching data over the PCIe. And now there are like 2 common approaches in the system community. One is that we are using CUDA unified memory. Now the SOTA is called the DeepUM. But unfortunately, the prefetching and the caching engine, they are not really aware of the size of the experts and also the pattern, how they access the memory. This usually means like the massive page fault and also OS cache miss. So this also motivate more machine learning specific offloading system, like the current SOTA is called the Brimstone. But actually, Brimstone is designed for the dense neural network, like the dense large language model. They are not really aware of the sparse activation among the experts, and as the result, because they cannot predict which experts will be activated, they will have to prefetch all the experts and caching all the experts in the GPU memory. Still suffer from a very high performance overhead. Actually today, right, offloading usually means very slow. But actually, what can make the sparse MOE like a big opportunity to make the offloading efficient here? Here, I am doing some real-world data benchmark. So here we are tackling the Google Transformer. We are only selecting the first 3 layers, and then we are actually measuring for each expert how many tokens it flows through. Here we only show the top heater experts that can covering over 90% of the token traffic per layer. As you can see here, even though each layer can have up to 128 experts, only 4, 5 to 6 experts actually are the heavy hitter, right? But why actually is happening that, right? Because actually we found out that in the serving scenario, usually the data actually are not as diverse as the training situation, because in the training, situation for the MOE, you want the MOE to see as much as possible of the data in the real world. But in the serving scenario, you usually target like a certain circumstances, right? This actually means that, so in your brain, only partial results or partial knowledge will be required for some scenario. Actually, we see this also in the MOE, right? But if we can see it here, right, so you have like a very low activation ratio, while some of the experts are heavily reused in processing the request. Actually, this will mean something for the system researcher, which means that by using this property, we can have potentially has very low GPU and host traffic, while at the same time, we can have a very space efficient cache to make it work. Another pattern we also observe is that usually experts, they want to collaborate with each other, which means that if you know that this expert will be activated, and very likely it will trigger these two experts in the second layer, and also this one in the third layer, right? This actually can form some group of the activation. By observing this group activation, this can allow us to do very efficient cross-layer prefetching, where you observe this expert to be activated, you can already prefetching these experts, right, through overlap prefetching and the inference. So, but how generic is this observation, right? We then extend the measurement to many open source MOE model. As you can see here, so even though we serve the MOE model for almost 300 LN tasks, right, from 3 big data sets, we increase the batch size from 1 to 32, you will see that even though with like a very big batch size, trying keep activating different experts at the same time, less than 20% of the parameters actually are being activated. So Mix shows this model actually is the worst case for us because it only has 8 experts per layer, and every time you need to activate the top 2 experts, right? Even in such like a super dense, this very dense MOE model, you can still observe the selective activation pattern, right? Which means that actually, but the good news here is that, so today the entire industry, they are moving towards to build like a wider MOE layer, not the fewer. Right? This actually means in the future, this observation can actually sustain in the future. So, but actually this sounds very promising, right? But what really makes this challenging for the system people to leverage this opportunity, right? And our key insight here is that we found out that the sparse activation, they usually only emerge at a request level. And for many systems, right, we are keeping the tracing or the counting through the entire lifetime of the system. And this actually would mean that the sparse activation pattern will disappear. So we show this by using the tool model here, right? If we are only measuring one request, and you can see that the expert 2 will be heavily reused, right? So actually for the request 2, right, the expert 0 will be heavily reused. But if we merge all the trace for over 1,000 requests, all the experts, they become a uniform, right? That is because the data, they are different. They are triggered different experts in the graph, right? So if you let the trace to count all the experts through a lot of different data, the pattern disappear, right? And the same pattern can be also see the meta NLP model, right? For a single model, it's quite sparse, but over 1,000 requests, it actually becomes uniform, right? This actually motivates us to design a system that's called MOE Infinity. Here, it has like 2 key new features. One is that we implement the request level expert activation tracing so that we can really recover the fine-grained sparse activation pattern, right, at the request level, but we still keep the cost to keep all the possible requests this pattern low. Okay, and based on the trace, we use the trace to guide the prefetching and the caching to implement what I just presented to you several slides earlier. And if we can combine the new tracing and also the prefetching and the caching, we can get quite impressive result here. So here we consider like a simple example. like we are serving the meta NLP model on like a GPU, and actually the A5000 GPU is the consumer grade GPU. It costs only like 1/10 compared to the H100. So, but it provides almost 80% of the compute power, but only 20% of the GPU memory. But we enable this memory limited GPU server to really serve a very big model. And here we are measuring the latency, and also we compare it to the RPS, right? So here, this is a solution we call the GPU rich. So this actually means that you have super affluent GPU. You don't want to turn on the offloading. This can be the best case for us, right? As we can see here, so we can actually reach the same latency performance. And actually, in almost 90% of the RPS, actually our performance actually perform worse than the GPU-rich solution. But on the other hand, we are only consuming 4 times less GPU resources. And compared to other SOTA systems like those from the Microsoft and also Google, right? So they turn on offloading, but usually that means that their latency will drop to even 10 seconds per second, right? So this actually shows that by understanding the MOE pattern, we can largely improve the offloading efficiency. So in this talk, I hope I can convince you that MOE model actually offer huge opportunity for system design. For example, they have the selective activation, skill reduced pattern, and also the group activation to facilitate prediction. But the challenge here is that many of these opportunities, they only emerge at the request level. This actually requires new system design to do tracing, prefetching, caching, and parallelism. And our initial result actually is quite encouraging. Yeah, thank you.
Do we have any questions? Sorry. Need to be more on top of this. Do we have any questions? So maybe to get us started, should I think about the MOE as a meta model over transformers, or is this an alternative to transformers?
So basically, they are a combination. So you can imagine that for the MOE model is one way you can add a sparsity structure over the transformer. So for example, transformer, they can work within the expert level or at the router level. So actually, you are combining them together.
Got it.
Yeah.
Thank you.
Yeah.
We got a question from Teo.
Just to further clarify what Gilbert said, I could use something else as like each expert as opposed instead of a transformer.
Yeah.
Cool. Can we go ahead and get the next speaker coming up?
Yeah.
Do we have any other questions while we're transitioning? Okay, we have one from Schwabe.
So I think you said that there's little benefit in training. Is it the case that you want all of the experts to see all of the data? Or do you usually, for example, if I have an expert that's, I don't know, in English to Spanish translation, maybe I would only want to give it a subset of data.
Yeah. So usually for the training, you will have like a super big batch, which means that so every iteration you are feeding around 1 million tokens through the model. This actually would mean all the experts will be activated. But actually, for the serving case, you won't have such a big batch, right? You usually have like 1 to up to 32, which means that like maybe hundreds of tokens. In such a case, just a few experts will be activated.
Awesome, thank you.
Cool. So, getting fitted up here.
Okay.
Okay. So Jayon will tell us about how we should stop thinking so digitally and smooth everything out. My apologies if that's a terrible intro, but I'm really looking forward to this talk, so please take it away.
Hi, I'm Jayon from MIT, and I'm currently 4th-year PhD student and advised by Saman and Joel Emmer. I'll talk about our recent work in progress, the continuous tensor abstraction, which is a collaboration with Willow, Joel, and Saman. In the real world, many applications works on the continuous domain, like functions in numerical computing, managing spatial databases, 3D point clouds, and computer graphics. However, as you might know, manipulating such data has non-trivial challenges. For example, in spatial databases, the challenge lies in storing these geometries. It often requires very complex data structures such as quadtrees. For example, in a famous handwritten C++ library called GEOS, it takes approximately 500 lines of code to execute a 2D range search query over geometries. And here's another example with 3D deep learning on point clouds. In a well-known method for 3D point cloud called kpconv, the main idea is really, really simple. However, turning that idea into an actually efficient program takes a large amount of code, like around 2,000 lines of PyTorch. And many computations on discrete integer grid can easily fit in this way of thinking, like matrix vector multiply. But this is not sufficient for continuous domains. So in this talk, I want to share about the continuous tensor idea, which gives us a fun way to program with loops and tensors. So compared to integer index access like a bracket 2 or discrete loop iteration, our new idea suggests accessing tensor using real number index like a bracket 3.1415 and using continuous for loop that can keep going through an infinitely large range of real numbers. So to show you what this abstraction would look like, I've set up a very simple comparison using the dot product as an example. In regular programming languages, here's how you would write the code to perform the dot product between two vectors. And the most natural extension of dot product into the real domain is using now real number coordinates as shown in the blue and the red dots for the vector x and vector y. Now what we are suggesting is users will write the exactly same code as they would do for the regular dot product, but with a change in the semantics of the for loops. So the for loop now, you can imagine this iterates continuously. So imagine you iterate this domain very smoothly and perform multiply and accumulate for every single point. You would realize the effective multiplications between non-zeros only occur at 3.0 and 5.1. So this code will result in variable s being 44. And another example I like to share is how a vector, continuous vector, can have a data spread out continuously, as shown in the bottom left figure. Now we refer such coordinates as interval coordinates, and we call particular point coordinates in the middle example as pinpoint coordinates. So one thing very important to note here is that we rely on the assumption that all the tensors, continuous tensors, should be piecewise constant at this moment. So that being said, the tensor should only have finite number of non-zeros pieces, where each piece is a n-dimensional axis-aligned bounding boxes with a constant value. So as an example, interval coordinates in the bottom left figure can only have a constant value, but not arbitrarily truly continuous functions over those regions. So each coordinate spans on the continuous domain, but the value is actually constant. We can still demonstrate, we can express a lot of fun and various applications, even with this piecewise constant restrictions in the evaluation. And now here's the challenging part. Because the data is spread out very continuously within the interval coordinates, if you naively iterate over all the index I and perform dot products, what we will end up is infinity, as there are infinitely many non-zero points between 2.2 and 3 because non-zero points. There are a lot of non-zero points. So as you could see, the one challenge is considering a reduction on a continuous domain. So we need to be clear what is the semantic of repeating this s plus equal yi addition infinitely many times. So first of all, we introduced two types of reductions on plus equal operator, a summation mode and integral mode. And here I prepared two different continuous vectors, one with only pinpoint coordinates and another with interval coordinates. And summation mode shares a very similar semantic of our traditional tensor programming models. It just aggregates value from each pinpoint, so the result will be 5 plus 6 plus 7. On the other hand, integral mode operation operates on an aggregation with an integral. So from syntactical perspective, we distinguish these two modes in the presence of di in the expression. And in integral mode, this variable s will be 1.8 because the length of the interval is 0.6. And if we do integral reductions on the pinpoints, it'll be 0 because pinpoints inherently are interval with a length of 0. And for interval coordinates, the variable s will end up being infinity because there are infinitely many points in the intervals. And to demonstrate how easy and straightforward, let's consider another example, a radius search query in Google Maps. So imagine you want to count the number of predefined points within a circle of radius r. In the continuous tensor approach, here's how you can write the radius search query. So on the right, I prepare 2D continuous matrix A with a value of 1 at 6 different blue pinpoint coordinates, and rest of them are 0. And you want to write a continuous for loops that outputs the count to be 3 because basically which is the number of blue points within the circle. And here's the code you want. Note that all the for loops in line 2 and 3 are continuous. So in line 2 to the 4, you'll continuously iterate through the red circle with an extra distance checking on the line 4 to keep in the circle. After that, in line 5, you will access tensor A with 2.2 plus dx and 3.9 plus dy, where 2.2 and 3.9 is basically the origin of the circle. So this code will add up all the points within this red circles, and which will end up being the count to be 3. So we built a compiler for this continuous loop using Finch. I won't go detail of compiler implementation in this talk, but as Willow suggested, Finch was originally designed for integer domain, but we extended for the continuous domain by adding some more cool rewriting rules. And our compiler needs basically two things: a code with continuous loops and the descriptions of how the continuous tensor are actually stored in the memory. And the compiler then gives you the code that can actually be run on the hardware. So we demonstrated the effectiveness of these abstractions across 4 different very non-traditional areas that people would have not thought about in tensor programming models. In the red box, saving in the lines of code shows the simplicity in expressing these non-traditional applications through our approach. And on the green box, our generic code also showed the very decent performance compared to the manually written library codes. So among this example, I'll show how trilinear interpolations along the ray sampling would work with this abstraction. To start, imagine a sparse grid that shows a gold key with a rainbow in it. And note that I've illustrated this figure in 2D continuous space for clarity, but the actual implementation occurs in the 3D space. So in the initial phase, we shoot the ray and uniformly sample the points along the ray. So this step is written in lines 1 to 4 in the code below. The for loop in the line 1 is basically represents a discrete iteration over the time, identical what you find in the traditional loop programming model. So nothing special until now. And every sample point x for x, y, z, what we're going to do is we apply trilinear interpolation on the nearby grids. So, and this process can be expressed through an integral reductions on the continuous loops in line 5 to 9 in a 3D space. And you can see this program is very clearly expressed in just 9 lines of code, whereas the reference PyTorch implementation takes like 80 lines of code. And also, on the single-threaded CPU, our generated code performs better than the PyTorch implementation. And now I'd like to talk about what we can do with these things, even with the restrictions of piecewise constant assumption. And there are a lot of applications that treats geometries. So not only spatial join in the spatial databases, there are rasterization and ray tracing, et cetera, but also, I mean, there are also a lot of kernels out there in 3D deep learnings as well. And programmers need to think about how to efficiently store these geometries and efficiently store geometries and efficiently process these geometries in various domains. And people in this workshop may know that there are tons of formats to store sparse matrix and sparse tensor that are published for decades. Similarly, there are also a lot of spatial data structures out there through a long history to store this geometry, such as KD trees or bounding volume hierarchy. We believe that this continuous n-dimensional tensor may describe many of them, as they can be viewed as nested bounding boxes. Also, similar to the motivation that Fred had in the Taco compiler, there can be a lot of combinations of choosing appropriate spatial data structures and the algorithms, so which is nearly impossible to handwrite all the cases. So the question is, like, can we bring these spatial data structures and algorithms into a very single, unified tensor domain if we have this kind of extension to the continuous domain? And lastly, many recent deep learning compilers are targeting MapMul accelerators like tensor cores, NVIDIA's tensor core, by doing a pattern matching on a for loop level. And you may have heard of it. There's another cool accelerator called RT core in NVIDIA GPU to optimize programs using bounding volume hierarchy. So similar to the tensor core, it might also be very interesting opportunity if we can describe the behavior of RT core with continuous for loops and offload the computations to the RT core by doing a pattern matching. I think this is all.
Do we have any questions? Awesome. Okay.
Great talk, Jaeyoon. I had a question on your performance numbers. It looked like there were speedups on all of the code except for one of the convolutions. Could you explain?
Oh, this.
Because of the 5x slowdown.
So the point cloud convolution involves not only like geometry processing, but also very heavily tensor computation, the traditional tensor computation. So the Finch cannot generate very high performance dense computation. So that's the reason we weren't that perform.
Really cool talk. Love the idea. I think I have a good understanding of how the pointwise code generation might go through, but I'm having a harder time with the interval, like the integral semantics version of this. I'm wondering if you can clarify that. My gut is telling me that you need to generate some sort of quadrature code, but I don't know how that goes through in Finch.
I don't know if you are familiar with the like two-finger merge intersection.
I'm afraid not, no.
So it's, I'll first do an example on the pinpoint coordinates. So basically, when you try to do an intersection between these two pinpoint coordinates, you have two fingers for each vector. And if you know, if one finger is ahead of the left finger, if the left finger is, anyway, I mean, it's basically sorted merge in the databases.
Yeah.
And we can apply a very similar techniques to the intervals.
Okay.
So, and Finch can automatically generate such codes.
Interesting. Okay, I have to look more into that. Super cool. And then a follow-up on that is, have you thought about different indexing strategies where there's like an I-1 in the setup? At least superficially, that would look like traditional explicit ODE solvers. I'm wondering if you've thought about that at all. I think the semantics might be different underlying this, but at least superficially.
It works, and as you said, that's traditional ODE setup, and it works in our compiler as well. But there is some restriction that sometimes, basically what you're saying is, can we do affine index expression But imagine if you do our convolutions on the continuous space, it'll end up in a like piecewise linear, the output. In such case, we can't generate such code because we rely on the piecewise constants. But if we do a convolution code with affine index expressions on the pinpoint coordinates, then it's fine because that will not produce the piecewise linear one.
Yeah, thank you.
Yeah.
Thanks for the great talk. So I have two questions. The first question is that isn't pinpoint computations actually ended up being something similar to what you would do with sparse tensors? Yeah. The second question, especially on the interval part, can you compare it with the work that the spatial databases have been doing? Can you position it somehow?
I think that's a good question.
So perhaps let me give you an answer. Correct me if I'm wrong. Yeah. Can you go back to the Cartesian product slide that it was using the... Yeah. So am I right that you're basically defining a way to generate efficient implementations for each of the physical operators in a spatial database? Am I right?
Yeah.
Yeah. So there is a line of work also in databases which is actually related to code generation, combining code generation with databases, which basically uses multi-stage programming to basically generate efficient implementation of I don't know how many of the spatial join operators, but spatial operators, but it's trying to do that. So I think it would be nice to also kind of position.
But, as far as I know, all of those spatial data databases actually use those spatial data structures and can actually code generate for some special cases. But they use but they can't create a customized kernel that can mimic the KD tree behavior. They just have a single big library implementation for the whole KD tree, and they just call the interface through the already built KD trees. But I think what we are suggesting here is, can we even explain all the behaviors of traversal through the KD trees in a tensor-like style?
I see. Yeah. So I can point you to some relevant work on that line.
Thank you.
Thank you.
So let me see. I think probably we should go ahead and get Paul started to get set up. But Jaeon has demonstrated the admirable quality of if you have a short talk, you get to field lots of questions. So let me go ahead and give the mic to Amanda while we're waiting.
Can you talk a little bit more about for the continuous domain why you're limited to piecewise constant functions? Like, would it no longer work if you were using like a pure differentiable function to represent like some continuous value in your interval?
I don't realize you can.
So you're basically meaning, can we do an extension to more piecewise arbitrary functions, right? So that involves a lot of works. Now it involves like a lot of symbolic computations in it, and we have to build a whole O-frame alpha. So we're trying to avoid going that direction. But I think that's a really cool directions as well.
I see. Thank you.
Awesome. Thanks. Let's give another round of applause here real quick.
Now's the time. So this is
So
working, right?
it's a good thing we brought up differential equations before our next speaker, Paul, who has done a very impressive amount of work on scientific computing, and I'm thrilled to hear what he has to tell us today.
Thank you for your kind invitation and introduction. I'm very happy to be here. I'm actually probably not going to do what you wanted me to do. Bear with me. I want to try and, well, what I really want to do is we have the remarkable privilege that we're all in the same room thinking about common stuff. And rather than talk about stuff you could read in my research papers, I thought we'd try and do something to provoke actual live thinking and perhaps even talking to each other. So I'm going to talk about a huge pile of things. I'm going to do my best to leave time for questions and discussion. The huge pile of things is done by a huge number of people, a couple of whom are actually in the audience today, Tobias and Michael. This talk, well, I went to a really good workshop September last year, organized by a friend of mine, Didem Unat, with some colleagues of hers. And the focus of this workshop, it's been running for a few years, this was just the most recent one, was abstractions for data locality. And what I wanted to talk about today is sparsity from the context of locality. So my thinking is that actually what's hard or interesting about locality from an implementation point of view, what's interesting about sparsity from an implementation point of view is very much about sparsity. And I'll say, hopefully, I'll try and make that case as we go forward. So I've got lots of slides, not too many, but I'll have to hurry, but I might skip some because I don't really have to finish the talk. If we ignite a decent conversation before I finish, then my work here is done. All right, a little bit about where I'm coming from, and then we'll dive in. So I've done all kinds of different things in architectures and cache coherency protocols and lots of performance stuff and even some bounds checking. I'm particularly proud of some work we did on pointer analysis, which ended up being implemented in GCC. The best citations are not from other papers. They're from widely used open source code. I think it's fair to say that although we were very proud of it, the impact of static analysis for pointers is pretty limited. Basically, it's really, really hard. And I'll say a bit more about that in a moment. That led me to get frustrated and to think, well, hang on a minute, we talked to all these applications people and they know so much about how their code could be implemented efficiently. Let's think about how we could automate that. And that led me into the world of PDEs, which Gilbert mentioned. So we've built Firedrake. I'll say something more about that. DeVito, you heard a tiny bit about this from Tobias earlier, and PyFire is another. These are all tools that automatically generate the code starting from the equation itself, from the weak form of the PDE in the finite element case. You type in the symbolic maths. It automates the textbook derivation and generates the code to assemble a linear system or to iterate your time step in an explicit method. And the really fun thing about that is it connects you to people doing all kinds of wonderful applications. I've always get sucked into, I tried to pull off the same trick in computer vision with mixed success, but we did loads of other fun things. So I do lots of different things. Let me also introduce this with this idea. I don't know if you've ever heard of it. I do not claim that I invented this term. I heard it from somebody who denies that they said it. But this is the concept of the Turing tax. Okay, so Turing, famous for many good things. One of them was the idea of a universal computing machine, a machine which could do anything that any special purpose machine could do and could be programmed to do it. Part of a thought experiment, thinking about the limits of what could possibly be done, he thought, instead of thinking about all those different machines, we'll talk about one universal one. The Turing tax is the cost in energy, transistors, time, whatever, of running a program on a universal programmable machine versus building the super highly optimized ASIC or whatever it is that would maximally specialize in order to massively to optimize performance to the limit. The Turing tax is the difference. The job of computer architects, arguably, is to minimize the Turing tax. The one way to do that is to become an accelerator specialist. The other way is to try and build machines which are programmable, take you some of the way along that full specialization, but retain programmability. And we see a lot of that in accelerator architecture. So that's the Turing tax. Here's another thought. Compiling's like skiing. So you want to get to the top of the mountain and build an intermediate representation that captures everything that we can know about the computation that we want to do. And once we've got that representation, we can come down the mountain, we can choose the best possible pathway, we can have the most fun. Along the way, there are some ski lifts, right? There's some static analysis that might help us build that representation. And on a good day, they take us a good way up the mountain, and the higher you get, the more fun you have. Of course, in a sense, all of this is a kind of Turing tax in the same sort of sense. It's the price to pay for using a general purpose programming language, when you could have fed the system with a direct representation of the computation you wanted to do that would mean all this analysis wouldn't really be needed. Right? And again, you might wonder how real that is. It's clearly partially real, at least some of the time. Okay. So what we've been doing, for example, in particular with those PDE tools, is trying to build power tools. Instead of something which is good for pretty much anything, we have something which is good for a subset of those things, but massively more efficient when it's the right tool. And I would claim that we're reasonably successful in achieving productivity. We actually raise the level at which people are thinking about their problems. Performance, we automate the optimizations they would otherwise be implementing by hand. And because it's automated, we can automate multiple backends for different platforms. That's the plan. All right. The thing is that it's actually not really the performance that's the most important thing about tools like that. The really important thing is to support the users in making a decision, having invented a new way to model a physical phenomenon. You want them, instead of diving into how am I going to implement this, they code it up, they figure out their model was wrong, they do it again the same day, right? And once you get there, those people are navigating their expertise, right? They are thinking about how to model their physics, for example. And you are taking it from here in terms of building a high-performance implementation good enough that they don't have to be thinking about it. All right, so the point of this picture is if you were exploring a country like Denmark, wouldn't it be great to have an incredibly fast car so that you could see as much of the country as possible? Wouldn't it be wiser to have a guide who tells you what you should actually do? And that domain knowledge is going to transform the experience on holiday. All right. So I was introduced as somebody who worked on tools for PDEs. Here's the compiler architecture for one of them. This is Firedrake. Firedrake automates the finite element method. So it implements a domain-specific language. I wonder if you can see my pointer, which goes by the name of the Unified Form Language. It's embedded in Python. We didn't invent it, incidentally. It was invented by the Phoenix people in Simula. So this is a kind of re-implementation of the same language. That language essentially invites you to type in your PDE, specify discretization. And what the compiler is doing is weaving those things together to generate the code that assembles the matrix, the linear system that you need to solve, for example, or enables you to solve it by constructing a matrix-free implementation. So this compiler architecture has been the subject of quite a lot of iterated design. And another thing you might think about is this is a sparsity workshop, where's the sparsity here? So there's a tensor contraction layer there. Now, mostly that's pretty dense, but in fact, sometimes it has interesting structured sparsity and block structured sparsity. That's a computation which is happening at every element of the mesh, like every tetrahedron of the mesh. The mesh itself, of course, is a graph or something which you can also think of as a sparse representation in some sense. Of course, what we're assembling is a linear system, which is, again, a sparse matrix, whose structure came from the mesh itself. So I could talk to you about all the applications and so on. That's probably not the point. Oh, one little thing. Yes, this. we heard a little bit about how much we love rewriting. And there's a colorful history of rewriting behind this project, but one little bit of rewriting that I thought was really instructive was we did some work I was really, really pleased with on eliminating redundancies, redundant recalculation of things, generalizing loop invariant code motion. And we did it on a loop tree representation down at the bottom here. We later came along, and for somewhat different reasons, it created this tensor contraction layer up here. Then we realized that the loop invariant code motions that we were doing here were in fact factorizations in the tensor contraction representation. And that enabled us to delete thousands of lines of horrible tree manipulation code and replace it with a couple of pages of Python up here that just implements that factorization. And that's what winning looks like, right? That's the art of compiler architecture, is finding the right representation to make a hard problem an easy one. Right. Okay, this talk is actually not really about that. I'm sorry to disappoint you, Gilbert. I wanted to focus on this locality thing, right? What I think, and you might dispute this, what I think makes sparsity challenging is basically locality in its various forms. And what makes locality hard, well, maybe it's just hard, but something that certainly makes it harder is composition, right? When we compose constituent parts, we need to know where our data is, and we need to try and align our iterations and so on. And where I'm really going with this is that the key topic that underpins getting that right is the metadata question. How do I know where my data is? How do I know where my non-zeros are? How do I know how my data is distributed? And in dense systems, that's relatively straightforward, right? We take our grid, for example, and we can just divide it up. And that geometry is a small representation of where our data is. It's a compact representation. In the sparse case, or even simply the unstructured mesh case, you need something much bigger. You need something whose size, the size of the metadata, is somehow proportional to the size of the data itself. And that's trouble. So the game in thinking about how to optimize locality is to try to live with or overcome that problem. Okay, so I mentioned locality, and the textbook tells you there's spatial locality, there's temporal locality. I've added physical locality, and you can argue whether it belongs here or not. But if we've distributed our computation across a parallel machine, then we need to think about where the communication is going to take place. What do we know about how to optimize these things? Well, spatial locality, roughly what we want to do is to co-optimize the layout and the schedule. We want to be accessing the data in the order in which it's laid out in our memory. And that's, well, it's easy when it's easy, and it's hard when things are more rich, when the data structures are richer, the sparsity, particularly with dynamism, this becomes more difficult. Temporal, so the big thing that we know, the story we know for what to do about temporal locality is tiling, right? And classically, tiles are rectangles, right? Tiles are rectangles, and that's a lovely compact representation of how you've partitioned your schedule, in fact, in order to achieve temporal locality. In the unstructured case, we divide our world into patches, but the patches have complicated shapes. And what iterations are in a patch, well, we list them, right? So we again end up with metadata in proportion to the amount of work we're going to do when we visit this patch. And again, that's trouble, right? So we've built that one. When we think about the communication optimization, we also run into problems. For example, if you have a parallel computation here and another parallel computation here, you might think that's great, everything's parallel, we're all good, until we realize that we have a all-to-all communication pattern between them, and we should have tried to optimize across that boundary in a way to minimize that data movement. All right. I'm worried I'm going to run out of time, and this is a monster slide. Should we do this one? A little bit, yeah. So I'm interested in the shape of the data and the shape of the computation graph, and when we get to know these things and how that affects our choices in what we're doing. So in the kind of classical structured mesh, like finite difference stencils, we just know, and we heard about DeVito that does that. In an unstructured mesh computation, like Firedrake, for example, and many others, of course, typically the mesh is not known until you start the computation and load the mesh into memory, but then you do know, right? You do some partitioning, you might do some renumbering, and optimize for parallelism, locality, communication, spatial, and temporal. And then you can stick with it, right? You don't need to change any of that. You can run perhaps thousands of time steps on that partitioned and distributed and renumbered mesh. Of course, sometimes you're in this space where you do things like adaptive mesh refinement. And this messes you up again, right? And again, this is where you really start thinking, well, how big is my description of where the data is and what the dependencies are? And how can I amortize the cost of computing on that description? So one way to do this is to think about everything block-wise. That amortizes in one way. The other is to do it element-wise, but to reuse that schedule many times. Finally, of course, we get into this crazy world where we have things like particles that move every time step. So the interaction graph of our computation, this happens in molecular dynamics, for example, is changing all the time. And so in our vision applications, we have similar things where as with each successive frame from the camera, you add observations to your graph representing what you know about the world. And you're optimizing that graph to try and establish the most likely configuration of things in your world. And each time you add some more edges, you need to re-optimize. Another lovely example comes from our work on pointer analysis, actually, where we have a graph representing what might point to what else, and then we have an assignment using a pointer that adds edges to that graph. Right? And the really fun thing we did with that, incidentally, is we did an incremental topological sort, because visiting those elements in the topological sort order optimizes convergence rate. That's not a locality optimization, but it's a good one. Okay. This is fairly breathless. Should we take a, how are we doing for time? We're about out. In that case, I will skip to my conclusions and leave you with this. My claim, and we should dispute this if you wish, is that the fundamental issue here is locality. And a big part of that is supporting composition. It's a nice quote here from a friend of mine who works for the Swiss Weather Service. Composition should not be a concern for domain scientists. We optimize components, we invite them to compose them. We should be optimizing across those components for them. And that leads you into this calculation of how to keep your metadata compact, to control the costs of not only storing it, but computing on it, and to manage the amortization of that investment in optimizing for your, the locality of your sparse computation. And finally, just for fun, and this connects incidentally to the immediately preceding talk in some sense, if we were better at bridging the domain expertise, as we've been trying to do with our PDE tools, we might recognize that the sparsity that really makes numerical methods fast is not necessarily sparsity in the representation of the data. It's sparsity in the actual data. A lovely example of this is if you think about a galaxy full of stars, and every star is exerting gravitational force on every other star. So the force matrix is completely dense. Now we know that that force gets smaller with distance. So we do things like build a octtree decomposition. Now we compute the force, which is a matrix vector product, basically, right? We compute the force acting on a star by traversing that octtree and asking which boxes do I need to open in order to answer that query accurately, up to some epsilon. And what we have there is an octtree representation of a dense data structure. The data is all present, but each individual in a product doesn't necessarily visit it all, right? And this is data sparsity, but not necessarily representation sparsity. That kind of thing is a bridge into lots of interesting opportunities. With that, I'll finish. Thank you very much.
Well, we Fred, can you go ahead and start getting set up? Well, we got the importance of locality and also the importance of compression earlier. So I'm sorry we don't have as much time for questions. It's been compressed out. But Paul, if you'd like to take one question real quick while we're switching, who do we have in the audience? Does anybody have a question they would like to ask? Matthias.
Very nice talk, and I'm curious about your opinion. So you talked a bunch about the challenges of metadata and partitioning things. Many scheduling algorithms come from the other side of saying we try to be adaptive because you will not get the metadata handled and you will not correctly partition it anyway. So we try to compensate that by exponential decay of task sizes and many other things. So what's your take on pushing some of those problems into the scheduling algorithms?
So scheduling algorithms operate on scheduling units which have metadata about their dependence and their access times and so on. I think you're referring to tricks like, what's it called, where you... Right. I mean, I think you're tackling exactly the problems that I'm referring to with some statistics, if you can. I think. Yeah.
Okay. Well, thank you very much, Paul. And let's take advantage of our locality in this room later to chat more about these topics. I'm just going for as many stupid jokes as I can. Someone with a much drier sense of humor than me will take us away with the final talk, and then we will have a panel. Before we get started with that, I should remind you all again real quick that there is a wonderful reception at Copenhagen City Hall after this. So please don't miss out. It's an incredibly special and unique opportunity. And also, we will look bad if we do not eat enough of their pancakes, I am told. Why are there pancakes? I don't know either. But if you come with me to City Hall, we'll all find out. Okay, sorry about that interruption. Fred, please take it away.
Now it works? Yep. Yes, okay. Yeah, so I talked to Paul a little earlier, and he was saying that this workshop has shown how much scope expansion there is and mission creep, because you start with sparse linear algebra and then you have databases and all sort of stuff. So I'm going to try to mission creep as much as I possibly can. You can consider this talk just a summary of everything that's been going on, because I think everything I'm going to say has been anticipated a little bit in different talks. So this is, I'm going to try to talk about where I think we're going, whether we want to or not. There's a bunch of different applications that we care about, and most of these have been talked about already. You have different domains like computational engineering, and you have machine learning and bio and all sorts of stuff. And we do not want to build, we do not want our languages that we will use to run across different machines to be bound to each of these domains. There's too many domains, so we want to lay it at a lower level. Excuse me, I'm also a little jet lagged. So what can we do if we can't build a domain-specific language for every domain? What can we do? Well, all of the things that we're going to be running on large computers and across heavy accelerators are going to compute on collections of data. And why collections of data? Well, that's where the parallelism is. It's sort of like why do you rob banks? That's where the money is. So we're going to be dealing with collections of data. And there's fewer collections of data than there are application domains. So here's a few collections. You have sets, you have relations like we talked about, you have graphs, you have meshes, and you have tensors and things like that. So in addition to many different types of collections, you also have many different types of hardware, and these are all domain-specific accelerators, including some that are now cropping up into normal machines like GPUs. And all of those accelerators are also working on collections of data, whether it's small tensors, small vectors, or larger pieces of data like a sparse tensor in the case of maybe the Semanova hardware. So we have collections that we want to compute with. We have hardware that can compute on collections. And then we have many different data structures as we've seen. It's not just dense arrays. You have the KD trees that Jayon mentioned. You have B trees. You have hash maps. You have all sorts of tries and sparse matrix data structures. So we have a lot of different data. We have a lot of different types of data structures. So we end up with a bunch of applications and a bunch of hardware and a bunch of data structures. So how can we get on top of this so we don't have to write 50 different domain-specific languages and 50 different compilers? So we need programming systems, but not too many of them. So the reason why we need compilers is because they're a productivity tool. They're not a performance tool. We can always write the code they generate. They're productivity tools that let us generate the code we need as opposed to write it by hand. And if you're going to have a comprehensive programming system that can deal with different applications, I really mean all the applications that we're going to run on supercomputers, not just a few domains. Then we need a small number of high-level languages on which we can write those applications. It can't be 50 languages. That's going to be unwieldy. We need a modular compiler infrastructure where we can have the same compiler infrastructure work on different types of languages in this small family and also be portable across all the different architectures I just saw. Not just CPUs and GPUs, but also data flow architecture, specialized TPUs and systolic arrays, and distributed machines. So we need to be able to plug in hardware as we build different hardware, and we need to be able to plug in different data structures as we've seen. And then we need to be able to generate code that iterates over different data structures, composes different hardware, so you can use the different hardware resources you have available to you. And then you want it to be able to fuse and tile for locality. Locality is key here. And by fusion, I mean fusion across, not just inside one of the languages, but across the languages, which means we have to have a unified compiler infrastructure that all of the languages can feed into. So let's look at what the small number of languages are. And I think the guiding principle here is that we're dealing with collections of data. So when object-oriented programming came out, the basic idea was that we were going to have objects that are each a recursion on the machine. Each object, you implement each object independently, and then you get emergent behavior as the objects are communicating with each other. We want the opposite of that. We want a collection of objects where we define the global behavior, whether it's a tensor equation or some sort of physical laws. And then we want the local behavior of the different objects to be compiled from the global descriptions. So this is a different programming model than object orientation. It's a collection-oriented programming model. And luckily, we have some precursors. Here's a few of my favorite papers. The settled paper from Kennedy and Schwartz that dealt with a set language. And the basic idea was if you could detach the computations from the order in which you iterate over data and the way you access data, you can create a portable programming system. The same idea in relational algebra about the same time. And then there's a wonderful survey by Blalock and his student on collection-oriented languages. And these are good starting points, but we need something that's a little bit more semantically rich. than just these. So here are the 4 languages. They're just languages on different types of collections. So first is the relations, and relational algebra is really good for combining data to form a system. And by system, I mean a system of interconnected objects. A relation by definition is a relation over sets, so it's relationships between sets. Next are graphs. So graphs are good for thinking about local operations. You want to forget about the whole and focus on a piece. Maybe you want to do a mesh cut, or you want to do some sort of local triangle stiffness computation. So very good for local operations. Tensors are good for the opposite. They're good for global operations, where you want to forget about the pieces, shove everything into a large tensor, and think about the whole system as one particle moving in very high dimensional space. And then we want space, which is good for spatial operations, where you're talking about not. So the first one is how do objects relate to a relation. The next one is how do they relate to edges that are themselves objects. Then you have tensors, how do they linearly relate, where the different dimensions of the tensors are sets of objects. And space are how do objects relate through spatial distances with some sort of distance metric in some sort of space. And I think these are complete enough that you can do most of the computations we're going to do on large computers. And these also accidentally sort of hit all the 4 major areas of mathematics. So that's probably not a coincidence. Okay, so let me go through quickly what kind of operations we want on different ones. They're all going to be collection-oriented operations where the operations do not talk about the order of operations or how we access data. Because if you talk about them in your programming model, you cannot port your code without untangling those details. We cannot program with respect to the machine even. So if you write code with respect to one machine, we have to untangle it to port it to a new machine. So we're going to write code with respect to collections of data. So you have the tensor algebra on tensors. You have nonlinear functions like you find in machine learning, but also general functions, foo, applied across different tensors. Stencils, you want to be able to reshape tensors, where it's kind of the typecasting operations of tensor, where you compose them together or reshape them into a different dimensional tensor and so forth. And you want recurrences. This recurrence here is the Cholesky decomposition, which is the direct solver that's very common. It's just a recurrence through different tensors. And if those tensors are sparse, you have a sparse Cholesky. Then you have relations. And relations, they're the most complete, probably, of these, where you just want relational algebra. So here you see the different operations we've seen before today. And here's the triangle query expressed in relations. And then for graphs, you really want local operations where you can zoom in on a piece of the graph and just do a local operation there. And you probably do that for all vertices at the same time in parallel. But you want more general graphs. You want hypergraphs, and you want graphs where edges are themselves objects that can be connected by other sets that are also edges. So you can get hierarchies, like a cell connects faces, connects edges, connects degrees of freedom. So you can get meaningful hierarchies like that. So here, for instance, you have a tetrahedra where you have a hyper edge there that connects multiple vertices. So that way you can model meshes with just graphs. And here the same thing is shown, where you have faces connecting edges, connecting vertices. And that would be a triangle in a mesh. Okay, and then finally the spatial operations. They have to do with how objects relate through space. So here are some objects scattered around in space. Maybe you want to do a range query, like in a spatial database. Or maybe you want to express a collision detection because you're implementing a simulation. Here's collision detection in a small functional language. And here's ray tracing in a functional language. This is ray tracing, that line. So you can express them very compactly if you have a good language. Of course, these are not optimized. That has to happen by the compiler. You have to have data structures underneath this that accelerates all of this. So you want these 4 collections. So you want ways to move between them, because an application is not just going to be a mesh. It's going to be a mesh plus linear algebra, for instance. There's going to be multiple different abstractions in the same application, and you need ways to move between them in the programming model. And then you need a compiler that can remove the cost of those transitions, so you don't actually move data. Just because you translated a graph into a matrix doesn't mean you have to actually move any data. You can just push that linear algebra back onto the graph, for instance. Here's a couple examples. So this is a relation here that turns into a matrix. So 2 of the columns turn into dimensions, and the last column turn into the values of the matrix. Here you have a piece of a simulation application where you have a hypergraph that describes a mesh that turns into a matrix. You compute on the matrix to maybe compute some dynamic simulation, and then you project that back onto the mesh, which is a graph. And then if you, the type system here relates triangles and the degrees of freedom to the types of the tensor. So that's the relationship between the different data models. They're all dealing with sets. Everything are sets. And then here you have, I've taken the same simulation and I added collision detection, where you add a couple of matrices that model the collisions, and then you have 2 colliding dolphins at the nose there, and they add into the linear system, and then you can compute with that. So you get 3 different data models in the same application very naturally. You don't want 4 compilers, and you don't want this to be too complicated. So you want all of these languages to be compiled down to one unified intermediate representation where you have a single language. And that's possible because everything here is dealing with sets and iteration of the data structure, and obviously so, because when you have collections, you iterate over data structures. What else would you do? So it's all about iterating on sets and bags and iterating on relationships between sets and bags means multisets. So for instance, a tensor is just a linear relationship between different sets. A relation is a relation over sets, so it's a relationship over sets. And space is just relationships between the objects themselves through space. And then graphs are just connected by edges, so also just relationships between vertices. So that means that we can start to think about all of these as some hierarchical traversal through different sets that are connected in some way, whether it's through a relation or through a matrix or through a graph. So here you see the sets on this tensor getting turned into a one of these coordinate hierarchies. And then we can have loops that just run over the different sets. So a triply nested loop, and if there's multiple different data structure, we can do co-iteration with known techniques. Same with the relation, same kind of hierarchy. Same with the graphs, same kind of hierarchy. And then these get a little wild. The object in space, the trees there end up being space-filling trees, like Katy trees and things like that. So whereas these will be 3 nested loops, these are going to be some sort of recursion over a space-filling tree, like a bounded volume hierarchy. But still, we are iterating over sets and collections of sets and the relationships between sets. So I think it's possible to build such a compiler where we can take the different operations, put them all together into one compiler infrastructure that has a very general IR that's just about iterating over sets. And then when you have that IR that iterates over sets and relationships between sets, we can compile that down to specific code that iterates over specific data structure. So the IR will be abstracted from the specific data structures, and then you can embed that as you compile down to low-level hardware. And I think it's possible to make that portable across all the major architectures. We've seen in our research how to compile the sparse tensor algebra to CPUs, GPUs, distributed machines, data flow hardware, and also to TPU-like hardware. So I think that's possible for the other people have shown the same with relational algebra, and I think it's possible with the rest too, of course. So that's my talk. Thanks.
Awesome. Thank you, Fred. It looks like we have one question from Matthias. If somebody else has a question, I will go with them in preference. Sorry, Matthias. Olivia, Fred's your advisor. You can ask him later. Okay. Let me get a question from Tobias real quick. And could everybody who is a speaker in the session make their way up to the front here so that we can do the panel?
So I saw at the end you made the case that I mean everything is sets and backs, right? So there should be this universal abstraction, right?
Yep. Yep.
And so I'm wondering a little bit like what we've seen in other compilers is that you really tailor abstractions to specific use cases. I'm wondering is there some kind of tension where you say actually like sometimes the same concept looked from a different perspective is more make certain transformations easier, make certain mappings better. So how do you work with this tension?
Well, I think at least for graphs and tensors and relations, they look very similar when you get them down to sort of abstract loops over sets like that. So you can tile all of them, and you can do those kind of transformations. Where I think they become a little different is that, say in tensor algebra, you can make some assumptions because they live in a semi-ring, whereas in relational algebra, it's more general, so you can't make those assumptions. But I think from the point of view of what can you express and how can you optimize it, I think that's very similar. I think mechanically, I think the search space is very different. So I can imagine the code the specific programs will look very different depending on where they come from, and you might need different optimization algorithms to search over that.
So you say there's a global minimum in terms of like a global optimum in terms of how to represent these things versus potentially multiple choices.
Yeah, I think
Okay.
there's a way to get them in such a way that it's not just a union of three things, but it's a more unified thing. Yeah.
Okay.
Okay. Go ahead and take a seat. Yeah. So let's get started with the panel, if that's all right. I will take the privilege of asking an initial question. So something of a theme amongst this session that I think Fred spoke to, but I would say somehow touched less on the heart of it than other people was an aspect of continuous space, maybe not as obvious in Paul's, but really a lot of those DSLs you were talking about are continuous. And thinking about something like octree optimizations for gravitational computations is very much about taking advantage of continuous properties or getting approximations in machine learning. And if we're dealing with that sort of, I mean, it's almost analysis really, instead of these nice finite discrete sets. And I'm wondering if you all have thoughts about where our abstractions are breaking down there at all. If you disagree with that, take a different opinion, but that seems like something different than the rest of the workshop that's come up here.
Something I don't think anyone has ever shown me a code generation strategy, although maybe it lies in the stuff Paul's talking about, is go from first principles to a fast multipole method. Because this involves precisely the sort of analysis that Gilbert, I think, is referencing, where you have to very explicitly handle the different distances that points can have, and based on that, come up with different analytic approximations. And it involves a careful coupling of the data structure and the analysis, and like the structure. And I think maybe a problem, to throw a gear into what Fred is saying, is sometimes the algorithmic analysis and the details of how we do the algorithm need to be coordinated very tightly. Like we talked about attention earlier today. I think that's actually a very simplistic but a very clear example of this. And so, yeah. How do you deal with the case of fast multipole method?
Go ahead, whoever would like to take this first, and then we'll cycle some.
Well, I think you're probably going to do that at a higher level where you design your algorithm. So it's a question of what's your algorithm. Is it the spatial connection between the different planets, or is the fast multiple algorithm your algorithm? And I think you can have languages that kind of try to derive the fast multiple method, but I think probably more fruitful to just express it directly, at least as a first step. And then for the things with the continuous things that Gilbert mentioned, I think there's a very interesting and tricky thing there. Which one thing is you can have hierarchies that follow the objects, like bounded volume hierarchies. But then you can also have hierarchies like KD trees that follow space. And then that plays out very differently depending on which query you do. Do you talk about space? Are you asking for things in space? Or are you asking for collection between objects? And it looks very different.
I guess just to clarify the question a little bit there, like even presuming that there's a set of objects is one way to look at the spatial thing. Another is to say, well, you know, I have a gravitational field. And that's just a very different abstraction, right? And that's more to what Jayon was maybe looking at.
While I was doing this project, I thought bringing all of those geometry stuff and the continuous stuff into a tensor world is the great idea, but while the project goes on, I realized, existing abstraction also works very well. I mean, sometimes existing abstraction is actually the more natural way to think about it, and I don't know the exact answer to be that. But like as an example, GraphBlaz is super interesting project. But sometimes like people from the graph applications say like it's unnatural to think graphs as a linear algebras, though they can have an inherently same meaning. Like I don't know the answer, but I feel maybe unifying all the stuff is a cool way in intellectual sense, but in practical and in a practical sense, maybe having a separate higher level abstractions might be more useful.
Let me pass the mic to Amir.
So I want to actually continue on that discussion. I think that perhaps what Fred was showing was not the language that we expose to the users. I think the language that we can expose to the users could remain at whatever domain they are, but somehow to be able to basically globally optimize across the fuse across these different domains, then there is no other way apart, no other kind of modular way apart from having a kind of same think about them from the same point of view. Yeah, I totally agree that it's going to be counterproductive from the programmer's point of view.
So, this doesn't sound a bit left field. Computing on sparse data is about computing on a compressed representation of a dense object. And that's a really fun game to play. It gets much more fun if you're prepared to consider lossy compression. And this is kind of what numerical analysis is about, right? And we shouldn't be too surprised that we land there if we've got floating point numbers already, right? So we might ask, so we can approximate, for example, a dense tensor as a product of smaller or sparser ones. The question is, how do we know that we've done so appropriately for the context of use? Now, to reason properly, mathematically, about the context of use, you need to think about the action at a distance that's happening in your PDE, or the spectrum of your solution. Or we can step back and say, well, in the machine learning case, we just compute a loss and we optimize. And indeed, in many engineering applications, you're kind of doing the same thing. You're actually solving an inverse problem. You're trying to solve for the optimum design of a wing, for example. And so it's actually okay to approximate. We can put that approximation into the loop and into the system. So it's not quite deriving the FMM algorithm as requested. And what I'm looking for is what we have the right to automate.
Any other quick thoughts on that, or I'll pass it on?
So, building on that, it's interesting that to describe a computation precisely is simple, but the minute you want to describe it more imprecisely, in natural language is so simple, but in programming language it's very hard, because the part of that is most of the time we are very comfortable input output exactly the same in the compiler. Minute you go to compression, the trouble is that the optimization function or the cost function is sometimes more complicated than the computational style. For example, if you look at something like signal processing of we'll say music, the function about how ear works is so much more computation than anything that. So the interesting thing that is, I really like that idea that we can do that and we can incorporate things that actually we lost precision. I mean, like for example, the question is, every physics textbook has a one-line formula. And by the time it reaches code, it is 10 pages. Why we discretize, we do floating point errors, we deal all those things. That is what the 10 pages is all about. Not the formula, still we are doing one-line formula. So if we can also incorporate some of those into this language framework, then have some human has to go and figure out what that, I think that would be really cool. But I don't know, because that function that you have to do that to condition things and stuff seem to be a lot more complicated than actually the computation itself sometime.
Yeah, I think it's one line, and then you have 10 lines of boundary conditions, and then you have about 10,000 lines of code of mesh code and things like that. Yeah, yeah. I think a lot of the code is not just that it's dealing with meshes and different type of data. Part of it is dealing with different type of data structure. Part of it is dealing with the machine and trying to map it efficiently to a machine. And these seem like they're separate orthogonal pieces.
Mapping to machine and stuff, I think, can be mechanized. And where you fall is where you can produce a different answer.
I think
so if you had to produce a different answer, how do you do that? What's the cost function? How do you maximize that? Seem to be a lot of times harder than sometimes black magic. Like for example, in signal processing, it's just a black magic. There's no even equation how to do that. And other places, there's I think where a lot of domain intuition comes from.
So you guys have PDEs, and then you insert some discretization scheme at the side. How is that decided?
So there are two answers to that. Literally, how is this decided? That's a user problem, right?
At least it's separate.
And actually, Teo is a good person to comment on how you select discretizations. You need to select a discretization that enables you to represent the solution of your PDE. And there's a whole world of numerical methods there. What we do is we have one way to understand what the Fadrake tool does is it weaves the PDE with the discretization. So it's a do what I say tool.
Maybe to spin this question in a different way, keep the conversation going, is as well as if other people have commented, like, where should we be drawing that line between the automation that we want to have happen in a sparse compiler versus what we expect the user to do? I think this is really a fantastic broad question, right? Because everything being automatic sounds great until you realize there's somebody on the other side of that automation whose problem it is now, right? And you could just remove that entirely and say, oh, we have a great solution to sparse computing. Write the C code you want, and we'll go ahead and run it. So obviously neither the fully going to one extreme or the other is not satisfactory for us. So where should we be drawing that abstraction boundary?
So yeah, so I first need to admit that I'm not really an expert in DSL design, but but actually we are the users of many DSL. For example, some of my students, they're actually using the Cerebras chips, right? So which actually they also provide their own C style DSL. But actually, while we are using their chips, right, we found out that actually at the very beginning, I try to encourage my students to use some compiler, right? So to really free their life. But then they found out that actually to really touch some of this low-level hardware feature, the compiler actually prevent you from doing that. Actually, and then I talked to the Cerebras people. They told me that they tried 4 compiler for 4 years, but they found out that in the end you have to design like a C style DSL so that many people can really fully utilize their chips. And the one thing I found out that it's because right now the hardware is really evolving quickly, right? We are moving from this GPU so we just moved from CPU to GPU in 5 years, but then actually GPU really now reaching the point that they cannot scale, right? So now we are having this scale out chips very soon. But if the hardware is evolving so quickly, and then many of the problem they are moving from competition actually to communication, because actually one of the key insights we found out that the reason we cannot fully utilize the Cerebras chips is not because actually every single processing element cannot be fully utilized. So actually it's because that the communication become the bottleneck within the chips, right? And we cannot find some very good way to solve that, even those Cerebras people, right? So this actually becomes like a super complicated problem. So then actually I also talked to Michelle, and also sometime in Edinburgh, I said, is there some hint I can learn from the compiler people, how I can compile single process compilation with distributed computing? And Michelle told me, usually this is like a 2 separate domain. Okay, there's nothing really can combine. So this is why actually when Amir invited me to come to here, I really want to come to here to learn if there's anything I can learn from the compiler people, so that I can learn how to combine these 2 domains so that I can free my life of using this new hardware. So this is my personal thinking.
Well, I think it's instructive to think of the PyTorch ecosystem right here, because in some sense, compilers are not about performance, they're about productivity. Yeah. You can always get better performance, or at least the same performance, by writing code by hand. And in PyTorch, the PyTorch ecosystem, they've been very successful of having this library where people can write things in very high level primitives. But then anytime you really need performance, you have to go in and you have to sort of implement, probably in Triton, some sort of special implementation of a specific set of primitives, and then that composes with the rest of your kernel. So I think if you only had Triton, you didn't have the PyTorch library, then you would be in this situation where everything has to be written at the highest performance in the lowest level. Whereas the current situation, you can write your model and then you can go in and you can replace certain components of it with Triton. And I think that's a more productive way. It's almost like the EXO language, right? You can start by having something simple, and then you can start to insert more optimized pieces into it. And then the key is those pieces have to compose with the rest, and that's a PL question.
I think I was recently studying the 3D deep learning stuff, and there are a lot of cool opportunities where sparse tensors can play with. But I realized people are all writing CUDA codes from the scratch because they cannot find any existing well-defined sparse primitives that can be very performed well. Even though we can theoretically say those are the solved problem. So what I'm trying to say here is I think someone needs to pick a very specific data structure and not exploring all the different level formats. We can support this pattern, we can support this data structure, we can support this representation. Someone needs to pick very universal representation that doesn't have to be always performance, but on all cases, but generally generally performance, so that users can actually play with. I think that was the lessons I recently had.
Maybe we could get real quick some closing statements. Is that? Would you like that to be your closing statement, Jaehyun? Okay, so we can march down, and then after we march down the panel, we can march over to City Hall to get our pancakes.
Okay, I didn't prepare a closing statement. I did prepare a question in case nobody asked any. So I thought I'd ask. And this comes from a conversation with Fred earlier, to which he also referred, about the mission creep, right? About the idea that sparse tensor-like representations provide a handle on a very large class of data structures, including, for example, the whole of relational databases. And that sounds fantastic. One of the things you should appreciate in thinking that is that what you're saying is that you can take lots of things and lower them into this representation. And that's fantastic as compiler engineers, because we love it when we can lower into a common IR. The question, I guess, is what do we expect to lose in that lowering? But this was a closing statement, so you don't get to answer.
I think mine would be that I think one of the maybe 5 or 10 most important problems in computer science is portability across architectures, especially as we're going to get more and more different architecture. This has been clear for 15 years at least, that this was going to happen, and it is happening. And I think that's a portability problem, because we can always port our code in assembly languages and C. That's fine, but it's not going to people are going to run out of steam once you've done that once or twice. I keep meeting people who have had tremendous fun for 3 years writing CUDA and have gotten really tired of it, and then they look at Triton, and then they have fun for a year, and then they won't. So it's just, I think dealing with portability is crucial, and I think these higher level abstractions are really getting at that. It's dealing with portability.
Okay. Yeah, so actually, I think, so actually my closing statement would be related to the different definition of the sparsity, right? So where the Amir first talked to me about sparse tensor, right? I didn't realize actually he mentioned about the CSR or these different types of the sparse format. Because actually, for people working on AI systems, sparsity means to them, usually you have like a multiple dense module, really dense, but you have the router to conditionally activate them, right? So that's why I think this is also one of the major reasons why today's sparse AI model has become very popular, but you will find out very little of it actually is using sparse tensor to really do that, because people are actually using different way, right, to really define sparsity. I think this actually, I also see like seeing increasing work actually doing sparsity beyond the MOE architecture, like at the data level. So hopefully in the future, we can find out some unified way we can really merge them together again. Yeah.
Awesome. So thank you all so much for coming to the workshop. I think it was a lot of fun. By a general acclaim, should we do this again next year or not? Yes or no? Oh, it seems like a lot of good support. Okay. So, thank you, Schwabe. We needed at least one contrarian. Well, thank you all for signing up to be speakers for next year. When you put your thumbs up, we had a little recording going. But no, seriously, thank you all for coming, and this should be a lot of fun. Enjoy your PLDI.